Yeah, Roshan, better we can start. I think let them join. YouTube Live, she is working on it. We will make it live.
Sure, Pancha.
Yeah.
Pancha, are you able to see the screen?
Yeah, yeah.
Okay, thank you. Okay, good morning, everyone. Thank you for joining this two-day international workshop on geospatial data science and GeoAI workshop. What I'm going to do in next 15-20 minutes is going to explain about what is this technology innovation hub, what are our activities, where did we start, and what kind of a plans we have. I'll just go through quick an overview on this to kind of give you what is technology innovation hub. So it all started with a national mission on interdisciplinary cyber physical system. Government of India, there's a big drive on Atmanirbhar. So we see that much of the imports what we do today is closely related to cyber physical systems. So Government of India, with the help of DST, they have allocated about 3,600 crores to start this 25 hubs in various streams of cyber physical systems. As you can see from the left-hand side, there are a number of um, areas where we have about 25 hubs, mostly at Indian Institute of Technology, triple ITs, ISC Bangalore, even BITS Pilani. So there are a number of institutes which are hosting this technology innovation hubs. All the technology innovation hubs are supposed to work in these domain areas. For example, you can see at the list 24, where IIT Tirupati is there, in which the positioning and precision technologies has been awarded to us. Now, the aim of this entire mission is to kind of have a knowledge generation, translational research, technology and product development, human resource development, innovation and commercialization. So unlike any other projects, this is mainly targeted to develop products, tools, develop kind of a translational research methodologies for the researchers to convert their work into products. So all these 25 hubs are registered as a Section 8 company. We also have a Section 8 company at IIT Tirupati. We call it as IIT Tirupati Navavishkar iHub Foundation. There are basically four major objectives of technology innovation hubs. The first one is to cater with the technology development, completely focus on positioning and precision technologies. So we kind of look into development of products, tools, IPs, patents. Then the second major objective what we have is human resource development and skill development. In case of human resource development, I'll explain you in detail, but there are a number of fellowships which are available for us to disperse across the country at different levels. Then there are also a number of skill development programs like what we are doing today. We are going to conduct a lot of skill development programs to make sure that we create enough manpower in skilled manpower in next maybe 5 to 10 years, so that under the positioning and precision technologies, we have enough people who can actually carry out some of these programs. Now, when it comes to the technology, as I said, like its positioning and precision technologies is one of the most common, even as we think about it, we are all talking about positioning and precision in day-to-day life. One important aspect is connected directly where we all understand is remote sensing, GIS, GPS, or in fact nowadays we see a lot of non-invasive technologies. So these all come under the positioning and precision technologies. So some of the technologies what we thought we'll be focusing on initially, but this is not an exclusive list, is on quantum-based positioning, which is very important in navigation, especially in the satellite navigation and other important places. Then remote sensing is one of the key areas. SAR interferometry, LiDAR. These are something which is now currently many of us are focusing on to. This is the current technology, state of the art. And coming to the subject inputs and processing, we have precision timing, geospatial data. As you can understand now, there's a big drive in the country to create this geospatial data platforms. High definition maps. Now we would like to have very precise information. So mapping of high definition is very important. And also looking at what are our key resources and habitat maps like natural resource management, built environment. So these are something which are very important for input and processing. And the type of system development, what we thought is looking at atomic clocks. A lot of decision supports can be created, especially when we talk about GIS and remote sensing. A lot of areas where we can create these decision support systems for the stakeholders, end users, industries. And in fact, there's a lot of boom nowadays in this, especially in the decision support systems. Monitoring and mapping of the systems, web-based tools. These are all what we are going to focus. Now, if you take an part in the applications area, we have number of applications. In fact, you name anything which is of national importance, GIS and remote sensing plays an important role. So we are kind of looking at navigation and time synchronizing, precision agriculture, defense systems, water resource or natural resource management, disaster management, social media analytics. In fact, GIS remote sensing, at least GIS tools were very helpful in recent pandemic where people were trying to map and then look into various solutions. Now, what we have done at Technology Innovation Hub is we kind of reached out to the experts across the country and asked them like what kind of an areas we should be focusing, wherein we should be able to, become the world leaders in the positioning and precision technologies. So we have come across some of these 8 important topics, what you can see here. Again, I say this is not exclusive list, but this is something which most of them agreed for. So in positioning technologies, we are going to focus on atomic clocks, navigation sensors for satellites, navigation sensors for indoor localization. This is another area where our Technology Innovation Hub wants to focus a lot. IoT and embedded hardware developments for various geospatial applications. When it comes to precision technologies, this is another 2 important areas where I think there's a lot of scope for all researchers, students, aspiring students. Geospatial data processing and geospatial data applications. And there are some other areas where to create some kind of a infrastructure, very high precise infrastructure, and also a part of communication and network system for positioning and precision technologies. Some of the areas what we are focusing here, you can see defense, navigation, quantum technologies, indoor positioning. These are all with respect to the technology development. When it comes to an application, the process oriented, we kind of narrow it down to disaster management. Precision agriculture is a big thing nowadays in India. It's been there in the West for some time, but now it's kind of taking up very fast in India. Precision agriculture requires a lot of remote sensing and GIS applications and other technologies. Land records is one area where we wanted to focus, which includes the rural and urban. Especially these are useful for insurance and taxation. Then we have other areas like we cannot separate it when we talk about remote sensing with image processing. This is one area. Then data science, what we are here today. I think there's a lot of data collected lot of information collected. How do we extract the features? How do we extract the information from this plethora of collection of data, different forms of data? So data science becomes very important, and data science can be easily integrated into our geospatial data applications as well as processing. Then apart from that, we kind of also look into smart cities and also smart villages. These are some of the areas where we have decided to focus on. Now, what do we have an opportunities at TIH? What do you actually can um, help? I mean, how TIH can help you is what is important. I thought, like I just wanted to tell you, there are 4 sectors as where you can be very helpful, and especially in the 2 of the sectors. The first one is technology development. So we have a lot of funds for technology development. If any one of you have ideas, you want to develop a product, then we'll be very happy to support you. There are only a few conditions that you have to be a registered uh, researcher and then institutes. So this is one area where many of us can join and take an opportunity to build a technology in these areas. The only condition we have is the technology should be at least, we call TRL greater than or equal to 4. That means the technology readiness level uh, is greater than or equal to 4, which means it should be at least lab demonstratable product. Product, when I say, there are other ways of looking product like a software, tools, all these come under that. You should be at least able to have IPs, patents, at least one IP and patent through your idea. But the product itself is important. And the second place where if many of the audience are in students, then this would be of very important thing is human resource development, in which we have internships and fellowships for UG, PG, PhD, and postdoctoral. So in if you're an undergraduate student, we have per project, that is a maximum of 2 students allowed. We'll be giving 10,000 per month for 10 months. This is a stipend available, plus an additional project support of maybe about, depending on the project and all, at the max of 20,000 rupees. We'll be able to support you on that. If you are a postgraduate student, and we'll be able to support you for the entire 2 years of graduation program, plus an additional funds of about 30 to 40,000 depending on the project and proposal what you give. And similarly, we have PhD fellowships, which is equivalent to what we get it with the Ministry of Education. First 2 years, 31,000. The next 2 years, will get 35,000. This is for about 4 years. And of course, if you have completed the PhD and you would like to do a postdoc, that is also available, which we give about 80,000 per month. Now for UG, PG, PhD fellowships, you need not come to IIT Tirupati. You should be registered anywhere, any part of the our any institute in our country. It should be recognized institutes, and you can work from your own institutes. You should find a local mentor from your own institutes, and we'll be doing the rest of the support from here. So all UG, PG, PhD fellowships can be carried out from their host institute. It's not that you have to come to IIT Tirupati and only IIT Tirupati students are allowed. So it is anywhere, anyone from our country can apply if they are registered student from an institutes. Only postdoctoral fellowships have to be at the Technology Innovation Hub at IIT Tirupati. So this is one important aspect of human resource development. And if you are a faculty and if you are from a research institutes want to conduct skill development programs, we again have a lot of funding to do this kind of events, programs, conference, basically to disseminate about the PPT positioning and precision technologies. There's a lot of funds available for skill development programs. In fact, if you can keep visiting our website, you should be able to see in the next upcoming month, there's a series of programs have been lined up. And in fact, if you want to conduct and if you're interested to conduct, please let us know, contact us. We should be able to help you in conducting the programs. The other important aspect as a youngster where I see most of us are focusing is on startup ecosystem. So many of us feel like to create a startup, there's a kind of enthu among the youth where are the youngsters where we feel like why don't we start our own company and then create our own world, right? So even for that, we have a lot of support. This is one of our major objectives where we can support the startups. So if you are interested and if you have a great idea, please let us know. You can come and contact us. We should be able to help you up in setting up a startup and connecting it with various entrepreneurs or venture capitalists and all. So a lot of plans are there. And there are a number of collaborations we are into with different industries, stakeholders, government agencies, national, both national and international. So this is one place where in all those four sectors, our technology innovation hub should be able to help you. Either if even if you're a student, you're a teacher, researcher, and industry, or whatever, whoever you are, I think there is something here where we can combinedly be able to help you and take this technology innovation hub positioning and precision technologies across the country. This is something which is like a quick overview of what is happening here, what we are supposed to do. We are supposed to create within 5 years about 21 products, skill development programs, and there are a number of collaborations we need to create. So it's just an overview of what we are kind of into. As I said, there are a number of HRD programs are already in line, and will be very soon. You'll be seeing on our website series of programs, very high quality programs, uh, kind of being planned. And there are also an opportunity, what we call hub and spoke model. If you come from some different institutes, the institute itself can become as a spoke for us. And as what we are talking about, the activities of hub, the spokes also can do the same thing. So this is like an hub and spoke model. As an individuals also, you can join our team. There are a number of opportunities, number of areas where you can work with the experts, develop products or ideas with the experts. So this is also one of the aspects where as an individuals you can join, if not as an institute. So this is my last slide. We have an hub governing body. We have a great mentors here. So we have from industry, we have from academia, and there's a good team which is leading us all this. So hub governing body as Dr. YVN Krishnamurthy from IST Trivandrum, Dr. Ajit Kalgati from Antrix, Major General Dr. R. Shivakumar sir, he is retired from Army. Then Professor Omkar Dikshit from IIT Kanpur. And we also have Shri PK Vijay Varchia, General Manager SIDBI. Again, the SIDBI is one very important we feel because a lot of scope for the startups whenever it comes to the funding. Of course, the internal team, we have our Director, Professor K.N. Satyanarayana. Then we have our CEO who's going to give a talk tomorrow evening at the end. He's going to explain you what kind of other opportunities or the startups are there. So, Mr. Srinivas Murthy. Then, of course, all this, what you see today as a TIHIT Tirupati would go a major thanks to all our faculty who has been supporting, including Pancha, who is the lead in this conducting this program today. Thank you. I would, if you have any questions, I would like to take the questions now. Let me know if you have any questions. I'll be very happy to answer them.
Yeah, participants, if you have any questions, let us know. So here, because our team members are there, we'll be trying to answer the questions if you have any. And our next speaker is also on the line. So we'll start the next session partly. So before that, I just want to give a quick overview about this workshop, which is going to happen today. So we invited about 8 speakers. So today about 5 speakers will speak, and tomorrow about another 3 speakers will speak. And then we have our CEO also talk about some of the summary of like whatever they are speaking about. We are trying to cover most of the challenging and opportunities and the basic ideas behind the geospatial data science and GeoAI. So they will try to cover from the scratch, like what is geospatial data science and how it is useful to the country, to the world, and how they are, what are all the challenges available, and if you learn this geospatial data science and GeoAI, what are the opportunities which you have. All these things will be will be discussed in the next couple of in the next 2 days, okay? So today and tomorrow. So so let's take another 2 minutes break, and then I will introduce our speaker at 10:30. Then we'll start the session. Hope other colleagues, other participants will join also. Okay, so let me introduce the speaker. So today's the first session we are starting with Dr. Vaibhav Kumar. So he is going to talk about addressing the urban planning challenges using GeoAI. So let me briefly introduce about Dr. Vaibhav Kumar. He is an assistant professor in the Department of Data Science and Engineering in ISER Bhopal. He has a GeoAI research lab in ISER Bhopal, which is addressing many of the urban problems. He is actually a multidisciplinary researcher. He got exposure to geocomputation, spatial data modeling, ML, 3D GIS, and computer programming. He is actually originally a computer scientist by training. Like he did MTech in geoinformatics from IIRS Dehradun. He has more experience and research in this area, especially in the area of urban science and engineering. And he received his PhD also in the same area from IIT Bombay. Currently, he is working mostly on the deep learning framework, which could extract some of the big geospatial data aspects. So it's time for the speaker. So I just hand over the session to Dr. Vaibhav Kumar. The floor is to you. Thank you, Dr. Vaibhav.
Thank you, Dr. Maipan, for this detailed introduction. So I was thinking to give all these details, but you have got it all. And thank you, Dr. Awad, also for inviting me. So should I share the screen now?
Yeah, please. Participant, if you have any questions, you can put it in the chat box also. We'll try to address it.
Yeah, or you can, if you want, you can interrupt in between, and we can have a two-way interaction at any point of time. So that won't be an issue. Okay, so I am going to talk about something which is very important in today's context, and that's related to urban planning challenges. And the tools and techniques which we are going to talk about is GeoAI. So the topic is going to address different planning challenges and the tools that are going to be used or are used, or in future what we are going to use, where actually we are moving in the future. So those are the things that we are going to discuss. So we will be going in this way. So I believe there are people who are also not from a technical background or they must have not been through the topic called GeoAI. So what I will do is I will give a very high level discussion, and I will discuss some aspects of AI, and then introduce GeoAI and why GeoAI is a lot of challenges, and it's not possible to cover or touch upon every challenge. So what I will do is I will show you some of the examples from my work, and also the work which is going around across the globe, which is related to some GUI problems, and how they are being implemented for solving urban planning challenges. So I'll try to I tried to put the examples which are very catchy, very cool in today's context. So let's start with that. So what I'm going to start with is the definition of AI, and the whole idea of artificial intelligence was coined to compare the brain or bring these two entities in sync. So we tried to build a system which could kind of emulate the brain, and the key word here is to emulate the brain of human. So our hope while building this system was that our brain is a form of a computer, and we hope this that we can develop a computer which can emulate brain, and we hope that we can understand how a brain works, and we can emulate that in our computer intelligence. And that was our goal as well, to create computer intelligence through different programming techniques, to do some kind of activities which can make the system as intelligent as we are. So if we coin the definition, so it is derived from this hope and goal that it is the study of ideas that enables computer to be intelligent. And intelligent here is a very kind of a philosophical term in context of AI. So this is a debatable term, the philosophy of AI. So the term intelligent it itself has to be coined before defining AI. But we won't go into those discussions, but we will surely touch upon some of them. So the idea was to develop the computer science concerned with to develop the parts of the computer science which are concerned with design of systems which can exhibit human intelligence. So suppose, and this is the definition from Oxford Concise Oxford Dictionary. So we are limiting the intelligence to humans. So we believe that humans are intelligent. So suppose if there are humans who are not responding in such a way that we can call it intelligent, or suppose if we ask a spelling of a word from a 2-year kid, and we then tell that this kid is an intelligent kid, and then suppose if we ask the same question to a student from, let's say, 12th standard, then we don't call it intelligent. So there are different philosophical theories behind the intelligence. Is human only intelligent species, or is nature also intelligent? So if nature or different other species are intelligent, are our AI, or is our AI actually trying to mimic all of them, is able to capture all of them? So that's a whole new idea of AI. But to this discussion, or to the discussions or the theories that are actually going around in the world, we are limiting it to human intelligence, right? So if to summarize it, from the above two definitions, we say that, okay, we are trying to study the intelligent part of the human, not the unintelligent part of the human. So we are not trying to develop which can emulate a human who is going to do suicide, and we are going to only limit it to the intelligent part and represent those actions. So that's how the term called as rational computing comes. So our system has to take the rational decisions instead of taking all the decisions. So that's the whole idea of AI in today's context, right? So how do we achieve that? So when we say that we are trying to develop systems which are trying to emulate human, how do we achieve that? So generally the theory is that the algorithms are being developed, the algorithms work on different data sets, they give some solution, but where do they actually differ from AI? So AI was actually coined as a generic framework. So the idea in front of the developers, or the idea who actually coined the term AI, was that they wanted to solve almost all the problems through AI. So at that time, there were very limited computational facilities. So they came up with the idea that why do we need to develop certain kind of a system for certain kind of a problem? Instead, let's generalize a framework. And that framework should have generic representation. And whenever a problem has to be solved, all the problems has to be represented in that generic framework. And then that could solve almost every kind of a problem. So AI is actually that generic framework. So suppose in the initial days, and even today, the traditional AI, which we call as AI, was termed as search problem. So there were different search problems, different search techniques, informed search techniques, heuristic search techniques, or evolutionary algorithms. So they all were the part of the traditional AI, where we called it AI as a search. So that was the notion of AI. For example, so this is a problem of the queen's problem, where your queen should not be placed in such a way that they can actually we call it that they should not cross each other's path. So how do we actually generalize the problem? So we can define certain things in that problem, that we should have some input states, we should have some initials, we should be defining initial state, we should be defining what are the actions that can lead to certain states when applied to a state. So we have
evaluation function, that if you apply a function there, then you will reach to a different state. And then you have a goal test, that whether I have reached the goal or not. And then what is the actions that we have taken? What is the path that I took to reach that solution? So that was a generic representation. That is a generic representation of search, that we can actually model every kind of a problem into a search problem. Means that's a big statement, but a lot of the problems can be solved through search techniques. So this is a generic representation of AI as traditional AI. Then AI is also coined as a framework in the terms of knowledge representation. So we as a human have certain intelligence, and we see the environment, we learn from the environment, and that idea is stored in our brain as certain knowledge, and we then infer from the knowledge, and then we take the decision, we do reasoning, and then we take the decision. So decision making is dependent on how we are actually representing the knowledge. So suppose we have a robot, and we have given them some instructions, some knowledge to it, that if you move left, then you will be seeing this kind of a thing. If A is B, then B is C, or something like that. But suppose if we haven't represented that knowledge, right? Or suppose we are developing a robot to actually emulate the person whether he is going to do the suicide or not. So how we are actually going to represent that information is going to decide how the robot is going to act, whether he is going to jump from the wall or is going to take a step back. So if the representation is wrong, the actions can be wrong as well. So the knowledge representation was termed as the key aspect of AI, and that's why it's also known as one of the key pillars of AI, or the definition of AI, that AI is also can be considered as knowledge representation. So there are different techniques through which knowledge is being represented. And the last is AI as learning, which is the modern AI. That's what we understand AI as, that the learning is AI. Yes, it is in the current context. We have developed different models in the late last 10 years or so, which has actually fueled the whole aspect of artificial intelligence in the form of learning. So our agents, our models are now learning from the environment, taking actions which we never believed that they could take, right? So neural networks was developed very early, but now we are actually we are more utilizing the power of neural networks. And obviously these techniques, these notion of AI as a generic framework can be integrated in a single AI system as well. So to summarize this slide, artificial intelligence is a generic framework to solve almost every problem. That is the aim. So we have to generalize any problem in one representation. So one representation can be search, other can be knowledge representation, or it can be learning, which we are going to talk more in this presentation. So there are different areas of AI and some dependencies. We are aware with a lot of them. So for example, search is also used in planning. It's also a part. It can be also a part of machine learning. NLP is one of the main components of AI. Then you have vision, robotics, knowledge representation. So they are very interlinked with each other. That's why I mentioned in the earlier slide that these three can be interchangeably used, or they can be actually integrated in a common system as well, right? So these are some of the main areas of AI, the core areas of AI in which different algorithms are developed, right? So let's move to GeoAI now. So if there's any question till now, feel free to ask now. Okay, so we will be moving to GeoAI. So the idea is that what is GeoAI, and it's actually a combination of, it's a subset of spatial data science. So it takes different theories from different expertise, different kind of subjects such as computer science, engineering, statistics, and the different components are integrated in GeoAI, right? So that makes it a multidisciplinary field, and it helps us to make our geographic information more intelligent, and that's how it is being defined as well, right? So it helps us to look into the patterns, the ideas which were not able to understand before we actually moved into integration of GeoAI with our geographic information. So that's why it's fueling the whole new paradigm of the new smart cities, and the different kind of problems that we are facing in and addressing in the city development, the urban planning context. So it's one of the most emerging scientific discipline, and yes, it's very multidisciplinary. So people from different backgrounds are actually contributing directly or indirectly to GeoAI. So a computer scientist who is developing an algorithm is actually used by the scientists who are actually developing GeoAI based solutions. So they are contributing. A lot of the people who are not even aware about the geography are actually contributing in the area of GeoAI. So that's what is fueling GeoAI. And apart from that, there is something else which is fueling AI, which is what is changed. So in we had algorithms in past. So in fact, it means it can be very it can be new information for some of the listeners, that convolution neural network paper was first published in way back in 1997. So algorithms were always there. So neural network was coined in, I believe, in 1950s, 60s. And way back in 1997, Deep Blue, the AI system of IBM, actually defeated Gary Kasparov in a chess game. And chess game is a very is a game which is considered as a hallmark of intelligence, not from today, but through our course of history. Game is a part of is considered as a notion of intelligence. So we had the algorithms, but the thing that changed is the computational power and the data. So we can see that we are moving to the in the direction where we have a lot of computational power. So we are using GPUs, we are using cloud-based systems, we are using a lot of them, and they are becoming cheap and they are becoming small. So that's what is fueling GeoAI. In fact, NVIDIA company was invited in White House for a presentation on AI, and NVIDIA was never dedicated to AI. They were more into the hardware development. So they are more in the development of computational power rather than AI. But that's the company which is fueling the AI growth. So we can understand that the computational power is the major contributor of the rise of GeoAI or AI techniques or AI paradigm. And the third and most important aspect is data. So we have different kinds of data sensors now, and we have a lot of data which is arriving to us in different formats and different representations, and we need algorithms to handle all of them. And spatial big data is one of the main data which is actually fueling a lot of these developments. So what is actually geospatial big data? So there are different definitions of big data. V's is one of the definition which we can say that we can define a geospatial big data or big data using variety, volume, velocity, and veracity. So there are different researchers who limit the definitions to either of three, or they have also added certain things. So we are now seeing a tremendous rise in the volume of the data that we are receiving. So if you don't even go to the satellite imagery that we are collecting nowadays, we are using we are using social media regularly, we are tweeting, so we are actually fueling the whole idea of information transfer, and it's happening so fast. Right? So everybody is equipped with a good camera, with good sensor, with which can actually transfer the geotagged information, the crowdsourcing paradigm, the semantic web. So all of them are actually increasing the whole volume of the data which was not in the past. Now our databases can hold a lot of different tuples. So you can see we can have 1 trillion RDF tuples we can hold it and actually access it. That's why we are storing the lot of different big data in our database. The data is also having a lot of varieties. So you have 2D data, you have 3D data, you have imagery data, you have vector data sets in the form of line, point, polygon, and then the whole 3D CAD models are now we are able to store it in our databases. We are able to process it in online websites, and through different libraries, we are able to process it in our standalone systems. So a lot of variety of data is also one of the key aspects of geospatial big data, which is not actually in context of other big data which are limited to mostly into the text format or the integer format. So now we have more information in the form of variety, and then the velocity of the data has actually increased. So the information transfer has increased. The information of the speed of transferring the data from satellites to our receiving centers and different organizations have actually tremendously increased, right? So we are now, the temporary information is changing from days to minutes to seconds, and a lot of speed is the one of the factor which is driving the GeoAI paradigm. And then the accuracy of the data sets is also one of the key aspect of why GeoAI is propelling. So for example, we had the images which were in the resolutions of 50 meters, and now we are moving to the era of drones which are giving us imaging the resolution of centimeters. So the problems that we would have never thought of solving at that period, now we are actually able to solve those problems using highly accurate data sets, right? So that's what is the key of GeoAI paradigm: the computational power, the increase in the computational power, and the increase in geospatial big data. And these two, when combined, are actually handling the urban planning challenges. So there are a lot of challenges in different domains. Urban planning is one of the key challenge, and if you look at the pace at which our cities are developing, it's tremendous. So we are seeing the urbanization which we haven't seen in the past. So if we look at the numbers, by 2030 our 54% population will be urbanized, and it's also predicted that by 2050 more than 65% people will be residing in the urban area. And it's just the definition of urban area. Or rural areas, by the introduction, when we introduce the technology, the whole idea of rural domain has also changed. So they are also slowly moving into the semi-urban environment. The mentality is moving to the semi-urban environment. People are actually demanding the solutions which are smart, rather than the brute force technique that was the whole root of our rural areas, right? A lot of majority of people who are actually using the technology are living in rural societies than in the urban. Actually, there was a study which showed that the rise of people, rise of smartphones and the social media has been thrice than compared to the cities in the rural areas, right? So it shows that how much the information has increased, how much the population has been linked to different technologies, and how the urbanization is going to not going to be centered at the core cities, but it is also going to influence the rural areas as well, right? And to support, to cater the resources, to cater the demand, and the demands are huge, so demands are very varied. So you want the safety perspective, you want your waste to be collected in a smarter way, you want good health, you want good smart parking, you want intelligent traffic management, you want good lively conditions. So there are a lot of things that you need in our common life, and those are the only some of the aspects of urban planning challenges, right? And the core of all of this lies the good planning tool and derivation of good policy instruments. And the good policy instrument derivation needs evidences which are actually derived from conclusions, from data, which is driven by GeoAI now. And we are moving towards building smart cities with a very fast pace, and a lot of the topics that we cover now, just this management, smart management, the health, and all those things, they all are slowly uh, moving into the direction of becoming smart. So we are introducing different techniques, the technologies which are making them smart, they are making it a kind of automatized. So we are into that direction. So how GeoAI addresses these challenges? Right, so our slums are increasing, but still we need to do some planning aspect. We need tools to actually figure out where are the slums, what is the condition of the slums, what are the neighborhoods that are actually influencing the slums, or a lot of this. So we need GeoAI for governance, we need different urban planning tools and different kind of problems such as disaster, for planning, for let's say taxation. So we need GeoAI for governance, and we have a lot of data to do that. So researchers who are into the governance can actually look into this idea. We need the safety, we need healthcare, and all of these are being fueled by GeoAI tools. And we need education, we need GeoAI for education, to actually citizen participation. So we need accurate data sets. For example, in the cases different disaster cases, let's say fire. So a basic scenario for during fire is that whenever a fire occurs, people actually call fire station, they tell them some information about the fire, and based on that first information, the resources are being planned and deployed. And many times those resources are not adequate, or they are kind of more than required. And then this actually leads to, we can say that, not a good resource planning or not a good response planning. So we need citizens who are aware to pass the information about such thing, and that requires some technology and requires awareness, and GeoAI is the tool that can do that for good decision making, right? So we need GeoAI for urban economy, we need the GeoAI for logistics, mobility. So our traffic is one of the traffic scenarios are one of the most talked about aspects in our cities. So we can see a lot of information on our websites, social media, that people are actually very concerned about traffic flow and all those things, the environment degradation. So all of these things are actually very linked to each other, right? We need solutions which can actually plan, which are very planned, and are actually can actually serve the resource constrained societies like us. Like we are a very resource constrained societies, and we need to plan our available resources very strategically. And for a good planning, we need good GeoAI tool, good mathematical tools to support it, to come up with a statement that, look, this is the best way to do this, and this is the best way to do this in future, and all those the problems that we can actually face can be tackled by these things, right? So these are the challenges that we talked about, and GeoAI is at the core of solving these challenges. So right, so we covered the different the theories about AI, GeoAI, and how they are actually helping helping solve different problems, urban problems. But it won't be kind of feasible to talk all of this. So what I've done is I've prepared some slides to show you some studies which employed GeoAI to solve different problems. So for example, this slide is related to growth modeling. So we need tools which can actually predict the urban expansion, and based on how the urban expansion is going to take place, decision makers do coin the policies. They come up with the idea that how much greenery is going to be in 2024 or 2034, and they make up different kind of strategies. They define, they coin the techniques, and then they come up with the whole development plan for upcoming 20 to 25 years. So that requires certain kind of growth modeling into that, and that's why it's a very important component, and GeoAI is at the core of it to identify the features in the urban area. So it's a very well researched problem where we actually apply GeoAI to identify different features in the images, satellite imageries, UAV imageries, and then kind of integrate with the information such as the surface maps, and then we get the solutions which are actually implementable. Right, so this is one example of cadastral planning in the urban planning. So our population has to be somehow adjusted in the existing space of a city, and we need different kind of planning tools to support it. So for example, we need to identify where the illegal construction activity is going on, where the taxation is, how to tax the construction. So the green in the bottom left one, the green one shows which are actually the legal buildings, and red one shows which have some illegality info attribute attached to them. Then the information, some information about the building, that the left, the second image from the left bottom is the information related to buildings which are related to which building has some damage component, through which actually the taxation can be done. Right, so the upper ones are the 3D buildings of different areas which show different attribution to the buildings, and how we can play around with these features, and query the aspects, that whether the road, how close is this building to the road, adjoining road, whether it's in the permissible limit or not, how, and then we actually do the attribution and fire multiple queries, and then come up with the different kind of answers which are required for decision making. Right, so moving to the environment, so we are very aware about the facts that our cities are very facing a deep crunch of resources when it comes to the environment. So our cities are most polluted cities in the world, so that's a very major problem, and the images highlight those things. Right, so there can be different studies which model different climatic patterns, and then different data which can integrate different data, use GeoAI techniques to predict different kinds of variables, such as the content of certain particles in the air. So I tried to put some new kind of stuff which maybe it can be exciting for you, for some of the budding researchers who are looking at this PPT. So for example, this is one of the study in the left image. You can see that researchers have used deep learning techniques to extract the greenery over the rooftop and the solar panels, and then they have integrated this information for coming up with the index, which is a green roof index, and solar roof index, and they have implemented it on open source data for whole of the different cities across the globe, and then they have came up with the conclusion that these are the cities which are actually green, and these are the cities which are actually utilizing their roof for solar generation, and they are so much of, and then they have linked it with different urban sustainability parameters. Right, so such kind of studies for Indian context can also be a very good research problem. and is much required as well. This is one of the study done in Beijing, where the researchers have used different urban morphology. They have designed different urban block diagrams for urban morphology, and then they have come up with the idea of which area has more thermal comfort. So if you want to design a urban neighborhood, what is the actual way, can be a good way of actually coming out with a plan which can help you to reduce the temperature in the vicinity and can have good thermal comfort instead of making it more means it to instead of making it more heated kind of a thing. So such kind of studies are very important in that context. So these are two from the environment part, and then yes, in the traffic part where we are talking about mobility and the traffic. So if you have seen this news cuttings, it says the traffic jam in 4 metros costs more than entire rail budget, and this is just for the peak hours congestion. So if we go to any metro city, we face a lot of congestion, and this is now becoming more of a trend in even tier 2 cities in our country. So traffic is one of the major areas where GeoAI can play its part, and it's playing its part. So for example, for the safety aspect, location aware driving is one of the research problems which is in the open domain. So the researchers are using highly accurate location data from GNSS, and then combining it, integrating it with network data, and then using different sensors, remote sensing sensors. And then as a whole multimodal system, they are coming with the idea of location aware driving. So you know which car is beside you, behind you, at what distance, and then some level of automation can be done in that context. The right one is the image where the tweet concentration for some roads, for the major roads, was being extracted, and the GeoAI techniques were applied. So if a person tweeted something from major roads or about major roads, that was being fetched, and then it was being processed, and then we get such kind of maps, which can be a very important input in some decision making systems. Similarly, we use computer vision algorithms to actually identify what are the different type of vehicles moving on the road. Then you quantify the congestion in terms of vehicle, and then you know which are the hotspots which are actually related to what kind of vehicles, and then you plan different infrastructure based on that. So the upper one is based the top one is based on that. So it shows that how infrastructure planning carried out based on how the traffic hotspot varied throughout the day, right? And the bottom one is how the traffic planning is done in the real time environment using AI algorithms in Munich. So the computer vision is actually helping them to identify different types of vehicle and the people who are into that area. Integrating it with map as a decision making system, and then we are good to go with a better system than existing system, right? This is one of the work which is being carried out in my lab, and it's in collaboration with Professor Bharat Lohani from IIT Kanpur. So we are actually simulating the data. So the researchers have said that after around 2025, the data will be more of the simulated data that will be used in training AI, because it's not feasible to actually collect a lot of real data, annotate it, and then use in the modeling. It's a very time and resource consuming exercise. So instead, we can generate our simulated data in our lab for different kind of environment, and then use it to train our systems. So for example, the left one shows the images, stacked images where camera is actually on infrastructure for a road intersection, and the bottom one is for a camera on a moving vehicle. So suppose we are actually moving on this road and we want to actually plan our speed, we can actually use this information on the information from the infrastructure to plan how the congestion is at the junction, whether at what speed he should be optimally driving from location A to location B so that he can save the fuel. Also, different kind of problems can be addressed using such kind of simulation. And the right one is the generation of LiDAR data using a MLS setup mounted on a car, and there are dynamic objects in the scene, and then using physics equations we generate LiDAR data. So it's work in a progress, and I believe Professor Bharat Lohani later tomorrow will also discuss some of the aspects of these. So these are one of the key aspects of the futuristic mobility and traffic planning, the safe movement planning. So all those can be taken care of using the AI techniques, the GeoAI techniques, right? So moving to disaster management, our smart cities, which are actually going to be the next our next talking point. Our cities are going to be converted to smart cities. We are in that process. It's a ambitious exercise. So we are not looking into the disaster management more than the other aspects. So it's lacking in some of the smart cities plan, and it can be a stupid exercise if we don't go by the disaster strategy, integration of disaster strategy in smart city development. So for example, Mumbai still is lacking more than 66, I guess, fire stations than it is required. So we need a good resource planning tool which is driven by the empirical evidences, and GeoAI comes into the picture. And then you have different disasters such as earthquakes. So for example, this image on the top right shows the damage assessment quantification using LiDAR data, right? So it's not just the assessment, it also helps government to plan how to spend their money as a part of the plan, where they give certain help to the people whose buildings are damaged or they face certain consequences. So we need highly accurate information in that case, and combined with the highly accurate data, GeoAI does this job for us, right? So this is the top left is one of the study where it shows that how we can plan the fire resources during different time of the day, and based on the different change in the patterns of fire. So the top right is the image which shows how the fire intensity and location pattern is changing over the day for 2 years. It was for 2015 to 2016, and then how we can actually come up with the idea of small fire stations which can be dynamically shifted throughout the day, and can be also used to cater the demand of congested areas, the slums, the informal settlements, where the smaller fire engines, the smaller dynamic engines can be shifted throughout the day and can cater the first step demand and also the existing demand, right? So there are different other disasters where GeoAI is a very important tool. For example, the left bottom is of the tweet map of Australia, where cyclone was going to strike. So social media is a very powerful sensor nowadays, where the geo information is helping us to understand what people are talking about certain kind of a topic, and what is their responses, what is their sentiment about it, and then the decision makers take the decision based on the real-time scenario, which can be actually done through the tools like NLP, right? The natural language processing. So the disaster management has other certain components as well. So this is related to route planning. So we want our convoys, our resource teams to move through a certain rescue path. We need optimal planning. We need supplies, warehouses, bunkers. So we need logistic management for that. And the top one is the top right is the diagram for the image of a route planning system in 2-dimension, and the below is for a 3-dimension system, where these systems can be implemented to use for rescue and response, right? And then we can integrate all these ideas into geographic information systems, and the good emergency response system can be developed, right? Then you can use 3D information as a critical component in almost every aspect of planning, including disaster management. So we can define certain threat envelopes, that if a bomb is going to be exploded, what are the buildings that are going to be infected, what can be the level of that impact. So these diagrams show that. Then you have different simulation based scenarios. So simulation is going to be the future of different GeoAI systems. So you can simulate different scenarios like in a game engine related to different disaster cases. And then in advance, so you preempt in advance how the environment will be, how the people will respond to different cases, how the troops should be placed, how the rescue plan should be carried out. So simulation is a very good tool for that. You can create multiple scenarios for that, any kind of a condition, right? So you can have autonomous system based on simulation perception engine, which can be used for different as a rescue vehicle in different disasters where people are actually moving in a haphazard way, right? So these are some other ongoing works in my lab related to our planning challenges. So one of them is gender classification for LiDAR data. So gender is a very important component in decision making system, whether it is a disaster or whether it's autonomous driving or any decision making system. We need the information of how is the crowd behaving, right? Or who is for taking any cognitive decision. We need to know whether the human is a woman, child, or a male, and then we take certain decisions out of it. So gender classification is one of the problem. And then you have route planning for waste collection. So we talked about smart waste management. So this research is related to how dynamic information of smart bins. So the information such as how the volume of waste is changing in different bins at different locations, and based on the condition of different collection vehicles and their limits, the dynamic paths are being calculated for smart waste collection. And this study is related to perception modeling. So integration of images and audio are being used to create a perception of an environment, and then based on the perception, certain decision can be made. So for example, we are doing it for safety. So the same path cannot be safe for you during the day, or it can be safe during the afternoon. And again, the perception of that path is going to be changed during night. So we are actually have come up with the idea of safety driven paths, right? So we are apart from distance and time, we are offering the safety driven path, or we can say the perception driven path. And then we are quantifying the greenery and open spaces for different urban typologies. We are trying to quantify how much is the disparity between the informal settlements, the planned settlements, and how do we plan it in for the future betterment. So we have developed some GeoAI techniques for that, right? So now this is the last slide. So I will try to sum up the whole discussion that yes, GeoAI is the most important component, which is going to drive the whole idea of geospatial intelligence. And by 2025, GeoAI is going to cover the whole 40% of the all smart city applications. So what all the applications which are going to be deployed in a smart city? 40% of them will be driven by GeoAI components, right? And the development of AI driven cities is one of the top enterprise trends. So I was listening to the last presentation where the professor mentioned the idea of startups. So the researchers who are listening here should look into the idea of, or can look into the idea of coming up with good enterprise to solve urban problems using AI, right? So in future, we will have thinking, breathing cities. So we will communicate with different entities using infrastructure, using AI. So we have cities which is thinking, the city which is actually breathing, and you will feel it like a real entity, right? And that's how the cities have been assumed or has been coined by different artists in the past, that cities should be breathable, right? And then the next frontier is that how the whole idea of GeoAI will emerge, right? So we can move ahead from deep learning to meta learning based techniques such as few shot learning, where we don't need a lot of data to train. And then we will be looking into the idea of spatially explicit models in GeoAI. So those models which are considering actually the spatial information, the spatial neighborhood details, the spatial inputs, and the spatial outputs, instead of application of AI techniques to just geospatial data. It can also be in the format of the algorithms which actually consider the spatial aspects in the modeling. So those can be one of the next frontiers of GeoAI and can be used to solve different problems, including the urban planning problems, right? So I will stop here, and I will love to have some discussion on the topic, and you can shoot any problems.
Yeah, participants, if you have any questions, please have an interaction. Participants, any question?
Hello.
Yeah.
Yeah,
Hello.
Divyesh, go ahead.
Yes, I'm Divyesh. I am from National Forensic Sciences University. My question regarding the LiDAR mapping for indoor navigation. So, Vaibhav sir, can you elaborate more into indoor navigation part through LiDAR?
Absolutely, Miss LiDAR is, or you can say, the 3D maps of indoor environments are the key inputs in indoor mapping and planning solutions based on in indoor environment. For example, in evacuation planning, so we are actually developing a LiDAR based solution where we are developing a 3D model of the whole indoor environment and using it to simulate how people will react in when a fire case occurs. So yes, a LiDAR is going to be a very good tool for indoor mapping.
And sir, can we real time get the information like where is the person located inside the premises of the building? So can we get the exact location in indoor inside of the building
Absolutely,
inside?
yeah. So see, the LiDAR is a very good tool to capture the geometry. So even if you don't have lights in an indoor environment, let's say for a cases where you don't have light, then also LiDAR can be very helpful to identify where are the humans in the whole indoor setup. So it is it is a very important tool there, right?
Okay, okay. Thank you, sir. Yeah.
Any other participants? Any other question?
So I hope I finished in time.
Yeah, yeah. Okay, so I have a couple of questions actually. So this, where the India is standing in this one?
So in the perspective of GeoAI,
Yeah,
or yeah, so we are. I think we are in the place where we can say we are at the center of the implementation of GeoAI.
okay.
So if we miss, I will give it through a different example. So suppose we are looking from the urban perspective, the developed countries have their cities well planned,
Mhm.
and that's why they have very limited challenges to address
Mhm.
using GeoAI.
Okay.
However, we are having different cities which have different sort of problems, very complex problems, which are not existent in developed cities. For example, the slum part. So if you want to quantify how good is a slum, how good is the quality of life, you need to know certain information or certain components such as whether the environment is clean or not, how much is the wind, how much is the airflow, how much is the sunlight they are getting. So that opens up a completely new domain of GeoAI where you apply certain inputs and develop a model. So considering that we have certain challenges which are unique, our GeoAI position is, I believe, at the forefront. We are developing the solutions which are somehow better than the developed countries.
Okay. Yeah. And the second question is that, like, how much the funding, of course, our TAH is also funding on this aspect. So apart from that, like, how much funding the government is pumping on this GeoAI and geospatial data system?
I believe geospatial technology is at the center of the planning for the government agencies. So if we have followed, if we all have followed the last few years, government has put a lot of money into it. They have pumped all the resources into geospatial technologies, especially AI. So there is a program of AI for all,
And then we have program where geospatial technology is promoted. So it's all happening, and the government's special focus is on GeoAI, and there's a lot of funding available in this domain.
Okay. Okay. Yeah. So another request, probably it's not about question. So what we are planning is that since you are an expert in this field, suppose some problems which you feel like that would be addressed as as our hub or as a whole country. What you can do is that you can just send me the draft of the proposal or some of the challenging problems which is available, which we can put it in our website, and we can conduct some kind of hackathon or something where the students can come and participate, and then they can solve it. So the funding we can provide from our side, as well as if possible, we can write good proposals with other institutes. Also, part of the funding will be from PA. So that is also possible. So those problems, if we can find out and then list it out, we can put it in our IIT website also, where students can contribute.
Absolutely. Yeah, I will do that.
Yeah. Participants, if you have any other questions, please go ahead. We have another 10 minutes to speak. Aved, do you have any questions?
No, thank you, Vaibhav. So it's a very nice presentation on GeoAI and its application. So thank you. I don't have any question. And any participant who have any question, they can ask in if you have problem to speak online. So you can ask your questions in the chat box. Vaibhav sir will answer it. Okay, in chat box itself. Okay. Thank you.
Some of the participants from industry also, at least 4 or 5 participants from industry also. So if they have any questions which is related to the industry problem which we are facing also, you can just try to ask. Okay. I think there are no questions from participants. So thank you, Dr. Vaibhav. Thanks for presenting your recent developments as well as the challenges and other opportunities available, especially in urban planning and GeoAI. So thanks for giving the nice talk. We'll have some live session. I mean, like we will invite you for some of the workshops in the future also to our TA guides. Right now we are in the transition phase because our IIT, we are in temporary campus and we are moving to the permanent campus soon. So that's the reason we thought to conduct this online and instead of conducting the offline. So from next time onwards, we'll try to conduct offline, and participants can come and have some discussions, because in the online, probably they may hesitate to ask in front, but if it is offline, people will just join for the dinner and tea time. They will be asking the questions personally too. That is really missing that. So we'll have it soon.
Absolutely. Thank you, Dr. Mariappan. Thank you, Avadh. Yeah, and means you can share the email ID and my number with students.
Yeah, sure.
If they need any correspondence, so I would love that.
Yeah, sure.
Thank you.
Thank you. Yeah, the next talk is at 11:50. So we'll have another 25 minutes break. So please stay with us, or you can join back at 11:45 also. We'll start the session in next 2 minutes. Okay. Good morning, all, and welcome you back again. So here with us, Dr. Isapatik Das, who is going to talk about geospatial impact of lockdown of air pollution. So he is actually my colleague in our department. He did his PhD in statistics from Indian Institute of Technology, Bombay. He did his MSc in statistics and information technology from IIT Kharagpur, and later he did postdoctoral research also at Duke University in USA. Then he joined as an assistant professor at IIT Tirupati in Department of Mathematics and Statistics. So he is good at teaching, especially on statistical related areas on data science, etc. So he especially on the topics like spatiotemporal model, biostatistics, and statistical machine learning, etc. So since his expertise is in geospatial and spatial data science, we invited him for this talk. Also, he received some of the research fellowships like UGC Raman postdoctoral fellowship and CICOPS collaborative research run and some of the startup research run also. So with this, I just leave the floor to Dr. Isapatik Das. Isapatik, you can continue.
Yeah, good morning all, and thank you, Dr. Panchajaram, for inviting me for this talk and for this introduction about me. And yeah, so I hope I'm audible. So
yeah.
Okay. So I will share this slide here. Yeah. So the topic here I am going to cover here, the geospatial impact of lockdown on air pollution. So basically, I am assuming that her students are also attending, and they should also follow this talk. So I'll start with very basics. So what is spatial statistics? I will start from there, and how spatial statistics important for in our statistical analysis. What is the difference? What is geospatial statistics? And the implementation, some of the modeling technique for air pollution data, how we can analyze. So that I'll discuss here. So very basics I will also cover here so that student can also follow. So any meanwhile you may stop me. Any students, suppose they are learning stage in the spatial statistics, they want to learn, interested to learn, so they can learn here. So that is my goal. So anywhere you are getting any doubt or any confusion, so you must ask me. I will repeat and I will discuss. So spatial statistics, this term spatial statistics refers to the application of statistical concepts and method to data that have a spatial location attached to them. So this location element is used as an important and necessary part of this analysis. So usual statistical technique what we use. So there also we can use as a variable as a space, but here specifically the space is very important. The term spatial statistics is sometimes used to cover deterministic mathematical procedures applied to location data as in optimal facility, location area, coverage problems. So now we'll discuss what is difference of this traditional versus the spatial. So you may think actually initially we may think that we have all these models developed in statistics, so that also applicable here in spatial statistics. That is true. So suppose if we consider a very basic model, suppose in modeling technique, very beginning we start with a linear regression model, and there we see that this response yi we usually model with some variable beta naught plus beta 1 xi plus epsilon I. So where I is the variable, I is the indices or number of the observation number, I is the observation, and epsilon I we consider it is a normal 0 and sigma square. So here also you may think that in spatial statistics there may be space. So this space S is the space we can include in this model, and then this modeling approach also we can use there. So that is some kind of doubt in the beginning that why the spatial statistics is very much any special thing we have to consider. But in spatial statistics later on we'll understand the technique. So the problem here. So usually, suppose if you consider air pollution, so air pollution is some place. So some place we are taking some data of air pollution, maybe PM 2.5 or Na2 or CO2 presence of, but that is dependent on some the position, which position we are taking. So that is the space here related. And if you consider suppose the nearby position. So here is the one position we are taking some air pollution data, some suppose CO2. And if we consider nearby position, so it is assumed that so this data all contain the observation content similar or very close to if the space is close. So that means they are all independent. We cannot consider. So here in linear regression model we consider that epsilon, epsilon 2, and epsilon n in number of this error or corresponding this variable yi. So these are all independently distributed randomly. But here, by nature of this data, they will not be independent. So they will be very much correlated. So that is the one part that we have to include in the model. So in the spatial statistics, one part is that this all the data here instead of y, we will consider y of s. So or some other variable also we will consider later. So that means it is dependent on the space. Not only that. So this error variable or this distribution of yi will be correlated to each other. So these are some of the reason that we consider the spatial statistics. So independent of observation assumption, spatial statistics operate on data that are assumed to be spatially dependent. So spatial statistics, so we have to consider spatial autocorrelation. So later on we'll discuss it is a spatial process. So have been developed to account spatial autocorrelations. So distribution theory also we have to consider. So other reason is that we cannot get repeated observation always. So in linear regression model, we sometimes say that at a particular position we will take suppose m number of observations. At xi we will take repeated m number of observations, but 10 number of observations. But here it is not possible. In spatial statistics, most of the time, suppose at a particular position we have one data. So that is another restriction that we have to consider a spatial statistics model. So now the name we are sometimes confused with spatial and geospatial. So the word spatial originated from Latin spatia, which means space. So spatial means pertaining to the space or having to do with the space, relating to the space, the position, size, etc. So space means any space. It refers to feature of phenomena distributed in any space, not only the Earth's surface. So usually we consider the problem spatial statistics mean Earth's surface. It may not be like suppose we are considering a disease, particular disease in a body, and we are suppose cancer disease, and we want to spread around that space. So that is also related to the spatial statistics, but it is not any Earth surface. Since geo is from the Greek, this Goya, G-A-Y-A, meaning Earth. So this geospatial thus means the Earth space. So geospatial is that type of spatial data which is related to the Earth. But usually, this is the basic difference. But the terms spatial and geospatial are often used interchangeably. So we can use interchangeably. So United States Geographical Survey, USGS, says that the terms spatial and geospatial are equivalent. So basically, in a layman way, in a broader sense, we don't distinguish. But if you want try to understand any very specific, then we have to understand spatial mean any space and geospatial means related to the Earth's surface. So now let us discuss some of the conceptual things in geospatial data model concepts. So here data represent a simplified view of the real world. So physical entities or phenomena are approximated by the GIS. So geographical information system, spatial location, extent of the physical entities, non-spatial properties. Entity is represented by a spatial feature or a spatial object. So a spatial object means maybe some road that ponds, all are related to the space. Essential characteristics are also defined for each entity. Objects are abstractions in the spatial database. Spatial objects are the object in spatial database representing real-world entities with associated attributes. So, for example, you can see that this is some kind of map, maybe from the Google map. You have seen that. So, this kind of map. So here we'll take some particular position as a data. Spatial data model is mean of representing, manipulating spatially referred information. So data model is the object in a spatial database plus the relationship among them. So here our goal is to make some relationship with respect to the space and our goal, the aim or in interest of the study. Coordinates are used to define the spatial location extend to the geographic object. So usually geospatial data means Earth's surface, and there you know that the latitude and longitude is the coordinate we consider. Attribute or non-spatial data are linked with coordinate data to define each spatial object in the spatial database. So most conceptualizations or models view the world as set of layers. So each layer organize spatial and attribute data for a given set of cartographic and spatial objects. For example, a lake, river, road, etc. So if you consider this kind of some real world, so then we can make like this data layers. So it is parcel, district, streets, soils, utilities, land use, topography, hydrology. So all kind of data we can consider. So attribute data are categorized as nominal, ordinal, or interval ratio. So in our whenever we are analyzing statistically, so different type of variable we consider. So it may be categorical variable or continuous variable, and categorical variable may be it can be classified into nominal or ordinal. So nominal attribute, like suppose there is no order, there is only the category, different category. For example, if you consider color, so color is so blue, black, green, like that. So there is no order, but it is a categorical variable. So it is known as nominal attributes. So vegetation type, city name, owner of parcel, soil type, etc. And nominal attributes can also be images, film clips, audio, or other descriptive information. Images of buildings or surrounding in real estate management database. So now what is ordinal attributes? Ordinal also a categorical variable, but it has some kind of order we assume. So variable that imply rank, order, or scale by their values. Ordinal attribute may be descriptive. So for example, suppose some object we are measuring by suppose in a piece, like we considering some kind of group on a small size, medium size, large size. So low, moderate, high level of suppose concentration something regarding pollution also we can think, ranging from 1 to 5 soil erosion level. So these are some kind of order. These are also categorical, but we can order like small is less than medium, less than large, like this kind of order we can make here. So kind of conceptual that it is a ordinal response variable. Now other variable like we consider it is a continuous. So interval or ratio attributes are used to numerical items where both order and absolute difference in magnitude are reflected in the number. So note that in categorical variable we cannot make the absolute difference. So there is no difference, just different category. But here in the continuous variable, we can consider, so any real number you can think. Here order also there, real number on a linear scale. For example, you are considering area. So some unit is there. And so that you have some real number, area, length, weight, height, depth, value, etc. are presented by interval or ratio intervals. So spatial objects are represented in two most common spatial data models. So here spatial data models begin with conceptualization, how you represent the real world phenomena or entities. Example, a road can be represented as a lines, river as lines or polygon, city or town as the point or polygon. So it is just a representation in different way of the data. So real world data, the road to include the road type, highway, street, like that. So width of the road also you can consider. So that's why here the data is classified into two different types. One is known as vector data model, another is called raster data model. So vector data model use discrete objects such as point, lines, polygons. So all the data you are storing or visualizing like a discrete points. So point, lines represent the geometry of the real world entities, discrete entities. For example, in a road or river, city, towns, lakes, wetland, farm, etc., you can represent by the vector data model. But in the raster data model, represent continuous phenomena that may change continuously across the region. So usually the latitude, longitude concepts, so like any coordinate system, so you all the space you make small square regions and then you give some coordinates. So that is known as raster data model. It is like a continuous continuous data representation. So elevation, rainfall, temperature, soil moisture, etc. Raster model use grid cells for representing continuous phenomena. So here you can see some images. So here vector data model, there is a representation by this kind of line, and this is points, some area. So line, it is like you can think that a road or river, and this is like some city or some kind of here some points mean some poles like that you can represent. And raster data model, you can see that. So we can see that here this is some grid of lines, and it is like a coordinate system. So any point you can associate it with some coordinate system, some latitude, longitude in a earth surface, and then all this space location will be represented in a continuous manner. So any basically in our modeling, or later on whenever in the area of air pollution data modeling we'll consider, you will see that we will consider this kind of modeling concept, this kind of representation. So here more view, it is the real world, and this is the vector data model, and this is the raster image or raster data model. So here in this real world, it is this is as a representation raster, and this is for the vector representations. So vector data model, raster model can represent same phenomena also. So for example, elevation represented surface, continuous field using rastered grid as a lines. I represent counter or equal elevation, discrete objects as a point of heights also. Data can be converted from one conceptual view to another also. It can be possible. There are three basic type of vector objects: points, lines, and polygons. Basically, vector data model, basically points, line, and polygons like this. It is represented, and vector data model, like a vector polygon model in a spatial data model, represent entity which covers an area, lake, building, parcel, etc. So now raster data model defines the world as a regular set of cells in a uniform grid pattern. So usually we see data and modeling, we use the raster data model. Cells are square and evenly spread in a XY direction. Each cell represent attribute values and cell location of phenomena or entities. Cell dimension specifies the length and width of the cell in the surface units. Raster data model represent continuous phenomena or spatial feature. So elevation, so all this precipitation, slope, etc. And raster data model may also be used to represent discrete data also, like land cover, forest, wetlands, urban areas. Raster are digital area photographs, imagery from satellites, digital picture, or even scanned maps also we can represent by raster data models. So now these are all kind of different type of geospatial data model concept we discussed. Now we'll discuss how this spatial statistics will implement, and we define some of the objects. So it is known as spatial process. So spatial random field. So S is a location and D is a subset of RD. R is the D-dimensional space. So basically, if you consider only Earth surface as a 2-dimension, then R2 latitude longitude we consider. And if you consider a 3-dimensional space also, here D will be 3 and S will be some location. So ZS is the observed value. So for example, pollution of the data at some space, some location, or some suppose in data mining, suppose your depth of that position you mine for the data mining. So generic data location vector of coordinates S is the D subset of the index set, subset of potential locations, and ZS random variable at S with realization Z is the observed value. So example, S are XY coordinate of house sales, Z sales price at S. So suppose different houses, some kind of some sales are have been followed, and then what is the sales price at S? And also suppose in different countries, so what is the crime rate in S? Different country, S is the particular position. Now, what is spatial continuity? So here we'll start understanding how spatial statistics is developed here. So basically, so whenever if we are considering like a spatial process, spatial continuity is a feature of the process where data set which are spatially close to each other are more likely to have similar values than two data sets are far apart. So here, spatial continuity means it is spatially some, for example, if you consider a continuous function, so if you change the particular values, the function also will be values close to each other. So as a layman way, we understand that. Here, spatial continuity also similarly we understand that suppose if you change slightly the space, then the value will also not like very much changing. So it is the value will be very much close to each other. Particular location as we have shown. So the picture, so they are spatial continuity means, but how will analyze this spatial continuity? So one of the way to analyze the spatial continuity, it is known as H scatter plot or correlogram. So correlogram that we will discuss. So first, suppose in a particular location xi, suppose we have some ds is the some space, some particular space we consider, and all the xi. So let us if you suppose ds is the some d subset of some R2 or RD in. So in our case, let us for simplification, let us consider this is R2, and we are writing it like this ds. So it is a particular some space we are considering on the Earth surface, and then all kind of location. So this location we usually denote, suppose xi is a vector. So xi actually contain 2 points. So maybe it is longitude and latitude and longitude, and there are many points. We have some data set, and that data set we are considering that is xi. So it is a xi is a vector, and z is some suppose maybe pollution at that point. And now if you consider this notation, so here you will see this notation. It is a minute. Okay. So maybe we have to get. Yeah, this is the scatter spot. So here, this ZX. So what does it mean? The ZX. So ZX is all points considering this all xi. If we vary, then ZX is a set of all points here we consider. So here this is z of x. So xi is all these points in the D. So all xi is all the points in the D. So this is the point. So this is the ds subset of some R2, and all points, suppose x1, x2 like this. So some n number of points are there. So we consider z of x is the all the this set z of xi, such that xi is belongs to this ds. So all these point we are considering here, and then another vector we consider zx plus k. Note that sometimes we used this notation k, sometimes we use age also. So in different author they followed, but we follow sometimes k. So then this all the point xi plus k. So now what is this xi plus k? So xi is a vector. You know that xi is a vector, like xi is this point xi1 and xi2, and if we add some k is also a vector actually. So k is a vector means, so say k1 k2. So we actually adding coordinate wise. So xi plus k means, so this is actually xi1 plus k1 and comma xi2 plus k2. Basically we any position xi, so we are slight displacement from in any direction. So here suppose another point x1 x11 plus k1 comma x12 plus k2. So this is the xi plus k, this is another point. So we are considering the some difference. So this difference we denote by mod k. It is root over of k1 square plus k2 square. So this difference we are considering. For spatial continuity, we will consider these two set of data. So xi plus k, zxi plus k, such that xi belongs to ds and zx. So this variable usually we denote, suppose this variable we denote, suppose this is some vector. So suppose this is the vector v, and this is vector, suppose v, this is, sorry, so vector u, and this is the vector v. So that means, so u contains some points. So u contains some points. So like u and v, two random variables now. So one contains, so like zx1, zx2, like this, and another point, for instance, x1 plus k, zx2 plus k, like this. Sorry, k is fixed here. So like this, zxn plus k. So two a variable we are getting. So note that each variable, this is the value at that point, and if you take some kind of changes in that value, then you will getting this observation. So it may be the pollution. So now spatially continuity means this, if k is very small displacement, then this value and this variable, so they will be very similar to each other. So that is the things we want to quantify here. So I hope I am going very slow, and I think you are following. And if you have any doubt, you can ask. So then we are doing the scatter plot between this zx and zx plus k. So this scatter plot, it is known as a scatter plot. So how this a scatter plot should be looks like? Suppose if you consider two variable have the same values, then this will be on the line x equal to y. So now these are not the same values. We take small displacement. So we expect that if there is a spatial continuity, so then this value will be close to each other. So it will be around the x equal to y line. So now if you vary this k, sorry, here this age, that's what I told here. Sometimes this is I followed. So this is age is the same here. Okay, some displacement. If we if we say that if we change the value age, and if we plot the correlation coefficient, so we can consider correlation coefficient between these two variable u and v, and then if you consider this correlation coefficient and plot it by over the age, then it is known as the correlogram. So we'll discuss again. So here some data set. So data set is about exploratory drill hole samples, which are, it is a rose mining data set, which are drilled by the rose mining. the holes were drilled up to a depth of 10 meter with sample located 1 meter interval. The data has content easting and northing parameter. So there are 3 parameters we consider: easting position, northing position, and depth of the hole. So here it is given, you can see that this is the easting position and north position. So this position, it is transformed to some numerical values, and then this is the depth. So with some units here. So it is just to understand some sample data set we have considered here. And now suppose we want to find this H scatter spot, or is there any special correlation is there? So how is spatially correlated? So here you can see that some point xi, yi. Now if you add xi, xj, yj, 2 points, xi, yi, 1 points, and these 2 coordinates. So this is the difference hij. So depending upon this hij, you will get some kind of pair of value. So suppose if you consider it is the x1 position, and now if you consider age is 0, 1, sorry, this is the one location here, x1, y1, suppose this is. Now if you add suppose age equal to 0, 1, then this first coordinate will be no change, second coordinate will be added with 1. So that's why we'll get this point. So age is 0, 1 here. So that's why this kind of combination it is considered. Suppose if you consider age equal to 1, 1, then both the latitude and longitude we are shifting with 1. So that's why these values will be considered. So then we found this H scatter plot. So it is the Tth position and T plus H position, and then this two set we consider and we plot it. So you can see that these values are very much close to the x equal to y line. So that is the understanding of the spatial continuity. So those who are first time learning the spatial things, so then you may relate that how spatial continuity is understood from the H scatter plot. But from H scatter plot we can understand, but we cannot compare. Like it is age equal to 0, 1, it is age equal to 0, 2, age equal to 0, 3. So as the age increasing, you can see that these values are going away from the x equal to y line. So now how you will quantify this? So that's why there are some measure we have to consider. So one measure is that correlogram that we discussed and the moment of inertia. The relationship between the correlation coefficient on H scatter plot and H is called the correlation function or correlogram. So an alternative index for spatial continuity is the covariance. So basically what we here 1 minute. So this is the one variable u and this is one variable v, and it is depending upon these changes of different values of k. Suppose if you consider this, okay, so here they taken this this variable more understanding. So v is the observed value. V is the observed value is the location t. T contains the vector x1, y1. In the data set, x1 is the latitude, y1 is the longitude, and v is the depth of the hole. So then vt is the depth of the hole at x1, y1 position. Now any age displacement, so age maybe you can consider 0, 1. So some of the value they have considered. So that's why I'm writing those values also. So different values of age, you will get vt and some data set, and another is vt plus h, this data set. So this vt, if we represent by one variable, suppose this is the variable x, and usually in our usual statistics we take two random variable like x and y. So this is, suppose this contains this data vt1, vt2, like this position, and here this data contains this vt plus t1 plus h, vt2 plus h, like this data. And then if you consider this correlation, we say this is I think rho. So depending upon this rho, you will get the correlation between variable x and y, and covariance also you will get. So covariance between h and y. So this is covariance between c of h. C of h is covariance between x and y. So both actually measuring how x and y are associated. So that's why depending upon age, if you change the value, how rho is changing. So if you draw the curve, suppose you are changing values age. So actually because it is one dimension, so we'll take this mod age. So mod age is root over of the coordinate h1 square plus h2 square. So how mod is changing, and then the correlation coefficient. So correlation coefficient should be very high whenever age tends to 0. So So it will be, so the correlation coefficient should be decreased at the age increasing. So similarly, covariance coefficient, actually correlation coefficient between 0 to 1, -1 to 1, and covariance is maybe higher values. And then another measure also we consider. So here, so it is known as moment of inertia. So moment of inertia, like x and y data, xi and yi is the data. So moment of inertia, how it is defined. So I will discuss that. So actually, so moment of inertia. So now if we take this data, suppose this is the x and this is the y. So basically we are taking vt and vt plus h. So this is actually, this data is x1, x2 some value, and this is suppose x n number of values, and here y1, y2, yn number of value. So x1 is nothing but v of t1, and y1 is nothing but v of t1 plus h, x1, y1. Now if depending upon age, if age is close to 0, so then this two value will be very much same. So if we draw this this curve, this is the x variable and y variable, so then this data will be on the line x equal to y. So this line is equal to x, y equal to y. Now if you are increasing the values of age, so actually we are considering, because it is 2 dimension, mod age we will consider. So if we increase the age, then this value we expect that it will be close to x equal to y due to spatial continuity. If there is spatially very much related. So if age is increasing, so this data will be very close to x equal to 1. So like this. So but how it is near to x equal to y? So suppose if you consider any point xi, yi, then what is the distance from this line x equal to y? So this equation is x minus y equal to 0. So this distance is, if we find this distance, so this is equal to you know the formula. So actually distance will take the square of the distance. So xi minus yi whole square by 1 plus 1, so 2. So this is xi minus yi by 2 whole square by 2. This is the square of the distance. So other if you take the square root, then it will be xi mod of xi minus y by root over 2, root 2. So now if we take the average distance, so if we take 1 by n summation of the distance of all the xi yi, so then this is xi minus yi whole square by 2. So this is this 2n, it is coming. So this is known as moment of inertia. So moment of inertia. So now it depends upon xi, yi depends upon age. So this age, so this age depends upon age. Now if we have this moment of inertia, if we wrote with respect to age, this gamma age. So this gamma age, it is known as, if we plot this gamma age with respect to the age, different values of age, if we change the values of age, it is known as, if you plot this graph. So actually it is understood that if age close to 0, then this value will be very much close to x equal to y. So this value will be close to 0. But whenever age is increasing, this value xi, yi, this value will be away from the x equal to y line, and then this value will be increasing. So that is the phenomena here. So this is known as the variogram actually. So somewhere it is also mentioned semi-variogram. So there is some kind of different author described these different notations and different definition also. But here we will understand the same only variogram. So variogram is that whenever you are changing the values of age increasing, so how this gamma age is changing. So note that this age is 0, then gamma age should be equal to 0. So that we'll discuss in the variogram. So but it is I did not make it 0, so it should be like this. So but in practically, so if age is very close to 0, it may not be equal to 0 because of some reason. So that we'll discuss. So when we'll discuss in the variogram. So now, so hope you can see the slide. So this is the moment of inertia. It is defined here. So that's why this 2 factor is coming. So that is the reason that why instead of taking 1 by n, usually if we take average, then we take 1 by n. But here we are taking 1 by 2n. So what is the reason? The reason is that we are taking the distance from the x equal to y, and there this 2 factor, this it is come. It has come. So now for some data set here to understand it. So what is the correlation coefficient for different values of age? Some particular values 0, 1, 0, 2, 0, 3, and 0, 4 it is taken, and the correlation coefficient is like this. you can see that the correlation coefficient when age is close to 0 like 1, this correlation coefficient is 0.742, but whenever age is 0 then it is correlation coefficient 0.590. And like this, you can see that the whenever age is increasing, correlation coefficient decreasing, and covariance also similarly it should because it is just a taken unitless, it is here. So here covariance is also decreasing, but the moment of inertia, as we mentioned from the understanding from the definition, you can see that whenever age is small, this moment of inertia is 312.8, but whenever age is increasing, the moment of inertia also increasing. So here you could as per the graph, you can see as rho is the correlation coefficient decreasing at age increasing, mod age increasing, covariance also decreasing at mod age increasing, but gamma is this momentum inertia, it is increasing when mod age also increasing. So that is kind of understanding of spatial continuity with respect to these measures. So in geospatial data, just again it is mentioned that it is for a not only all this applicable for spatial statistics, for this geospatial statistics here we are considering with respect to geographical area like earth, so mining, air quality, house sales price. So this is the now we'll discuss the how this variogram modeling is important. So this momentum inertia, whenever you are considering with respect to age, so age how this variability changing, that is on the variogram modeling. So we want to consider modeling continuous variation across the space, estimating so how spatial dependence varies with distance, modeling distance decay. So some modeling variogram is used like kriging, so we'll discuss what is kriging also. So variograms show how the relationship zx and zx plus changes with respect to the lag h. So range is the distance at which the variogram reaches the plateau, and the plateau is it's called the sill. So the vertical distance from the origin to the value of the variogram at origin is called the Nugget effect. So here one image it is given, it is the variogram. So here variogram looks like this. Usually whenever mod age it is increasing, so then variogram also increases, but it will not increase throughout. So after sometimes practically whenever you will consider some data, you will see that after sometimes it will not be increasing similarly, it will be like a parallel to the x-axis, and that point it is known as sill. And usually we assume that gamma h gamma 0 should be 0, but it may not be a continuous. So whenever age is close to 0, it may not be that gamma is equal to close to 0, because of that at 0 it may not be spatially continuous. So then we test the limit, and where we limit means whenever age is small displacement and we see the values, and then we approximate this line where it is touching the y-axis, and this distance it is known as Nugget effect. So this is some kind of terminology of the variogram modeling. So why variogram modeling it is important? Because suppose you are for spatial interpolation, we use some of the technique where the correlation between the variables is important, and correlation or covariance if you want to know, then this variogram modeling will be used there, so to understand the variability. So how variogram model we will fit? So because whenever you have data, so but all x and x plus h we will not get all the data points. So data will be given to us with some of the locations. So if you want some data at zx, but at zx plus h you may not have the data. So then how you will find the variogram? So that is some method. Suppose xi, yi, vi denote the easting, northing position, value at ith variable respectively. Then we calculate all the kind of distance. So xi, all the ith, I and j position, and d1 is the minimum distance, and dn is the maximum distance, and this is the range. So then whole range it is divided into some kind of total. So like a histogram here also we consider. So some divided into equal interval. So that interval we have to think how we will divide the whole region. And after now each region, so basically all the data points. So if you have any doubt, or I will assume that all of you are following. So otherwise, if you have any doubt somewhere, you can stop me, ask me. So whenever you have some data like this, so somewhere we have some data like T1, T2, like Tn. So each Ti is combination of this xi and yi. This is a vector, and we have some data Vt1, Vt2, like this Vtn, and consider all kind of differences. So 1, 2, 2, 1. So then this Dij is the difference of some V of Ti minus V of Tj. Sorry, this is distance between the points, not the values. So Di is the distance between the spatial location. So like Ti minus Tj whole square. It is actually, if you take the norm, because Ti are all vectors for all these distance. So then you consider the minimum distance is d1 and maximum distance is dn over the all ij combination. And this length is, suppose here this d1, this is dn. So this is the distance for all the available data points situated like this distance. And then you divide this distance sum of the interval. And this interval, you will find that some of the data points are there, each interval, some of the data points. And then you take the average of this interval, and this is called the average lag. So all this, so h can be now depending given data points, h can be between dn and d1, because otherwise if you go beyond this, then you will don't have any data points. So basically, depending upon the available data point, you find out the this is the gamma h, sorry, rho h, this h, this is the this moment of this variogram, moment of inertia at h, and take the average of this gamma h of that interval and represent by this value, and then you plot. So this is the this some kind of value will get, and then you can approximate by a line, then you will get the variogram plot. So now, so this is the explained here, and then this is the distance and all this value, or all the values situated over the h. So all the values, then you take this gamma ij, all these values. So a empirical variable is fitted under some special variogram function. Then this method is called the fitting of variogram model. Now, after getting this, now you have to find some modeling approach. Usually, what we do that, which kind of model fitting this is act as a data for this. So one is h and another is gamma h. So you have some points, and you have to find some modeling approach to feed these data points. So here, so here in our data, like this data points. So here we discuss this data set. So it is some of part of this data set, this Ross mining data set. So we found these variogram models, and we saw this. This is actually the this is the original curve actually. So it is not a continuous smooth curve. So just we connected all this available average lag at the available gamma is what we found, and then we found. But we want to model it so that it can be used in other like interpolation technique like kriging. So then different type of variogram models are there. So we will not go in details in that direction. To understand it, what is variogram model? So there is different spherical, like exponential variogram. There are different proposed modeling. So some parametric form it is considered, and that parameter is estimated using some technique, maybe MLE or least square method, to find that estimates from these data. So available observations, and then here this fitted spherical variable on the rows data. So some this figure one, blue line indicate actual plot between average line, average variance of rows data, and red dotted line indicates spherical variogram which is fitted on the same data set. So here we saw that range is 475. Seal means where it is actually this flat, it is 135, and Nugget Effect, it is at age equal to tends to 0, it touching the y-axis as 32. So some other variogram also plotted. So now we'll discuss spatial estimation and spatial interpolation. I just want to see. Okay. So yeah. So spatial estimation is the process where estimation is done depending on the distance from the observed location. Spatial interpolation is the process of using points with known value to estimate the value to the other known points. So now our goal, whatever we discussed till now, it is so we covered like what is spatial continuity. From spatial continuity, how we access numerically, or we can understand how this spatially related continuous, like videogram analysis. And next is estimation purpose. So how suppose there are some of the locations we have known value, like air pollution. We'll discuss that some of the point some values are air pollution are measured, but some unknown location we don't have the air pollution. So how we will get that air pollution? So that is spatial interpolation. So there are several approach for interpolating spatially. So in our research here, we also proposed some methods, and we also evaluated this method. We used this method for some data set. We'll discuss that. So one method here to understand, we'll discuss. One is called the inverse distance weight method. So suppose there are n number of observed location. So where suppose we have been given some value. So some suppose air pollution, we know some n number of observed location, and then in a new location we want to find the we want to interpolate or some value. So obviously that new location it is unknown. The suppose air pollution is unknown, but it will be because of spatial continuity, this unknown value will be very close to the nearest neighbor. So it is some kind of nearest neighbor approach. So this known value zx naught is some kind of summation of z of xj lambda j. So lambda j summation j equal to 1 to n lambda. So what is the lambda j? Lambda j we say weighted average. So how this weight will be found? So it is in inverse distance weights, this weight is given 1 by distance between the values. So 1 by distance square. So that means this weight will be higher if the this location x naught is close to xj is close to x naught, then the weight will be higher, because distance, it is inverse of this distance. So distance is smaller means weight will be higher, distance is larger means weight will be small. So it is actually from our understanding that so new observation that will be close to the nearest values. So that's why this kind of methods. So it is understood in this way. Unknown, suppose some data is in a hill, some elevation we want to plot, and that some of the points, these elevations are given, and new points we want to find the what will be the elevation. So then what is the distance, and you take the inverse of this distance. So here this is explained in this here. Each input point has local influence, and that diminishes with distance. Estimate or average of value at n known points within window. So where w is some function of the distance. So this is explained here. So now, so this is same, it is explained. So now IDW is popular, easy, but not the actual. There may be some drawback. So interpolated values limited by the range of the data. So how long you will consider this data? No interpolated value will be outside the observed range of Z values. Now, how many points should be included in the averaging? What to do about irregular space points? For example, here it will see that the potentially under undesirable characteristic of IDW. So here you can see that some elevations are given. So here this data not present. So here only these two data is present. But the reality is that in this way this curve is done. But if you use the IDW, this blue curve. So this set of 6 data points clearly suggests a hill profile. But in areas where there is little or no data, the interpolator will move towards the overall mean, and blue line shows the profile interpolated by the IDW. So that's why it is not refallable. So, later more complicated model it is included. It is introduced. It is another model is ordinally peaking. So here also it is weighted, but this weight actually found by minimizing the errors. So that error I am not going in details. So then we will found this kind of equation. By solving this equation, we'll get this weight. So it is we'll apply this in our research. So where we did in the air pollution. So and also other method also we applied, like random forest kriging method also we have applied. But here beyond the scope today, we'll discuss more application area instead of going through a rigorous the methodologies. So air pollution is the biggest intimidation to public health and one of the primary reasons to cause respiratory hazards and chronic obstructive pulmonary disease. As a result, risk of patient being attacked by COVID-19 virus is too also high. So the air pollution at an alarming level attacks on the researcher recognition so much that influence of different policies, for example, odd and even trial implementation of CNG fuel are also reviewed in detail. So you have we have heard all these things. So here recently this news also it is found. So air pollution exacerbate burden on worker health. Here study says over the years air pollution in Delhi become a significant concern. So these news you are regularly finding poor air quality, extreme weather wreaking havoc on health of Delhi's outdoor workers. So transport sector emission inventory of megacity Delhi has been developed in the period of 2000-2005 to quantify the vehicular emissions and evaluate the effect of relevant policy reforms on total emission of various air pollutants like CO2, CO, all these air pollutants over the year to assist future policy formulations. Emission factor and vehicle utilization factor based approach as recommended by IPCC have been used for estimating emissions. So megacity Delhi, the national capital region of India, is one of the most polluted city in the world, having transport as major source of criteria area pollutants. In terms of emission of various pollutants, Delhi was among the top 5 SO2 emitting megacities of the world in early 90s, and transport sector was the prime culprit for it. This author stated that the emission range of NOx from transport sector is 66% to 74% in Delhi. Central Pollution Control Board (CPCB) data shows that almost 50% of the emission in Delhi is from the vehicular activities, followed by domestic, industrial, and power plants. So according to this author, diesel-driven vehicles were the major source of NOx emission in Delhi, whereas last contribution was from 2 and 3 wheelers. According to the Asian Development Bank, diesel-driven vehicles and the major contributor of PMM this emission among all vehicle categories in Delhi. As a consequence, incidence of respiratory disease in Delhi is 12 times the national average, and 30% of Delhi population suffer from respiratory disorders. Its poor air quality is responsible for about 18,600 premature deaths per year. So these are very serious concerns. Now, some of the research it was also carried out. So some of the literature we here mentioned. So here emission of PM focus area. So it is this Supla et al. 2020 IDW and OK. It is inverse distance weight and the ordinary it is used. And this China spatiotemporal estimation, it is IDW BLSTM perform efficient. This MA et al. 2019. These are all recent years, 2020, 2019 around. Spatiotemporal emission. So it is random forest STK responded satisfactory. How et al. 2020. So Delhi relationship between PM2.0 and other spatiotemporal coverage are explained. So this is Mondal et al. 2020. So some of the research are already done some research. So we will explore some more details about it, and also will implement some new interpolation methods also. So here some of the findings. So the CO2 emission increased by about 24% from 13%. 1 minute. So CO2. Okay. So the CO2 emission increased by about 24% in 2000 to 2005, and from 2000 to 2002 emission decreased by 11%. This is also decreased. Implementation of various emission norms and phasing out a old vehicle during this period might be responsible for decreased emission during 2001 and 2002. Increasing vehicle population led to rising emission between 2002 and 2005. So all these are the previous research. Emission of CO increased by 78% from 197 gigagrams in 2000 to 350 gigagrams in 2005. So gradual increasing trend was observed in emission from 2002 to 2001. Increasing two-wheeler population might be responsible for the gradual increment in CO emission during 2000 to 2005. So all it is mentioned here. So some of the increased and so will not discuss more. So here our study area is selected Delhi, the capital of India, to study the air pollution of before lockdown. So our goal here actually to study whether there is a lockdown effect in the air pollution, because during the lockdown we have seen that the some of the pollutant reduced. So how it is reduced and what is the spatial relationship with the reduced and some temporary relationship also we have studied here. So BL is the before lockdown and DL is the during lockdown. We use this abbreviation. So during the first wave of COVID-19 pandemic in India, it is 2019 onwards. We consider the air pollution data collected by the monitoring station maintained by the Central Pollution Control Board (CPCB). We consider this data set. The data set contains 38 monitoring stations, where the data were collected over 24 hours. The time period was taken 1st January 2019 to 28 February 2021. So all the data we collected during this time. So here before lockdown and the during lockdown we could capture in this period. So this is the map of the Delhi and list of the monitoring station in Delhi. It is given here. So CPCB monitoring stations are given in this black color, and these are the major activity of monitoring station. So Anand Bihar, so it is transport. So we classified into 4 different groups. So with respect to the major activities. So Anand Bihar, IGI Airport and the ITO Delhi, it is transport. RK Puram, Punjabi Bhat, Amgar, Burari Crossing, all these are residential. And the Lodhi Road, Sadipur, these are commercial. And other places like this Mathura Road, DTU, Daroka, North Campus, DU, and Pusa, all are institutional. So these 4 type of major zone we classified, and this is the detail of our research work. So this is PM25 divided the monitoring session on the basis of the major activity 4 classes. So if the data is missing, then we interpolate it using we found that random forest kriging method is the best prediction it is giving. So using this random forest kriging method, we actually interpolated the data, and then we analyzed the data, all these descriptive statistics, non-parametric test, all these things. And if data not missing, then we take the weekly average spatial analysis we did by Morgan I test of the spatial dependency we did, perform IDW, OK, and RFK. RFK is the random forest kriging method, and using those methods we compare these 3 methods, and also we predicted the unknown location, and we try to understand the effect of the lockdown. So this is the time point, what is before lockdown. It is 17/3/2019 March, and this is considered ending date is this, and during lockdown is considered 22/03/2022, 27/06/2022. It is the during lockdown, and this is after lockdown we consider in our study. And some of the descriptive statistical measurement of 24 hours PM2.5 emission during the entire time period. So these are some descriptive statistics. What is the minimum value, first quantile, median, mean, third quantile? These are all reported, and these are some of the distribution of PM2.5. You can see Anand Bihar, some of the places we did, and this is some descriptive statistics also mentioned along with this histogram. And then we fitted using this inverse distance one, but we because of not getting very good result, we modified this method. So we discussed earlier also inverse distance one method, where we used square distance, so distance whole square, but here we used p, d x0 xj whole to the power p here estimated from the data. So so that we get a best prediction, find out p on the basis of minimum RMAC. So this is the new concept here we used in our research. So here we we used p as a parameter, and different values of p we predicted some of the data we consider as a test data and some of the train data. On the test data we found the root mean square error and also R square, and we found in which values of p this mean square error is minimized and R square is the maximized. And we found that regarding, I think 0.6 is 21.0649. 0.7, so between 0.6 and 0.7 some value, it is the RMSE is the minimized. So that p we have used in our here also we can see that this curve. So this R square, it is increasing, and this higher when it is P is between 0.5 and 0.6. And here also you can see that between 0.5 and 0.6, 0.7, some value here. So this RMS is minimized. So that P is estimated, and then we've interpolated other positions, and then we see that during lockdown, IDW this prediction in the before lockdown. So before lockdown, it is between 84 and 108. These are the values. Blue is smaller and red color is higher. And you can see this counter plot of the regions, and 84 to 108. This is the value. But if you consider the interpolation value during lockdown, so this is 50 to 64. So that means 84 is the minimum here, 64 is the maximum. So during lockdown, this pollution PM 2.5 emission is very much reduced. So similar approach, we used this ordinary Kriging method also. So this method also we predicted, and this is also we found that this is 70 to 120 during before lockdown, but whenever during lockdown it is 40 to 80. So that is also we found that this value reduced. And random forest Kriging also similarly we see that it is during a lockdown it is 70 to 120 before lockdown, and during lockdown it is 10 to 60. So this maximum value is actually less than the minimum value of the pollution, and this is the some counter plot. And then we plotted this AQI index, air quality index also. So similar information we found that during lockdown it is reduced. And then we compare between these three methods, IDW, okay, because most of the author actually used this IDW and ordinary Kriging. We actually here used the random forest Kriging, and we are getting very good prediction corresponding this specially autocorrelated with 2019 and 2020 on the basis of RMSE. We can see that we predicted, and then these are the mean square error we found. So suppose if we 12th week, the mean square is 15.46, OK is 12.53, but the RFK is mean square is very small. So it is on the this test data. So we found that this prediction is very good for the random forest Kriging method. So that's why we used a random forest Kriging method for facial analysis also. So here we see the special trend of weekly PM 2.5 emission of the 20th week. Before lockdown, this is the special PM 2.5, specially for different region, how it is plotted. And during lockdown, this is here. So here you can see that this color is deep here in the towards the bottom, and very low in the top. So you can see 70 to 80 some measurement, 81 to 90 this color. So then you can see that 11 to 120. So it is actually 70 to 120. It is distributed here. So deep color is in this location, in this region. So similar things also we get, but during lockdown, this value is distributed 40 to 75. So here 75 is the maximum, here 70 is the minimum. So during lockdown. So these are the observations we see that. So percentage of average decrease of PM 2.5, PM 10 and AQI in different major activity zones because of the lockdown here we found. So PM 2.5 in the transport zone, it is 63.79%, it is decreased due to the lockdown. And residential area, it is 61.31%, and the institutional area 61.38%, and commercial area it is 62.13%. So PM 2.5 almost more than 60% it is reduced during the lockdown, and PM 10 is 62.9% reduced, 54.84 for the residential, 49.83 it is institutional, and commercial 45.73. And AQI index is reduced 11.1, 29.05, 22.71 institutional, and commercial is 26.76. So this is these are the conclusion. The central tendency of PM 2.5 during BL is significantly greater than the DL, which implies that. So we study some other statistical hypothesis also to find this significantly it is greater than, or it is just a randomly it is greater than. So we found that it is significantly greater than the during lockdown, which implies that the lockdown has an appreciable effect on controlling the PM 2.5 concentration. The average pollutant emission in Delhi decreased by approximately 60% because of lockdown. The transport zone is defined as the primary source of PM 2.5 concentration amidst all zones. So the weekly lockdown may be suggested to impose on transport zone to reduce PM 2.5 concentration. So this is just a suggestion because it practically it may or may not be possible. So now these are some of the reference initially what we discussed. We can found some applied geostatistics, this book, and this Noel and Cressy statistics for a special data set, and some of the references for the previous research we found.
Yeah. Thank you, Pratik. Any questions from audience? Any questions from audience? Okay, so I have one question regarding this data set. So this data sets, is it collected from the government database, or is it a real database, or is it a simulated database?
This is from CPCB. This central, sorry, here it is mentioned. This is CPCB.
Okay.
This is from Delhi Control Board. They consider they collect the data set. This is this Center Pollution Control Board. They collect the data set. So I have this some data set also.
So the allied question is like, suppose the students wants to do some research work in this related research. So how do they get this kind of data sets? Because for geospatial data science, especially, the data is the one which is going to drive the model, right? So how will they get this data?
Yeah, this CPCB website it is available. This data set available. Okay. So it is 24 hours basis. These data sets are.
Do they need to pay some charges, or is it?
No, it is free. Okay. Only you have to download. So some website also that I'm sharing. So this is the data set, and I will show some website also. So we downloaded this from the website, this data set. I can see that this region east north PM 2.5 wind direction. So this data set and add more information also there. So we have only considered part of this information in our study. So some website is there, CPCB website for considering the data set for this downloading the data set. So I have to.
So is it only for some specific location, or is it for the entire India it is available?
They have this established some of the center. So in the different locations. So 38 locations are there. So
all over India.
Yes, throughout the area. I have some 1 minute. So there are some. Okay. So
actually, these methods, statistics, is used in most of the area of geospatial. In fact, in SAR interferometry, GNSS, geodesy, all problems, there are many problems related to in which we use I can float you 100 words related, 100 methods related to geostatistics, like rigging, list square collocation, which is used. This is very useful statistical method for modeling geospatial in events actually. So there are many applications of this one. Without this one, you can't even make any software actually if you don't have knowledge about geostatistics. So it's working in this area is you can use some software, but clicking but if you will have knowledge about geostatistics, it will be very nice. So it's a very nice, it was very nice presentation actually.
Yeah, thank you. So this is the actually it is just loading. I think I shared the screen. I think you may see that.
Yeah.
So there will be some, I think, due to network issue, maybe.
Okay.
It is loading. So there will be some of the windows where
Mhm.
you can give some as per your expectation. Then there will be a download option. So then you can download that. So which date to there, which date, your PM 2.5, which locations if you give in the Delhi, then they will that data will be given. You will get this data.
Okay. Any other questions from audience, participants? Any questions? If you have, you can put it in the chat box also. Okay. Okay, I think there are no questions. If you have any questions, you can write to him also. Okay. Yeah.
So
Thank you.
here,
Yeah.
Okay. Yeah.
You
So
want
this.
to some demo?
No. I'm just as you asked me, Central's control room of air quality management. So here in the state also, like state-wise, you can select, and station name we can give some format, and the city name. Then we can download, submit, and we can download. Yes.
Okay. Okay. Thank you.
Yeah. Thank you for.
So we'll join at 2:30. Dr. Ramya will give the talk. Actually, in the agenda, in the abstract book, it was correct, but in the agenda book, there was a mistake. We just copy pasted the same topic of Isapati Kwan. So the topic will be on BILA remote sensing. So we'll start at I think 2:30. And please join for that. I'll end this session now. We'll start again at 2:30. Thank you.
Yeah. Thank you.
Good afternoon, Dr. Ramya. Good afternoon, Dr. Ramya. We are not able to hear you. We are not able to hear you. Could you check your mic?
Hello, can you hear me
Yeah,
now?
yeah, now I can hear you.
Okay, thank you.
Yeah, thank you. Okay, probably we'll start. The participants will join.
Okay.
Yeah, so welcome you all for the afternoon session of today, the Geospatial Data Science Workshop. So here with us, Dr. Ramya from IIST is with us. So she is going to talk about LiDAR remote sensing opportunities and challenges. She is working as in the area of remote sensing and image processing at IIST Trivandrum. She received her PhD in remote sensing from IIST Trivandrum, and she did her MS in remote sensing and spatial analysis from University of Southampton, UK, and BE in geoinformatics from College of Engineering, India. She has about 18 years of experience in handling both processing and handling and processing of geospatial images, especially on the multispectral, hyperspectral, and LiDAR sensors captured images. Okay, and also like satellite, airborne, ground-based images also she has handled. She has published several research papers, and she is the recipient of Commonwealth Award from Government of India and Government of UK for her master's program at UK. She recently got award from Kerala State Young Scientist Award also from the government of Kerala on the area of for her contribution in geospatial technology. Apart from that, she is reviewing many of the reputed journals, including IEEE, GRSS, and International Journal of Remote Sensing, etc. And also, he is the executive member of ISRS Trivandrum chapter, which is and vice chairman of IEEE GRS Kerala chapter. So, this brief introduction, I leave the floor to Dr. Ramya to talk on LIDAR remote sensing. What are the opportunities and challenges available? Thank you.
Thank you for the introduction. I'm not able to share my screen. It says host is stable.
1 minute.
Can you please enable it?
1 minute. 1 minute. Yeah, could you try now?
Can you hear me?
Yeah. You can share now. Yeah, we are able to see.
It's now in full screen. Can you see it?
Yeah, we can see.
Okay. Thank you. So, good afternoon to all. So, myself, Ramya from Indian Institute of Space Science and Technology at Trivandrum. This is part of Department in Space. So, I thank IIT Tirupati for giving me an opportunity to talk on this workshop on geospatial data science and GeoAI. So today I would be presenting on LiDAR remote sensing, which is one of the new domains in a different domain as far as remote sensing and geospatial is concerned, and the opportunities and challenges which are available for researchers to proceed with this. So with this brief background, I'll just start with my talk. So this is the overview of the talk which we are going to see. I'll just give a very brief intro to LiDAR and how it works and how we capture the geospatial LiDAR data and how it is different from the normal geospatial data that we are used to see, and some of the open challenges with respect to the data processing of the data, and some of the open research opportunities that is available. And also I'll highlight upon a few open LiDAR data sets that as a researcher we can straight away start using it. So this is just the overview. So again, moving on. So LiDAR, so light detection and ranging. So before we go into that, so LiDAR looks at the world differently. So it is going to see the world in 3D as we see it. So we are used to seeing things in 3D. That is how we work. So like even if I'm going to give you a 2D plan of a building and a 3D plan of a building, I'm sure that most of us are going to go with the 3D plan because that is more to the reality. Another simple example as far as geospatial is concerned is this is a very common application with respect to remote sensing, in which how this flood data, if suppose flood simulation modeling, in which if suppose a flood affects a city, how much area is it going to inundate in, etc. But if you look at this, here we see as if like all these areas getting inundated. But in reality, sometimes when we have like a multi-floor building, only like a single floor building gets completely submerged and the others might not get affected as it is. As if it is a single floor building. So this, so the impact would be less, and this would be better quantified if I have a 3D model. So this is an example of why 3D is needed. And I'm sure that all of us are familiar with 3D data, and now it has been there into multiple applications in robotics, self-driving car, 3D mapping, medical images, and augmented reality. So now the question on why LiDAR. So amongst all the remote sensing geospatial technologies which is available, starting from the normal optical to the microwave and to hyperspectral and different technologies which are out there, one of the most important technology which would enable us to capture or generate the 3D data over the larger surface at a shorter time at an unprecedented accuracy. I'm talking about centimeter to millimeter accuracy, very accurately, is LiDAR. So this is a unique technology, different from the normal other traditional remote sensing technology. And if we look into the LiDAR in the mapping market, how it is like penetrating into this geospatial community as a whole, you can see the growth in the market share that LiDAR is occupying, and you can see how it is growing over the period of time. So setting this as the context, we'll be talking more on LiDAR and how it can be used for different applications. So LiDAR means light detection and ranging. So it is similar to radar, except that instead of radio waves here, we are going to use light waves, and it allows us to capture the elevation of a surface at a very faster rate. So it usually operates in two wavelengths. One is in the near infrared, which is for topographic mapping, and another in the green region, which is for the bathymetric application. Because as remote sensing person, we will be all familiar that NIR gets completely absorbed in water domain. So we have two different wavelengths. So this LiDAR, as a sensor, we can place it in airborne or airborne satellite. First I will just talk about satellite, then airborne, then I can even fix it on a tripod and make measurements, or I can fit it on a car and use it for measurements, like I use it in my autonomous driving, etc. So airborne, again, I can have helicopter or aeroplane and so forth. So so how it works, as I told, this is a ranging technique in which I send a pulse, it goes, hits an object and it comes back. So based upon the time it takes, we find the distance of where the object is away from us. So the key enabling technology for this LiDAR is basically, apart from the laser scanning, etc., we need a precise GPS. So as such, it is going to measure our Earth surface. So relating to the IIT Tirupati's hub, as in we talk about precision and precision positioning, here we also require a very, very precise GPS location. To be more specific, a DGPS. Okay, so which I'm sure other people might be aware of, it will be able to deliver a less than centimeter level accuracy. So this ALTM or airborne laser terrain mapper, it combines basically, it's not only ALTM, even for a ground based or mobile based, the concept is the same. So we have a laser sensor, and in combination with her DGPS and a INS, we get the point clouds. Okay, so the term point cloud I'll just explain in a while. So this is basically what we get, a LiDAR point cloud. So it's not an image, first point here. So it is not like a normal satellite image, which I'm sure most of you are familiar working with, in which I get a gridded, uniform gridded image with each pixel carrying the intensity. Rather, this is a point cloud. Okay, and each of this points in the point cloud is very, very, very precise, and it can because of my DGPS which I operate with, and so this is in my global coordinate system. So that is again because I have my DGPS, I get it in my global coordinate system. And because of the technology that is involved in how the LiDAR acquires the point cloud, I am able to get a very dense looking point cloud. So if we just move on to the LiDAR point cloud processing, and as I had told, a conventional 2D image, if you take, or a 3D gridded image in that sense, like for example, 3D gridded image, I might mean like, you know, your DEM or DSM, it's all uniformly spaced with a intensity value in between. The XY, the origin and the spacing between the XY is fixed. Whereas in the LiDAR point cloud, we call it as point cloud because it is not organized and it is having a ill-defined boundary similar to a cloud. Okay, so there is no boundary. So that is why usually the LiDAR data is called as a LiDAR point cloud. So it is more difficult to process because, for example, if it is an image as such, if those who are familiar with image processing, for this pixel, if I have to get the 4 neighborhood or 8 neighborhood, there are like multiple algorithms available by which I can search for the 4 neighborhood or 8 neighborhood, do convolution operation, all that. But that is not the case with the point cloud. So here I cannot get the 4 neighborhood or 8 neighborhood. So the spacing between the points is not uniform. So that is one of the major challenges that we face while processing a LiDAR point cloud. So it is a voluminous data and it is not only going to have X, Y, Z information, but it can hold, each point can have multitude of other information as well. So usually instead of a normal ASCII file or a text file, I will be saving the LiDAR as a .las or in a .laz format, which is a ASPRS. ASPRS means American Society of Photogrammetry and Remote Sensing approved format. So this is how a LiDAR data is. Now, as I told, this is just a collection of points, okay, and there is no connectivity or anything between the points. So I cannot say, okay, this point is a neighbor of this or anything. So if I just open my text file or an ASCII file containing LiDAR point in your MATLAB or using any tool, what you will see is a list of X, Y, Z coordinates, maybe with other attributes, but that is it. But I cannot make out, okay, this is the point and the next point is going to be put after this. It is just unstructured and it is completely a simple representation of just the collection of points with no connectivity. So because of this, there are severe limitations. So there is no simplification, there is no smooth rendering, there is no topological information. Those who are familiar with GIS concept, you will know like topological information like adjacency. So there is no connectivity, nothing is there with the point cloud. It is just a simple point cloud. So now, if I have to use this point cloud to for my geospatial application, whether it is for urban application or for agricultural application or whatever, the processing that I have to do on this point cloud is quite different from what I would do with my 2D data. So here I have to use, it's not 3D image processing algorithm, it's basically 3D point cloud processing algorithm as such. So the complexity is high, the processing power is high, and the data volume is also tremendous. So it is a challenge. So here, the first step I would do while I'm working with the LiDAR data would be to establish the neighborhood, to reorganize the data such that I know, okay, this is the point I want, these are my neighborhood points. So how do I do that? So I would use, for example, I'm just trying to elaborate on what I'm saying. Usually the data is stored as per the scanning pattern of the sensor. So if the sensor is moving this way and if it is going to do it has a typical scanning pattern. So based upon the scanning pattern, only the data would be stored. So if I'm just going, if I have a text, if I have the LiDAR data file and I'm just going to, plot the first 100 points. This is how it is going to look. Okay, so here I cannot make out anything from this data. This just looks like some data that is put into the line. But if I do some reorganization of the data, in the sense I'm just going to jumble the data and use some data structuring way, then if again I'm going to plot the first 100 point, this is how it is going to look. So what you can see over here is, I'm not sure whether it is visible or something, but this is basically a roof of a building. Okay. So after doing this restructuring, all the points which is going to belong to a particular object are going to be grouped together. Okay. So there are many restructuring algorithms available, which we are not going to go into this lecture as such, but this data structuring and this neighborhood establishment is going to allow me for easy querying and parsing and finding the neighborhood, etc., so that I can proceed with my further work. So once that is done, another thing that I would do is basically registering, because usually whether I'm going to operate from a ground or from an airborne platform or from a mobile platform, it would be kind of taken in, it is like image registration. It would be taken as different point cloud. So in order to get the object that I require, I would need to register or stitch all the point cloud together to get my unique object, in which all my computer vision, my AI algorithms will be used for doing all this process. So once this is done, we can extract some features. So those who are familiar with image processing will be aware that if I have to do some image classification, I need some features in my feature space. But as far as LiDAR is concerned, it is just mostly this X, Y, Z information. So that might not be, my feature space is very limited. So what I should do is I should expand my feature space so that I can, I can apply my traditional algorithms, traditional classification algorithms, or even if I have to apply, my deep learning based algorithms, this feature extraction is very important. So if I'm just going to summarize this whole thing, so LiDAR point cloud data set is very unstructured, it is massive, it is computationally demanding. The data processing is very different from a 2D spectral image processing. The most important thing, the level of automation of all these processes is very, very minimal, as reported by this ISPRS, which is International Society of Photogrammetry and Remote Sensing report. So unlike the traditional images in which all these processes are many of the processes are mostly automated, as far as LiDAR processing is concerned, the level of automation is still very low, and there is a rising demand for 3D mapping in various application sectors like urban infrastructure mapping, forest management, ADAS, defense, transportation, robotic application, etc. So these are basically the challenges and the opportunities in LiDAR point cloud processing. Again, we will go into the depth. So if you look at it, LiDAR can be applied in various applications, from normal urban and infrastructure mapping to disaster, virtual reality, utility mapping, vegetation. All that are many applications which we can use the LiDAR point cloud. So first, today's lecture, I'm going to start with urban, then we'll move on to the other applications. So I hope you are all aware of this term digital twin, in which what we are trying to do is we are trying to create a twin model of our city. So of which, if I have to create a twin model of our city, LiDAR is going to be the most used technology for this aspect, because of the capture and the type of data it can produce. So once I have such a point cloud, the next step would be to create building models, 3D models from the data. So once I have the 3D data, so these 3D models make no use or no meaning to me unless and until I integrate it with my GIS layers, GIS attributes. Only if I integrate it with my GIS attributes, I can do some query on these 3D data. Only then decision makers can effectively use these 3D data for their decision making. So this is the whole concept or the workflow that we have to go with. So again, based upon some of the works that we have done with our students at IIST, I'll just illustrate on how this can be done. So once I have these 3D models as integrated with the GIS platform, not only for walkthrough or visualization, I can use it for these kinds of application, whether it's revenue collection, disaster management, change detection, network planning, energy potential like solar rooftop kind of a study, green space mapping. All these I can use it for. So these are some of the applications. So a simple question. So now that I have a point cloud, a simple thing would be first to detect the building. So visual interpretation, I can see the building roofs, but as such, I need some AI-based method in which all these processing can be automated. So this is called as labeling. So first step would be to label. So similar to our image classification, we aim to label each and every point in the point cloud with a class category. Class category in the sense whether it's building or a tree or a vegetation or a ground or a road, whatever. So assigning meaningful label to each and every point in the point cloud, be it a natural or a man-made object. That doesn't matter. So there are many techniques available: point-based labeling technique, object-based labeling techniques, and even now deep learning-based techniques are also getting popular. So this is again in one of our works, we have tried to apply object-based technique to a super voxel based object-based technique to label each and every point in the point cloud with using a benchmark data set, and our algorithm was found to be amongst the top 5. The paper you can refer to. Apart from this, so this was in 2016 around. Now, after that, some deep learning architectures are also becoming popular, like this .NET++ and RandLA.NET in 2021. So these are some of these, then KPCon was there. So there are many deep learning architectures are also coming up for this semantic labeling. So semantic labeling is not still a mature topic as such. So buildings, yes, it can be now labeled with around 96 to 97% accuracy. However, the challenge comes when we have data set, like this is a aerial data set that we have recently captured over Trivandrum. So those who have visited Kerala, you might be aware here, most of the buildings or the houses are covered with trees. So in an optical image, these buildings will not be visible at all, but that is not the case as in LiDAR. We can see the buildings. So this is actually a LiDAR data point of Trivandrum, and this is when we try to label with it. So actual problem comes when the vegetation are very, very close to the buildings, or it is like completely overshadowing the buildings. So how best can I classify in that aspect? So once that labeling is done, okay, the next step would be to create a proper model. So this, just to give an example, this we have done it for our own campus, in which we had used a TLS or a terrestrial laser scanner to go around and capture the entire city. So entire campus. So you can see when we had done, so this is like very, very fast. So each scan is going to just take me like 8 minutes or so, but I can capture the entire, I can capture this entire campus in about like maybe 2 to 3 hours. And after that, again, I have to apply some classification. So like even this car, buildings, vegetation, etc. I have to classify. So once I have that, I can use it to generate a map like this, a 2D map like this, and I can generate something called as a DEM, which is a digital elevation model, which is very, very important when I am which is very important for construction or maintenance or whatever. This is a very important data, and this is as precise as the ground data. This is the best accuracy that you can create a DEM with. And after that, we used it to create a 3D model. So once this kind of 3D model is done, as I told, these 3D models are good for visualization, but I needed to use it, like a decision maker would require to use it beyond visualization. So how many floors are there in the building? If I have to answer such a question, or like what is the solar potential of the building based on the geometry of the roof? How much area would be cast under the shadow of the building? So if I have to answer such a question, then I have to move beyond that just 3D visualization. So that is when we have the semantic model, which is very different from the pure geometric model that we have seen so far. So that is when this concept of city GML or city JSON, which is coming in. So this is basically OGC. OGC is Open Geospatial Consortium based format for storing the data such that many semantic information can be integrated within the 3D model. So once I have such a data, so once I have a 3D data like this, I can use it for different applications. So once I have a 3D city model of the city of an area, I can use it for urban planning or disaster management or training simulation. I can use it for multiple applications. So this is just an illustration on what are the applications that it can be used. So in that context, recently, as I told, we captured this data of Trivandrum, and simultaneously we did some field survey also because we wanted to use it for vegetation and other field stuff. And once we have that, this is a pilot study that we have done it for Trivandrum. We wanted to demonstrate how this building models in the city GML format can be used for some flood modeling simulation. So suppose if a flood occurs, if you remember the first example that I talked with, like which floor, which buildings would be getting affected. So we are doing it like in a broad kind of basis for the city corporation, in which like if suppose in the case of a disaster, if the city has to deploy manpower to go and rescue, which ward should it concentrate on? And even within the ward, where it should go, which building is going to get completely inundated first. So I should deploy my men there. So these kind of city, this kind of city querying can be possible. So I have to, my model should be able to do this kind of query. Like select the building has high rise within a region X. So it is basically, I'm going to integrate my GIS based querying on my point cloud as such. So this is just a video on what we had done so far. This is a pilot study. So there is 2 rivers flowing in middle of our city, Karamana and Pili river. So what we are trying to do is, if suppose there are like flood, this much of water flow which is there, and highlighting the different wards, we can basically tell okay where the flood, where the rescue team should go. So this is a crucial information. So it's not only a 3D model, but it is a 3D model used for decision making. So this querying is very important in that aspect. So this is one aspect. The next aspect would be, now how can I integrate this 3D with the AR and VR, which is basically the new kind of technologies that's rapidly coming out. This is again another research direction which is picking up as far as LiDAR data is concerned. So here, even the research that's going on at IIST, we are trying to kind of combine the LiDAR with the HoloLens and these kind of wearable devices so that we can better interact with the data. So here in this aspect, the buildings itself, we can categorize into different level based upon the how much detail we can capture. So like for example, the aerial data from the aircraft or from a drone, we'll not be able to capture inside the building, but this building information modeling is again another aspect. If I have to which is coming up, if I have to scan the entire building and if I have to navigate through the entire building. So in this aspect, we have scanned the entire library. This is again a pilot project in which the entire building, one of the complex building at our campus, the library building, we try to capture. So here, once I have this digital data, I can do n number of, my application or like how I can use this data, the opportunity is endless. So this is something. So this is our building. You can see the different levels, etc., which has been captured. So another important area similar to this building is this heritage mapping, in which again LiDAR is playing a very crucial and critical role. So basically preserving the architectural marvels of our country is very, very important. So each of the each of our state has its own architectural impact, and so this is actually our Kerala's traditional architecture. This is one of the palace which is near to our campus, and we try to create a 3D model of the campus. So this is the LiDAR. This is basically the tripod mounted LiDAR, and we try to capture this entire campus. So once this is kind of like a digital documentation or a digital archive. So once this is done, I can integrate it now with my AR VR kit, and I can use it as a virtual tourism destination. So that is the work that is going on. So now that the data is captured, it's all digital. Now can I like integrate it with my VR setup so that people like sitting at their own home can like navigate, or like it's kind of on the direction of virtual tourism. So the data and the video for this is available in YouTube. Those are interested can check it out. So this is a very, this was given to the Directorate of Archaeology, Government of Kerala, so that they can have a digital copy of the thing. So the next aspect as far as the urban is concerned is autonomous navigation. So I'm sure most of you are familiar with this ADAS concept, self-driving vehicles. So here the eyes are LiDAR. One of the major sensors that is there is the LiDAR. So this is going to, so for autonomous navigation, etc., we should know like the obstacles coming, etc. So that can be done with this LiDAR. So this is mobile LiDAR scanning. So in the car, we fit in the laser scanner and we drive. So if you compare this MLS and ALS, here, as far as LiDAR is concerned, similar to the resolution that you are aware of in the images, we talk about the point density, how dense the points are. So if I'm looking at a mobile laser scanner, you can see it is like very, very dense compared to a ALS scanner, which makes the processing even more complex. So for doing all this processing, we require a high-end machine for doing all these processing. Research in the area of GPU based processing, etc., is again another parallel processing again are all some of the research areas. Another thing is mapping the power line. So first initially I mentioned that building detection from LiDAR data has been like more or less matured. But the problem is when you are talking about other objects like, car or, power lines, these are some of the things that still possesses a challenge. So buildings within the vegetation, as far as Indian context is concerned, is also something that needs to be looked at. So that is just because of the lack of the data that is available and open to the researchers. These are all some of the hindrances as far as the Indian terrain is concerned. So one of the other application in which I can use this LiDAR is creating the DEM or the elevation model. So DEM is one of the important concepts as far as the geospatial data science is concerned. So we need to get very, very precisely, as precise as I can get the terrain changes. So if you look at this optical image, you can see this is all trees. I cannot see what is beyond the trees. But because of how the laser scanning works, the thing is like it can penetrate through the vegetation. So because of this concept, there are many processing algorithms which I can adapt, in which I can, I can take out all the trees and I can get only the ground points. Okay, so this technique we call in LiDAR data processing is filtering. So with this, I can create a digital elevation model which is very, very precise. Okay, so this ends. So I have kind of told about the different applications as far as urban is concerned. So this DEM as again for road laying, for all these aspects, DEM is very important. Like even now, all the national project which involves like highway, etc., they are capturing this LiDAR data for getting the DEM for the civil engineers needed for proper laying of the roads, etc. So all this is concerned with the urban. So the next thing is the mining. So mining also, so this is again from the aerial data that we have captured, in which one of the mine sites is included. So here the excavation from the mine can be clearly seen from the LiDAR data, which is not possible with the optical image, unless I use some photogrammetric technique. But again, I need a very, very precise optical image, which again has its own challenging problems. But the precision, and this is actually the true 3D. That is actually a 2.5D data, that what you get from the optical image. So once I have this, I can use it for kind of getting the this cut fill kind of a thing that you usually work in GIS. So the next broad area that we are going to discuss is the agriculture and forestry. So this is again another domain in which very important domain as far as geospatial data science is concerned, like how best or which technique can be used for managing this agriculture and forestry. And here LiDAR plays a very important role. So what can I get from LiDAR which I cannot get from the other geospatial technology? So mainly the information on the crop structural and the geometrical characteristics like height, width, volume, leaf area, all this like height, width and volume, for example. I cannot get it from the other geospatial technology directly. Okay. So this can be obtained from the LiDAR, and because of these information, I can use it for numerous applications. Because of this geometrical characteristics of the plant, I can use it for many applications, and thereby I can reduce the economic and the environmental impact. So the main thing is it can produce non-destructive, rapid and accurate and repeatable way of mapping a plantation or a forest. So this is very important, this non-destructive. So if you, I have some slides later, but if you know, like if I have to link it to climate change, if as a forester, I wanted to find out the biomass of a vegetation, then The way it is usually done using some destructive method is like I cut down the tree at different samples and then I compute the biomass by burning, etc. But which is not usually advised and which is not allowed. And allometric equations are developed based on the destructive method which people use across the globe to estimate the biomass. So LiDAR offers a non-destructive way of rapidly and accurately and mapping these kinds of things. So TLS, the terrestrial, has lots of potential in this direction. And another thing is, so if suppose I have to map or monitor the crop at a regular basis, now how these agriculturists do or like researchers do is they go and they take a, with some instrument, they'll make some measurement of the tree height or the crop height, the crop width, etc. Instead, if I have a TLS scanner, I can just go with that instrument. I can just take a scan and I can kind of use it for doing all these measurement automatically. So this is actually going to complement the manual method, and we are moving towards a direction in which all this can be automated. It can be made automated, and it can completely replace the manual method. So these are some of the data that we have worked with, captured for using or utilizing the LiDAR for studying different crops and understanding its biomass, this structural variation, etc. So in one of the studies, this was an experimental plot in Bangalore in which we had, this is a collaborative experiment in which we had sown different crops and we were trying to find out the impact of nitrogen on the crop growth. So this is a planned experiment and we were trying to compare it with the satellite image as well and some drone images as well. So here the challenge was like we had taken so many raw individual scans and we had to register it, etc. But the whole idea is, so this data was taken at a temporal basis, in the sense every 15 days we were capturing the whole thing, and we were able to kind of get the canopy height model, or in the sense at each day how much is the crop growth, how much is the crop width. Like we are talking about agricultural crops here, so this is actually a cabbage, and then you can see I'm sure that you are able to see the structure of the crop, the cabbage, and we had brinjal and tomato as well. This is just an experimental basis on how best LiDAR can be used. So another aspect is this precision farming. So this is basically in precision farming, as many of you might be aware of. It's like, applying pesticide or fertilizer at the targeted location. So if suppose I have an instrument like this, this is not from our study. So here in this study, what they have done is, in a tractor, they have a LiDAR sensor and some other sensor. So this moves through the in a field, and based upon the height, they are able to discriminate the weeds which is present between the maize plants and apply the pesticide only on the weeds. So this was an interesting experiment on how LiDAR can be used for precision farming. So this is with respect to the agricultural crops. This next thing is the trees. So as far as trees is concerned, we have to find out the tree volume, the leaf area index, the crop leaf density. All these are very important. So this is again in one of our studies. So this is over a park in Netherlands. We use our algorithms to detect each and every tree. And we have classified the tree based on elevation. So where does it apply? So urban green space mapping is again one more technique or one more area which is growing very popularly. So if suppose as a smart city or something, if the government is planning to develop a city, greenery is very important. So where should they have that greenery, or how should they manage the greenery? So where are the trees which are like very tall, which is very broad? So they should not be cutting down the trees, because as you know, more bigger the tree, you have lots of carbon storage. So it can be related to climate change as well. So in all these urban green space mapping as well, this LiDAR plays a very crucial role. So this is what I've been telling about the conventional method of estimating biomass in a deep forest is using some manual methods and some destructive methods, which is very time consuming, labor consuming, and sometimes not. If it is like burning down the trees, it's not so much recommended. So in that aspect, LiDAR plays a very useful. So you can see here, I can measure the DBH of the tree. I can measure the height. I can measure DBH is a diameter rest height, which is one of the important aspect that people use to relate it to climate and the biomass. So from a single tree, I can get all these measures, which I can use it to use it for different applications. So tree species is again, so you might be knowing that using hyperspectral, we can do this tree species, but even with the geometry or how the structure of the tree is, I can identify what sort of tree it is. So canopy height model, as I told, it's a very important aspect, which is difficult doing with other remote sensing approaches. Then biomass estimation. So in the biomass estimation, which I can relate it to climate, DBH and the height are the important aspects which I can find out using LiDAR. So as we have seen for forest studies or anything, LiDAR as such, it gives only the geometrical information. It doesn't give any spectral information. So we cannot undervalue the, we have to actually utilize the power of hyperspectral, which has a rich spectral information. So the trend is, or like the way forward is to fuse both, which is a laser, it lacks spectral discrimination capability, and hyperspectral, which lacks structural capability. So the way forward is to fuse both the technology or integrate both the techniques. So this is again one of the work in which we have done, in which we have used LiDAR and the hyperspectral for some classification within the category. This is again another prototype that is getting developed, in which there is a development of hyperspectral LiDAR scanner. So I hope many of you might be knowing about this NDVI, chlorophyll absorption ratios, which are like very important ratio as far as plants health is concerned. So now this scanner is able to kind of scan this whole plant, and within the plant they say that there is variation in the water or water index, the chlorophyll index, etc. So this is again as far as precision agriculture is concerned. This is a prototype which is being developed by the group in Finland, and I'm sure like maybe another couple of years this might come into the market. So now the next thing is global environmental. So as far as satellite is concerned, this is a very recent satellite, maybe 2020 launch satellite, which is there in our ISS, International Space Station. So the JEDI, the main aim is to map globally the forest with using the laser scanner. So JEDI experiment is an experimental satellite, but it is working in a very good way for mapping the forest canopy. So the challenges, so this is basically the applications. We have covered different applications. So to summarize, the LiDAR data is very big. So volumetric, so you can call it as the big data. So it is computationally very demanding. We need GPU based algorithm, very good processing, etc. we need a good visualization, and to extract information from the data is one of the big challenges. So again, integrating with other remote sensing technologies, again, one of the challenges, and we require some in-depth understanding of the point cloud and to handle this data compared to the normal remote sensing data, in which we have lots of softwares available for processing. As far as LiDAR is concerned, there are not many softwares available. So yeah, these are some of the challenges. And I have just listed out some of the open research areas as far as point cloud processing is concerned, which is related to GeoAI and stuff. So here we are using many machine learning, computer vision, and AI kind of technologies for doing all this point cloud registration, labeling, reconstruction, temporal data classification, integration. So all these are some of the open research challenges as far as point cloud processing is concerned. So if you are interested in this LiDAR point cloud, getting some Indian data might be a challenge, but yeah, so we have some random LiDAR data set basically based on some collaborative thing. We may be able to share some of the portions. But otherwise, some open LiDAR data set which is available for researchers to start with. There are like many open LiDAR data set which is available for download. I have just listed out ISPRS, DALES is now one of the popular data set, the NEON, Open Topography, iCumulus, all these are some of the data set. And the satellite mission, ISAT and JD are the two satellite missions in which LiDAR sensors is available, and both data are available to download at any part of the country or anywhere in the world. So internationally, many countries have opened their LiDAR data set and it is available for anyone to download and use. So in this aspect, like if somebody is interested in just developing the algorithm, so from looking at the perspective of developing algorithm, these data set is good enough. So there are you can go with any of these data sets. And for ADAS kind of application in which we operate with mobile laser scanner. So as I told, the type of data and the because of the point density, this mobile data set is quite different from ALS, and the data processing again, it is quite different from how you deal with the ALS data. So if you are interested in mobile or ADAS kind of application, again, there are many benchmark data sets available with which you can start your work on. And there are open source tools and libraries available for LiDAR data processing. GlassTools is one of the popular ones. And then you have many point cloud libraries, C++ library, PDAL, it supports Python and C++. And there are some visualizer as well, which you can use. And another interesting project that you might be aware of, or it is underway, is like to develop an intricate and detailed map of the Earth's topography. So this is a effort which is going on from the Colorado State University, in which they are trying to cover the entire globe, capture it by LiDAR. So this is it from my presentation. So thank you. If you have any questions or any comments,
yeah. So thank you very much for the detailed presentation. Actually, it was
I'm not able to hear. Sorry.
Could you hear me? Hello.
Yeah. Now
Yeah.
it's
Thank you for that detailed presentation. It was very elaborative. So I have seen like plenty of open challenges and problems available. Even we can post this itself as a separate workshop where we can discuss. Probably we planned a visit to IST last week, but due to some COVID situations there, we postponed. So once we come there, we'll discuss in detail, and probably we can host another workshop in this line, especially in IST. So that we'll discuss.
okay, sir. Sure.
So also like we'll request some of the challenges which we can address together. I mean, like with IIT NIF funding, etc. We'll discuss.
Yeah, yeah, so that would be great. Yes.
Yeah, yeah. So, participants, any questions?
Hello.
Yes, Divyesh.
Yes, ma'am, I'm Divyesh. I'm a GIS engineer at National Forensic Sciences University. I worked on LiDAR images, basically handled LiDAR mapping. I have used from Leica Geosystem. So, like, I have faced the many challenges in this LiDAR acquisition, scanning, and processing. So, like, one of the major challenge, like you have mentioned, that like the connectivity of point cloud in a structured way. So, ma'am, is there any automation on that side, like we can structure and linearly structure or creating a mesh model in a manner that like we can create a accurate mesh model of a complex object, like the complex object in terms of it has a curves, different complex arches, different geometries. So, like in that context, we can automate this mesh modeling.
So yeah, so for data structuring, there are the most popular structuring algorithm that's been used is this octree and KD tree algorithms. So these they are available. So if you are familiar with the SPEEDA library, which you
Okay.
can work on in Python,
Okay.
so there these options are available. Maybe you can try that out. So
Okay, ma'am. Okay. And ma'am, you have mentioned the accuracy of LiDAR point cloud. So, like I want to know, like, from like MM level accuracy, is there a point cloud accuracy or panoramic image accuracy?
no. This is all point cloud from the LiDAR data. So as far as the LiDAR data is concerned, I mean, if you are talking about a point cloud generated from an image,
Okay.
the accuracy is different compared to a point cloud generated from a LiDAR point cloud. So those two are two different techniques. So today, whatever we have concentrated is on the point cloud seen from a LiDAR sensor.
Yes,
So
yes.
here the vertical accuracy is very, very high. Very high in the sense I can get it like in the orders of centimeter, 5 centimeter or 10 centimeter or even lesser than that.
But ma'am, currently I working with the armed forces, like with the Indian Air Force. So in which I have faced the difficulties in horizontal accuracy. Like I got the accuracy around the 10 centimeter, 15 centimeter. So like
10
how can
centimeter or
so ma'am, like they are wanting to at MM level because they have a complex objects and complex structures. So they want the MM level accuracy. So how we will get the MM level accuracy in that case?
okay, so it depends. So are you using a TLS or a drone based or
No, ma'am.
ALS?
We are using the handled LiDAR scanner and a terrestrial LiDAR scanner.
Okay, so TLS, there are options in which you can set your level of accuracy. For example, if you are using this Faro sensor, you would be getting in millimeter level accuracy.
Okay, ma'am.
So yeah, it depends on the sensor. Usually when you buy a sensor, there are like certain specification that comes on with it, in which they report the accuracy. So you can have a look at that on what kind of sensor you're using. So
Ma'am, we have used the Faro scanner and Block to Go, like from Leica Geosystem. We used both the scanner, but like
okay.
we'll get the different accuracy from the TLS and handled LiDAR system. So like is there a point cloud density affects a lot in vertical and horizontal positioning of point cloud?
As far as the LiDAR is concerned, this vertical accuracy is very, very high. Okay, be it a ALS or a TLS or a MLS. So horizontal accuracy, see, you need a very good DGPS also. That is again one more thing that I mentioned. So it is going to depend upon your DGPS. So if you have to like overlay it on your Google Earth, and then if you want to like do further, then you should have a very good DGPS system as well, in which this positioning can be done. So your accuracy is going to be a function of all this.
Okay, okay. And ma'am, one more question regarding the CTGML modeling. Like I have worked on the CTGML on my master's level thesis. and like I worked on the slum portions of the like developing the 3D model of the slum using the CityGML semantic techniques. So like ma'am, I have one question regarding the LiDAR 3D data regarding like the orientation and complexity of the object. Like we'll get the orientation and different level of objects from the LiDAR point cloud, but like we will when converting the CityGML format, like it has a many issues in CityGML while converting. So like ma'am, can you suggest the I like in my thesis as well, I have faced many issues. So can we get the smoother processing from converting one format to another in a easy manner?
One format to another in the sense
Like
CityGML to
.ls
CityGML.
.ls to .ctgml. Like I want to convert. So like ma'am, which are the best tools like in the world to use?
So CityGML, there are like lots of converters available. If you look, or if you want to write your own codes, this OGC provides you a very detailed description on how CityGML format is based on. So dot last to CityGML. I mean, unless you have a classified data set, and if you are going to like differentiate different object, and then after that, if you convert it to CityGML, you will get a better result than directly going with that.
Okay, okay, ma'am. Right. And ma'am, one more question. Like, once I acquired all the lidar data, and like I want to differentiate into the different classes or features like buildings, roads, power line you have mentioned. So, like, ma'am, can we use the GeoAI tools, and which are the best GeoAI tools available in the market till date?
Last tools is one of the best, and another thing is now this QGIS of LiDAR toolbox, open toolbox, so that again works well. Apart from TerraSolid, so TerraSolid is a paid one. I'm talking about the open ones, last
Yes,
tools,
yes.
and so TerraSolid commercially that works well.
Okay, okay, ma'am. Thank you very much.
Okay, thank you.
Any other question?
Any other questions?
Okay. I don't think no other questions for that. Yeah, I thank you once again for giving this elaborative discussion. So we'll discuss about the other possibilities. Okay, thank you.
Thank you. Thank you very much.
So the next session is that it is from a foreign speaker. So we got to adjust according to their time. So 6 o'clock it will start. We'll have a break for another 2 hours, 20 minutes. So we'll meet after at 6 o'clock. So we can join around 5:55. Thank you all. I will end the session so you can join back at The speaker is yet to join. I'm still waiting for him. Once he joins, I will just update. Hello, Professor Anand. Hello. Yeah. Professor, would you hear us? You are on mute. You are on mute.
Okay, can you hear me on fine?
Yeah.
Okay, wonderful.
Yeah. So I think we can start the session. So some of the people will join, and some of them are watching on YouTube. So we'll start it.
Sure.
So thanks, Professor, for joining with us. So dear participants, good evening to everyone. So here with us, Professor Anand Padmanabhan is here. He is going to talk about democratizing access to geospatial data science tools in the era of CyberGIS. So Professor Anand Padmanabhan is from US. He is a research associate professor at the Department of Geography and Geography Information Science at the University of Illinois Urbana-Champaign. He did his PhD in computer science from the University of Iowa, and his research interest includes something like cyber infrastructure and cyber GIS, geospatial data science, data, etc. He is also the managing director of National Science Foundation, the Harnessing Data Evolution Institute for Geospatial Understanding through Integrative Discovery Environment. So he has worked with large national cyber project, cyber infrastructure projects like Open Science Grid and NSF's Extreme Science Engineering Discovery Environment, etc. And also he has published so many papers, especially in the area of distributed and advanced cyber infrastructure, cloud computation, etc. So without further delay, I'll just hand over the sessions to Professor Anand.
Thank you, Dr. Maniappan, for your kind introduction. I'll be happy to share my thoughts on how our research is kind of trying to progress access to geospatial data science tools and services in the era of cyber GIS, and how we are democratizing it. As Professor Maniappan said, that's kind of the topic of my introduction. So I'd like to share my screen if that's okay.
Yeah, please go ahead.
Okay, let's see. Okay, can you see my screen, I guess?
Yes, sir.
Okay, go ahead. I'll get this out of the way. Okay, good. So again, good evening to everyone in India. As Professor Maniappan said, I'm in the US currently with the University of Illinois Urbana-Champaign. My name is Anand Padmanabhan, and I'm with the Department of Geography and Geographic Information Sciences here at the University of Illinois. And I'm a research associate professor here. So as was introduced, I guess my talk is going to focus on democratizing access to geospatial data tools in the era of cyber GIS. So I'll define certain key terms here. What is cyber GIS? What do I mean by the era of cyber GIS? And then I'll talk about some of the tools that we have for democratizing access. At any point, feel free to interrupt me. If you have any questions, raise your hands, or I guess put things in the chat. I'll be trying to watch that. And please feel free to interrupt me. Okay, so I'll start off with the basic. I guess this probably people on the call already know. What is the definition of GIS? GIS is basically geographic information systems or sciences, you can say. There are two kind of definition there based on like geographic data based on kind of computer-based systems. How do you capture, model, retrieve, share, analyze, manipulate all this data? And the science behind it is kind of called the geographic information science. When we say GIS, people sometimes refer to geographic information systems like the tools, and then the science behind it, which is kind of the which is driving this GIS tools. What is cyber infrastructure? Cyber infrastructure essentially you can think about as a plumbing system for the modern economy or the modern like knowledge economy. So that's this was the definition by Dr. Atkins in 2003, which basically introduced this term called cyber infrastructure, which is very commonly used in the United States, but in Europe, maybe they use term e-signs or things like that. So it's essentially a similar concept, basically the infrastructure behind the knowledge economy. This includes tools, peoples, platforms, services, everything, which form this fabric. And so what is CyberGIS? So CyberGIS is essentially what we are doing is to combine these two things, the geographic information sciences system, but that is based on advanced computing and cyber infrastructure. That's what we define what CyberGIS is. So, and then I said I will define what is the era of CyberGIS, when what I mean by era of CyberGIS. This is kind of the context which I was thinking about when I say era of CyberGIS. So CyberGIS doesn't mean just, hey, we have, when I say what is geographic information science and system based on cyber infrastructure, it's kind of, it's maybe not as clear. So this context makes it a little bit more clear. So you have computation and data intensive analysis and applications and sciences on the top. This could be from various fields like earth and environment, food, energy security, sustainability, emergency management, all those kinds of things. This is kind of from an application point of view, which deal with geographic data, but these can be very highly intensive, computationally and data intensive. Now, of course, there is a data science, geospatial data science tool. This, I guess this workshop is focused on geospatial data science. So all of you might know already what that means. But essentially, you can think about it as like extending data science, which is kind of very popular to geographic data and geographic information. So spatial computational theories, methods associated with it, tools associated with it. Then we have a layer called CyberGIS and CyberGIS middleware, which you can think about as the science and technologies of how to combine these things which are on top, meaning the data intensive applications and science, and the geospatial data science concept with the bottom layer of the advanced computing and cyber infrastructure, where we have many of these resources like extreme scale computing or NSFXC. This is a little bit more from the US context, but there are others, I'm sure in India as well, where you have access to higher end computing environments. So that's what I mean by era of CyberGIS, and I'll go into each of these in a little bit more detail shortly. So what do we, again, this is kind of another expanding on the era of CyberGIS, kind of the, what do we have in terms of the ecosystem? So looking at it more on a systematic, like a architectural kind of perspective, computing architecture kind of perspective, we have this domain science applications from various areas. We have cross-cutting tools and services capabilities, CyberGIS capabilities and services, which we can think of our geospatial data transformation, software integration and interoperability, collaboration and problem solving, CyberGIS. So all these kinds of various tools which are there in order for you to make use of the computational infrastructure, the cyber infrastructure behind it, which can be the data infrastructure, the cloud infrastructure, and all those kinds of high performance computing infrastructure. Okay. So essentially, again, what is the era of CyberGIS? Big data, big compute, big collaboration for big problem solving. So that's what we will define as CyberGIS and the era of CyberGIS. Okay. So looking at it a little bit more deeply, I'm going to take some examples when I said these 4 layers. The first layer I mentioned was the computational and data intensive application and sciences. So in our team, we have done over the past, I guess, number of years or maybe even decade at this point, a number of applications that we have supported. For example, this was a project we did like maybe now 5 to 7 years ago, where we had like a flu mapper where we took data from Twitter, like streaming data from Twitter, and in real time tried to plot what is kind of the risk level associated with flu. And we had a similar one which we did for COVID mapping. I guess that was done more recently. And here we were also looking at travel trajectories of how people move and how that could impact the spread of the virus. Another example, this is more from a hydrology and hydrographic information science kind of thing. So this was one of the first thing which we were able to do is on a national scale, a flood inundation map on the US at a continental scale. Before this, it was not done before. So we were able to calculate something called the height above the nearest drainage, which basically means like what is the level of risk you have for flooding, like say when you have 3-foot inundation or 5 feet inundation, whatever. So you could define like how much inundation might happen, for example, if there is an extreme rainfall event or if there is a collapse of a dam or something. So that triggers a downstream event, and how does that would spread over the over any particular area. So this was kind of a base calculation which was now done at a national scale using high performance computing tools that we had, using like catchments and flow lines and digital elevation data and calculating this thing. This on the supercomputing, this took us like around 2 weeks of calculations. But before that, it was not done on this scale. So that is kind of the application. The other thing we did, like again, was something like urban flow, where we were mapping urban dynamics and population of urban movement, like using sensors as well as land use changes, Twitter data, other social media data as well. So this was another application that we looked at, and this was quite an interesting thing. This is not mapping anything. Actually, this was just mapping like using Twitter data. We just got the volume of Twitter data, and we were mapping them, and you could actually see the physical infrastructure of the urban area almost showing up here on this side here on the top. You could see the structure of the O'Hare Airport in Chicago, just based on the tweets that we were collecting without like even the base information. And here you could almost see the Chicago kind of population distribution, where you can see the downtown area and the airport area in the top. So you could see the whole thing based on mapping Twitter data information. So this is some of the applications that we have looked at. Of course, there were lots and lots more applications that we have looked at. This is just a small sample of things. Now I'll go into the second aspect, which is the geospatial data science. And when we say spatial or special, what exactly do we mean for geospatial data science? So where we see the geospatial data science and cyber GIS fitting in. So this is the traditional geospatial science technologies and services. We have the statistical tools and sciences and mathematicals, and you have the cyber infrastructure. So we see this as an intersection of all these 3 things, of the geospatial sciences and technologies, the statistics, as well as the computation. And when we say we are looking at this at a large level and at scale, this is what we mean. So we have spatial data, which is highly distributed, highly dependent. So this is why spatial is special, right? So it's not like any normal kind of big data set. It has certain dependence. You have spatial correlations and things like that. So the normal statistical properties where you say, hey, you can treat everything as independent, is not really true. So you have to consider those kinds of dependence in the data set, the distribution, the spatial distribution of the data set, the integration of these data set, the uncertainty associated with these data sets, the complexities, I guess, of these data sets. So from the computational point of view, So spatial, the traditional computer science complexity was as the intensity in terms of the calculations of these things, reproducibility, validity, etc., and those kinds of things. So we had an NSF DIPS project. This was this ended like 3-4 years ago, where we looked at all these aspects and created tools at scale. The other more recent things this has been happening, which we are looking at in terms of these supporting geospatial data science, is something called CyberGIS X. And I'll go into this a little bit in detail a little bit later in my talk, but just wanted to introduce this concept of, like, we have these tools which we are developing using Jupyter and the other environments like Jupyter notebooks and the geospatial libraries, where we are making this accessible to the broad community. So data science tools enhanced kind of with the geospatial flavor. So this is kind of the example that we look at called CyberGIS Lib, where we are taking many of the libraries, geospatial libraries, packaging it, making it all available together along with our libraries in order to, so that you could do geospatial data analytics. So some of these tools are available for free for everyone to use here. Okay, so the next part is CyberGIS middleware. This is a little bit more about accessing, democratizing access. And this is kind of the third portion of our bubble. So we have, you can think about it as the geospatial discovery and innovation environment, where we have this Jupyter environments, or we have a gateway environment where you have people who are not very knowledgeable about cyber infrastructure. And if you give them a supercomputer and say, hey, just go and figure it out, you give them a shell where you need to log in, you need to figure out the libraries, you need to figure out what packages to install and write code, parallel codes. Many people will just walk away and saying, hey, this is too difficult for me, we cannot do it. So what we are trying to do is kind of bridging this gap with our middleware and tools that we develop in order to access these high-end resources, like the virtual Roger that we have at Illinois, as well as the national Exceed, or newly it's going to transition to something called Access, which is kind of the national infrastructure within the US for cyber infrastructure. This is an example of kind of the details of the middleware that we created, and then we have a newer version of this from the geospatial middleware, which I will talk about a little bit more detail later in the talk. So this is kind of the initial architecture that we came up with in order to access this high performance computing, high throughput, and cloud computing through a gateway, kind of a portal interface through open APIs and services. And recently we have transitioned to something called CyberGIS Compute, where essentially it is taking this concept, but it is going into more of a standalone kind of service where you could talk to it from different clients, from different Jupyter environments, where and then you can do contribution. So we have the core, we have the contribution SDK as well, the SDK as well as the contribution mechanism, where you could contribute your code to run within these kind of high-end computing environments. So that is kind of the third piece. So we have covered, I guess, when I said the era of CyberGIS, we looked at some of the applications, we looked at what is geospatial data science, we looked at the CyberGIS kind of middleware, and now we're just looking at the infrastructure, the computing infrastructure, the advanced computing and cyber infrastructure that are available here. So one of the projects we had is establishing one of the first, this was an NSF project to establish one of the first supercomputers, which is tailored for geospatial data and geospatial sciences. Now, I guess these days it is very common to see supercomputers which have like traditional HPC as well as cloud kind of an environment, at least within the Exceed and the national infrastructure point of view. But when we started this project, there were usually when you said, hey, it has to be it's a high-end computing environment, it's usually meant it's a HPC, high performance computing environment, where you just submit job to a batch system and you wait. So this kind of we revolutionized it in such a way. So when we developed Roger was we came up with an architecture where we could do high performance computing along with like cloud computing, all backed up with high like disk space and all those kinds of things on top of geospatial software and CyberGIS software. So with this, what happened was we had a new modality kind of computing for HPC, data intensive science, as well as cloud, which was all kind of aimed to geospatial data. So this project ended actually with this kind of supercomputer, which was highly successful, and then we transitioned it into something which is more sustainable, and it is available within Illinois with all the CyberGIS stacks, which is now called Virtual Roger, and it's still operational. Yeah, so this Roger, as I said, was big data, HPC, cloud. And when we started it, it was kind of a new thing. Even when we worked with this National Supercomputing Center, which is here at Illinois, and at that time they had not done things like this before. So we challenged them to do this, and we set up this environment. And now it's become more common to have this kind of an integrated platform for doing science, essentially. So with all this, what do we have in the era of CyberGIS? We have a very grand opportunity to revolutionize discovery and innovation across multiple fields through synergistically advancing high-performance computing, geospatial computing, data science, software, and advanced cyber infrastructure. So that's kind of, we have this whole system. I guess we can think about the 4 layers which I talked about, the application, the data science, the CyberGIS middleware, as well as the advanced computing. So we have an opportunity to advance all of these together, and that's what we have been pursuing here at Illinois through our research. But there is a major challenge. Even though we have been successful in doing this, there is still a gap that only these tools are still available to a small set of people in terms of who have access to these resources. So one of the major challenges that we are addressing is how to democratize access to geospatial data science tools and capabilities so that we can catalyze a broad revolutionary change in discovery and innovation across geospatial context. So I'll present some of the tools, but before I do that, any questions or any things at this point? So this is kind of a transition point where I was introducing the era of CyberGIS at this point, but I'm going to transition out to talk about our tools and solutions that we have developed.
Any questions from participants? Okay. I don't have questions. You can go.
Okay. I'll move ahead, but again, feel free to interrupt anytime you feel. So we defined what is CyberGIS, what I mean by era of CyberGIS, and what are the things that we have developed to make this era of CyberGIS, and we have talked about the opportunity and the challenge. The challenge is democratizing access. So I'll talk about 2 tools here that we have developed in order to help us make progress towards democratizing access. The first thing is called CyberGIS X, and it is essentially an open platform for enabling this democratizing access for cutting edge geospatial or CyberGIS capabilities to enable advanced and computationally and data intensive geospatial analytics. Basically, what that means is you have a platform where you have many of the CyberGIS and geospatial software installed, and you can run your computation there. So this is kind of the first leg in accessing is to make it easy to use. So for this, we are using something called Jupyter Notebook. I hope many of you might be aware of Jupyter Notebooks. If not, it is essential. I'll give you a very short introduction here. You can think about it as it's an open source environment where you can do programming in a browser. You can write live codes. You can just run certain cells. You see visualization. You can write explanatory text. So essentially, it's kind of analogy to a notebook where people in the past used to take field notes, and they had notebooks where they used to record, jot down their experiments, and they took tedious notes on what they observed and what they did. So essentially, this is kind of a modern era equivalent. So you could essentially put what you did, your metadata, and things like that associated with it, as well as codes, which is kind of one of the important things in modern research, right? So your research is based on computational code. So you can put your codes and you can run the codes, and someone else can reproduce and rerun your code and get back your results. So that's kind of helping like reproducibility in modern era and modern sciences. But we want to go beyond Jupyter notebooks, right? So Jupyter notebooks is something, yeah, people can download and install, but it's not geospatially oriented. It's kind of, it gives you a vanilla environment with maybe generic Python or R kind of tools that are available. But if you want to do geospatial analytics, you have to install these modules, you have to install the libraries associated with geospatial packages, and that can be a barrier, a high barrier for many people. Also, we need to access powerful resources. This is kind of the second part I'll address on one of the other tools that we are developing. And of course, we want to make this easy to discover and share these notebooks and reproduce, easily reproduce things that you have been doing. Okay, so bottom line, essentially, keeping the bar low for entry users, for new users, and making it easy for advanced users to access advanced resources. So we had the 4 components, which currently, I guess, CyberGIS comprises of. You can think about a hub where we can say it's a discovery and sharing environment. You can go to the link that I had earlier. I'll show that again. cybergishub.cg.illinois.edu. If you go there, you can see this environment. It's a live environment where you can access it and you can register for it. If you have, we have integrated something called CI logon, which is meaning like many of the institutions, definitely in US and even across the globe, are integrated to it. So you could, many of the academic credentials you could just use to log into this platform without having to create a new login. If the institution doesn't have, then of course you could use something like a Google login to do this, but of course that needs to be approved, manually approved, because we wanted to do some kind of a test there. But again, if you are institution, if you see your institutional login there, you can use it and you can register and log in. If not, you could request for access and say why you wanted to access this platform. Anyway, that's the hub. Then the hub, behind the hub, we have this Jupyter CyberGIS Jupyter environment for interactive computing. This again has all the libraries and geospatial tools installed, pre-built, pre-installed. Then we have something called CyberGIS Compute, where if you, of course, the resources within the Jupyter environment are limited. It's running in a cloud environment. But if you want to access like high-end computing, this is your bridge to access the high-end computing environment. And of course, we have some visualization for advanced geospatial visualization. We have a package which is included there. So I'll talk a little bit more about these 2 components, which is the Jupyter component as well as the compute. Little bit more detail. So hub, it's a one-stop shop, I guess, for accessing the platform, CyberGIS X platform. You can use your organization credential to log in. You can create notebook, you can share notebook, you can discover notebooks, you can reproduce work. The great and the most important thing about it is like once you have a notebook, you can save and publish it. Since all the packages are there locally and they are available within this server, so once you publish your notebook, you put it in GitHub and you share this kind of, and you share the metadata and the information there. Any of the users on CyberGIS X can discover and find the notebook, run the notebook in the same environment that you had. So which is kind of helps with reproducibility. And I will talk a little bit more about how we did that within the CyberGIS Jupyter. It has, as I said, it has a lot of packages that are available, geospatial packages, including our CyberGIS, as well as many of the popularly used packages like GDAL, NumPy, GeoPandas, and things like that. And this is a little bit more in terms of the architecture. What we are doing is we have you get your own, essentially a container on virtual Roger where you access these kinds of sets, and then we have an isolated environment, and we are able to support multiple users and are scalable, and if needed, actually we can scale across like the local as well as the national environments. The third component that we had is the CyberGS compute, which essentially allows you to talk to the high performance computing environment from the Jupyter notebook. And I'll go into it a little bit more detail, but essentially it provides you this terminal environment is just provide you access to computational resources, but with CyberGS compute, you are able to make it more accessible to everyone. You are able to have a little bit more general purpose, and you are able to the steep learning curve is not there. So that is what we kind of get with CyberGS compute. And of course, visualization, like it's we have really great tools to do visualization in terms of and visual analytics. You could do multiple mapping and plotting at the same time, dynamically configurable software modules for visualization and for high dimensional geospatial data. So this is these are tools that are available. If you go to CyberGSX, and you will find details of all these tools. And lastly, we also have, since I said the hub is a community platform, so we have community notebooks that are available where you can just go and find the notebooks which are there, and you can run these notebooks. So this is the whole infrastructure which we set up to, again, to go back to the goal of democratizing access. And one of the research challenges, the things that we addressed here, so it's so we are doing both research as well as this kind of service to the democratizing of the access. The research part is talking about computational reproducibility, right? So you have these codes in the notebooks which are which need to be findable, accessible, reusable, and all those good things, but also need to have the software and the computational environment. It's not, you might say, hey, I put my notebook on GitHub and people can find it, but running your notebooks, you can provide all the instructions you want, but they will, it will be difficult, one. And second, they might not get exactly the same version of things that you had. So those are the two major challenges. And what we did is to develop CyberGS Jupyter as a scalable environment for managing and configuring the software environments and associated libraries, Python kernels, which becomes Jupyter kernels, and also integrating the CyberGS compute to access the high performance computing or the advanced cyber infrastructure environment. So it's kind of a one-stop shop. The hub provides you a one-stop and one-click kind of way to access or to reproduce your notebooks using these CyberGS Jupyter and compute behind the scenes for making it happen technically. The important trade-off that we are, of course, addressing with computational reproducibility is providing a stable computing environment for people to do the research, but but also keeping it updated so that it doesn't get outdated, like, right? So you create a software, you create a system, and then all the versions of the software will be outdated like a year down the road. So how do you keep up the environment while also keeping up reproducibility? That is kind of the key reproducibility challenge. And the solution we came up with is something which used tools like LMOD, EasyBuild. So these are basically, you can think about these as software management systems that are traditionally used in high-end computing environments, and then we customized it for the Jupyter environment. So what you can think about is, like, we have some certain common software, like, let's say GCC, G++, all those kinds of things, with maybe GDAL, Proch for libsqlite, all those kinds of geospatial software which we build using EasyBuild. So we can have multiple versions of GDAL, multiple versions of these. And then we also have the Conda environment. And within the Conda environment, what we could do is say, hey, use these versions of the software that from the backend, as well as this particular Conda environment. And together that becomes a Jupyter kernel where your code is run. So Conda environment will be like this path, as well as like loading these meta modules into this kernel so that you could create a kernel on CyberGS Jupyter. What does that give you? Essentially, that gives you a way of having this environment encapsulated within that kernel. So we could version that kernel and say, hey, I'm developing on Python, like the Jupyter kernel that you have per version 1 or version 0.9 or version 0.8 or whatever version that we have. And then with that version, so next time you come back and you run your code or your notebook, you can use that same version of the kernel, and all the software and the environment will remain the same, which helps tremendously with reproducibility. And updating software also becomes easier. So now you could have, say, multiple versions of the same software, and they can be managed at the same time, and different users can use different versions of the software, which gives us a lot of flexibility with doing these things, as well as doing reproducibility. So that is kind of what we had in terms of the CyberGS X environment. The technologies behind it is we were using the batch system for doing the jobs. We have the Docker-based cloud infrastructure to manage these user containers, and we have synchronization of the data between the cloud as well as the traditional high-end computing environment through shared file systems and things like that, as well as data transfer systems like Globus if you want to go on remote HPCs. So we have a paper in a couple of years back where I'm describing all these in detail. So that was the first part of the democratizing access, the tool that we are developing in the CyberGS Jupyter, CyberGS X, and the CyberGS Jupyter to help reproducibility. The second thing about democratizing access that we have developed is democratizing access to HPC. So one was democratizing access to the cloud and the platform, the tools, easily making it easy to use, like say you can log in with a browser. Now, the second part is how do we make this high performance computing, this advanced cyber infrastructure that we have developed, accessible. So that what we have done is to develop something called CyberGS Compute, which bridges the gap between the Jupyter and the HPC environment. So you could run like small scale jobs within the Jupyter environment, but if you want to run like a huge analysis, the big data analysis, big geospatial data on using a large amount of computation, you will use something like a high performance computing environment and use CyberGS Compute to access this. Again, this is kind of the general structure. We had a paper last year in a workshop in Geospatial describing this. How do we do this in terms of CyberGS Jupyter to HPC through compute? So we have three main components. The core, which basically is our middleware server, which automates job submission to HPC, so you don't need to know the batch system. So in this case, many of the HPC uses something called Slurm batch system. Like you don't need to know the details of all these things. How to write a script for accessing those batch system. That's the core is taking care of that. From the user's point of view, you are given access to SDK, which provides an interactive client to even access it in a codeless UI fashion. You can put a cell within your Jupyter notebooks. You will get a clean UI where you can specify, hey, this is the computation job I want to run. These are the data sets that I have, and you can run this. And the third important part here is these, I guess the first part is for us, like internal developers to manage SPCs. The second part is for users, right? Say users want to run an analysis on something which is already there. The third part is the contribution from the developers, model contributors. So we provide them we provide APIs for them so that with little or no modification for their existing code, you can port your code to run on HPC environment. Of course, it wouldn't make your code parallel, but will package your code in such a way that you are able to run it using containers and those kinds of things within the environment. If your code is intrinsically parallel, sure, we can use the parallel capabilities of offered by the high performance computing. If it is not, we could use like a smaller set, I guess, based on what is available, and you have larger access to memory and data sets. So essentially, it's a scalable middleware for enabling high performance and data intensive geospatial computing and research through our, I guess, the CyberGS Jupyter environment. Here's kind of a little bit more details in terms of what we had there. This was there in a Gateway conference last year, where we talked about the architecture of this computing core that we have. This includes our 3 layers, which is the API server to manage our API access. Then we have the connector and the maintainer pool, which basically maintainer manages a job, how to access it to the, how to manage a job, like how to go submit it, how to run this, how to get the results back, to check the status, all those kinds of things the maintainer does. And there is a connection pool basically so that we don't flood HPC with lots of connections. So we have a set of connection pools where we say, hey, we establish connections to certain HPCs and we maintain that connection for a longer time so that multiple jobs can use it. Talking a little bit more about our API server, it provides a RESTful user interface and authentication to various components, as well as it pushes the job to an internal queue, which the maintainer pool consumes. So between this API server and the next one, which is our maintainer, we have this pool that we maintain. And then, as I said, we have a lot of maintenance workers which are running, and the next maintainer worker, once a job is submitted, if there is a free maintainer, it will look at that queue and it will take that and it will establish a connection to HPC through the, I guess, the connection pool. So we have the connection pool. It will say, hey, when I start a maintainer, it says, give me a connection pool to the HPC I'm interested in. If that's not there, the connection will be established and connection pool will be returned. And then that connection pool will be used for that job. If it is already there, it will kind of reuse it. And we do a lot of computer science kind of implementation in order to make sure that these things work properly. And last thing we have is the SDK. I have the GitHub URL there for you to access, and this is an open SDK. Basically, what it does is it provides you a seamless access, even an interactive codeless access to access HPC or cyber infrastructure, and it basically runs on any Jupyter client. Of course, it's installed on CyberGSX. So once you go to CyberGSX, you can already find it installed and use it. So it integrates the CyberGS core functionality within the Jupyter environment. So from the Jupyter environment, you can talk to the core and then submit to HPC. The last portion with this was the compute contribute, where we saw where we let user how to contribute the code. I'm not going to talk more about this, too much about this, but essentially you could do, you have a GitHub repository where you can say, hey, I have this GitHub repository. We have some mechanisms for you to contribute this code. Say, do some manual checking. We'll ask you to develop some minimal, not changes, but like extra manifest file that you would add so that we know what your code is, what to run within your code. And then we'll use a particular GitHub commit, which has been checked and locked to that commit, so that when you run the job on HPC, it will run that particular commit once it has been approved. So that's essentially the two portions in terms of democratizing access, the tools that I talked about, CyberGSX, then the CyberGS compute. Lastly, I guess we want to talk about democratizing access through education. And there we have a project called the R of CI, which basically aims to, this is an NSF project I'm part of. I'm a co-PI on this, where we have, if you can go to rofci.org to find out more about this. But essentially what we are doing is we are creating lessons, hour-long lessons. This is modeled about after the hour of code, where you could, we are generating hour-long lessons where you could learn the basics of cyber infrastructure, cyber GIS, and those kinds of things. So this is So we'll be developing 17 hour-long lessons. We have a little bit more than halfway through it at this point. So you could see these lessons, and you could run these lessons on interactive Jupyter environments and things like that. So this is going to be integrated with CyberGIS X. Though you can run these lessons on CyberGIS X, but we'll make it easy for you to launch directly on CyberGIS X at this point pretty soon. So you could try 1 hour long lessons. We have a gateway lessons as well as 17 other lessons on various topics, which includes cyber infrastructure, parallel computing, big data, computational thinking, interdisciplinary communication, spatial thinking, geospatial data, as well as spatial modeling and analytics. So these are all going to be hour-long lessons. We'll have beginner and intermediate lessons for these, for all the things. And then we have this gateway lessons where we say it's mainly called the Hello to Cyber Infrastructure. It gives you basics of what a cyber infrastructure is and gives you that concept. The other part of this, if you want to learn more, is, of course, we have at Illinois, we have an online graduate degree in CyberGIS and Geospatial Data Science, including a bachelor's and a certificate, for which I'm serving as a program advisor for. So anyone is interested can feel free to visit that URL and contact me. So democratizing access. So I've talked about, I guess, what CyberGIS is. What is an era of CyberGIS? Democratizing access through CyberGIS X, meaning like easy to access platform, democratizing access to HPC, as well as democratizing access to education. So those three concepts that I talked about. And then looking ahead, what do I see happening in the near future? So we have this project called the NSF HDR, Harnessing the Data Revolution. This is an institute called the Institute for Geospatial Understanding through Integrative Discovery Environment, and iGuide for short. I'm serving as the managing director for this project, which essentially is kind of a progression with what we have been doing at Illinois for the past decade. And again, focusing on doing like high-end computing with geospatial data, big geospatial data, using transforming geospatial data-intensive science and education through AI and CyberGIS is what we are trying to do. And we are trying to establish a platform for geospatial data discovery environment. So that's, we are making steps, and I think this project is putting it all together. Not only, I guess, developing the tool, but also conducting the science behind it in terms of sustainability and resilience and those kinds of things. So we have like 6 focus areas, including convergence science, catalyst, geospatial AI and data science, cyber infrastructure, core cyber infrastructure capabilities and services. These are on the intellectual merit side. And on the broader impact side, educational and workforce development, engagement, partnership, as well as evaluation and knowledge transfer. So we can go to the URL and find a little bit more about the iGuide project. And this is kind of a broad vision of iGuide that I see a lot of things happening in iGuide in terms of resilience and sustainability and using geospatial data, big geospatial data in order to make sustained progress and advance in science in these key scientific areas to enable convergent sciences. So lastly, a simple acknowledgement to all the grants we had over the years. That definitely is worth it. And of course, I'm happy to take any questions and comments. Thank you.
Thank you, Professor.
Any questions or
Any questions?
Hello, yes, sir. Hello, am I audible, sir?
Yes.
Nice presentation, sir. I got to know very much detail in the detailed cyber GIS architecture. But like my discrimination question for the architecture perspective, in a monolithic architecture and microservice architecture, like how cyber GIS differentiate in both the architecture.
Cyber GIS, okay, so it's not a monolithic architecture in kind of one. So it is, as I said, it's a lot of components that you have. And if I go back, maybe this is the maybe you have. Let me see if I can find. Maybe I went a little. Oh yeah, I think this might be the thing about it is kind of, it's more of an ecosystem rather than just one system. So what I presented is not a single system, right? So it has various components. So if I were to talk about architecture in a computer science kind of perspective, we'll have to talk about, like, say, something like cyber GSX. Let me take cyber GSX as one of the example of talking about the architecture, or cyber GS Jupyter for that matter. I guess. So this one, you can see it has like various components here in terms of the hub, the Jupyter, the compute, and BIS. So hub is essentially, you can think about it as a web environment. It is based on WordPress, and it has all the tools associated with it. It has connection to, as I mentioned, the CI logon, where you could, it has been integrated, so you could use the CI logon. So that's kind of a third-party service that has been integrated. On Jupyter side, if I talk about purely CyberGS Jupyter, what it is, it's based on that itself is a distributed architecture and based on microservices system. It is based on Docker Swarm, and we also have a version of Kubernetes that we are working on right now. But on Docker Swarm, it has so the one which is deployed on production uses Docker Swarm, where so you have a number of nodes which are there, and then each of when the user launches his own kernel. So when you log into the system, you launch a container. So each user is associated with a container for themselves, and that container can run in anywhere in this Docker Swarm, right? So it goes into this Docker Swarm and it runs within the Docker Swarm. So that's kind of a service that's provided, and it uses the data sets which is coming from an NFS kind of file system, shared file system. Now, when it talks to compute, it is talking to compute, which also provides a service, which is a separate service, and it is the compute service is itself also Dockerized. So you have the compute core, which is Dockerized. Also, it has like a number of, as you might imagine, it has number of databases, so PostGIS database and MySQL database. So those kinds of things it has in the backend that has been Dockerized. And then for every user job, the maintainer, the connection pools, those have been Dockerized. And when you talk to cyber infrastructure in the backend, when you submit this job, so that is so that is also a distributed environment. So if you think about it, it's definitely not a monolithic architecture that everything is built in one place. It uses a lot of container, but so for each of these components, I could have a traditional kind of an architecture, computing architecture that I could present.
Okay, thank you, sir. And sir, one more question. Like, can we provide the replication backup server in HPC ecosystem?
HPC, yes, the well, there is. So there are two parts of what you said: replication and backup, right? So replication is yeah. So those are two different things. So backup is more like yeah, you have a backup which you can use later, and most of the HPCs, if you put it on their file systems, they actually automatically do backups as well as they do like RAID kind of things, so that on the back end, so loss of a particular disk or a bunch of disks might actually not affect it. But they also have like backups. If you mean replication, as in like say replicating data which is live usable, for some of these things we have to do. So for example, when you do CyberGS compute, you do it on our platform, like on the CyberGS X and on Virtual Roger. So for example, if you submit a job to a HPC, which is on a Exceed side, which is on a different system, so you have to copy that data over, so which is replicating it. We use tools like Globus, things like that, to copy these data seamlessly in the backend.
Okay, got it, sir. Yeah, thank you, sir. Thank you very much.
Yep.
there is a question in the chat box from one of the participants. So do you conduct any training session on cyber GIS?
Yes, we do conduct occasionally. It is kind of announced through our CyberGS channels and things like that. There is also a free Coursera course you can look at, but it's more on the conceptual side of things. But yeah, if you want training on many of these, we do trainings for the CyberGS X tools, and services. And of course, I mentioned to you the R of CI. That might be one of the things that you can think about as the training. So we have some of these which is available. Not I guess it will not tell you about CyberGIS tools in particular, but it will talk about the concepts associated with what cyber infrastructure is and what CyberGIS. So essentially, this covers the fundamentals behind CyberGIS.
Yeah. Any questions from audience?
Yes, sir. I have one question that, sir. Now, first of all, I want to thank you for your nice presentation, but I am unable to understand that what GIS cyber is, what you have built, that which spatial algorithm it is being focused on.
Spatial. It doesn't focus on a particular spatial algorithm as such. It makes, so it is focused on, I guess. So it's not a particular algorithm. We are kind of not doing a single algorithm. Though some of the researches we have done in the past have done like spatial, I guess, interpolations and those kinds of things we have done in the past. Yes. But the system which I presented is not focusing on a particular algorithm at all. So what we are trying to do is, as I said, the democratizing access part was one of the main things that we are doing. So many of so we are not focused to things that we developed. So if you look at the libraries that I presented here, including our CyberGIS libraries, which is for accessing. So we have all these various libraries and tools that are available. So for example, like the hand, that's something we developed, and some of the urban kind of analysis we developed, that's available. But like other tools like PySal, like geospatial tool, network, or
GeoLSTM or anything.
What's that?
GeoLSTM, like.
Yeah, we could add new things. So that's the beauty of the system. We could as I said, like you have this kind of scalable architecture where we use like the easy build stuff, where you could have multiple versions of the same software, as well as like continuously add new software without like affecting things that is already there. So our goal, so at least the goal from this talk and this research that which I was trying to present was not on a particular algorithm that what we did, but like a holistic view of what CyberGIS is and what is the tools and things that we have created in order to make it accessible to everyone. So the things that I presented, CyberGIS X, even compute, you can access it. R of CI, I guess, even those three things, anyone on this call can access it. Without having to actually have a collaboration with us or anything like that. So you can use it for your classroom research, for your classroom use, for whatever. So that's these are all tools that are available and out there.
Okay, sir. Thank you.
Not just for the US. Okay, not just for the US. This is also available for people in India.
Okay, sir.
This players from the geospatial technology also can be accessed from company sides.
Can you repeat that? I did not get it.
From company side also, are they able to access and put their tools, etc. here? Open source tools?
Mostly it is open source tools. It's not, because this is made accessible to everyone. So we are not doing any licensing or anything like that. So any tool, if a company wants to make a open source tool available and that's accessible, that's perfectly reasonable here. So. But of course, there are opportunities if a company wants to kind of develop a collaboration, we could do something which is separate and not accessible publicly.
Okay. So suppose some company wants to put their own tools over here and test it because the data is there. So if they want to test their own software or algorithm on this, is it possible?
Yes, that is possible, definitely.
Okay, thank you. So I think that I was similar kind of things we have developed something. Means in my part of research, we have developed similar kind of things where for cancer treatment, a similar kind of setup we have developed. Like the key algorithm they can develop, and companies can come and the doctors can provide the data. Similar kind of things. So this is a very wonderful tool because we have also developed a similar kind of things.
Right. Yeah,
So,
and this, yeah, this has been like definitely. I should say this is not my entirely. This is not entirely my work. There is lots of people behind it, of course. With the CyberGS Center, and yeah, definitely, I need to say that's definitely the case, and we are happy to develop collaboration with anyone if there is an interest on any of these.
So my question related to the local context here, like I know like these kind of software tools they are developing in Europe and US. So what do you think about that tools availability in India? Like are there any big research which is going on in this front end, especially on this cyber GIS on developing some platform for the Indian GIS data sets, etc.
I'm not sure actually in like from within India where people are doing in this context, but I imagine like some of the people in this call definitely will have much more better understanding of the Indian context of the research there. But what I would say is from the Europe and like the tools that we develop, I want to emphasize this, that these are not like US specific things. So the data set that we can host, like we can host any of the data sets here. You could upload your own data sets, some of these things. If it is too big, you can work with us and we have some access to storage. And if it's publicly available data set, we can definitely download and store this and make it accessible to everyone. So those kinds of things, it's not restricted, but it is driven by research. So what kind of data set we currently have is driven by what people are using, right? So this is like, so we don't download things just for the sake of things, but if there is a collaboration and people want to use it, they want to use it. For example, the hydrology of the hand example I brought up, we had some collaboration with the researchers where they wanted to do this at the national scale. We downloaded those kinds of data sets and we worked with them to make it happen. So if there are research in the Indian context where we want to, there is a certain things people are interested in looking at, and we want to develop a collaboration, I don't see from a technical point of view there is any barriers to stop access.
Yeah, one last question. So since we are talking about the advanced geo visualization, is it having a three-dimensional visualization also, or only two-dimensional visualization?
This is not a three-dimensional; it's a high-dimensional. In like it's not a 3D object, but it is high-dimensional, as in like you could do multiple data sets at the same times and compare between data sets. This is one of the research done by a faculty here, so they will be able to do a much better job of explaining it than I do. But essentially, the context is you could have multiple maps, and you could look at interaction between, like, if you change a parameter, how does that change in one map versus comparing it with the same parameter set differently in the same spatial extent on a different map. So you could do those kinds of things, and you could do plots and those kinds of things. So that's what it is. So you can look at the CyberGS X website, and where we will have information about CyberGS Viz as well.
Okay, thank you. Participants, any other questions?
Yes, sorry.
I don't think any other questions. So thank you, Prasad. Thanks for giving us a chance to listen to your wonderful voice and research. Thank you.
Yeah, thank you so much. And I guess feel free to reach me via email. My email address is there, and anytime feel free to contact me.
Sure. Whenever you are coming to India, also please let us know so that we can have a session at IIT Tirupati also.
Yeah, I'll definitely let you know. Yeah, I'm definitely, hopefully I'll able to visit India next year after the pandemic has slowed down a little bit, hopefully. So yeah, definitely we'll talk to you. I guess we'll reach out to you next year.
Okay, thank you.
And yeah, in the meantime, if there is any opportunities, I'll happy to give this talk or anything like that, or to develop collaborations.
Sure. Okay, sir. Thank you.
Thank you.
Thank you, sir.
Bye.
So we have another 20 minutes. Professor Sasi will join 7:30. Could you stay with us? We will start at Hello, Professor Sasi. Could you hear us? I think your mic is on mute.
Okay, can you hear me now?
Yeah, yes, sir. Yes. So
Okay.
we'll wait another 10 minutes. Participants are joining.
Sure, sure. And I just wanted to ask if we can check the PowerPoint slide show.
Yeah,
Can I
sure,
try
sure.
sharing?
Sure, sure, sure.
Okay. Let me just try that.
Yeah, we are able to.
Okay. All right. Are we able to see my slides?
Yeah, yeah.
Okay. Okay, great. And I'll just advance it 1 minute. So you can see the
Yes, yes.
slides. Okay, great. So just one or two other small questions. One is for time management.
Yes.
So, so the allocated time is 1 hour. Is that right?
Yes, sir.
Okay. So if, possible, if you could give me like some guidance, maybe half an hour is done.
Okay.
40, yeah.
Sure,
And question answer, you want to take it as we go, or you want to hold them?
You can go as if the participants are asking questions, you can stop and then ask.
Okay, okay. So so there again, if it will be helpful, do you expect them to maybe use chat or question answer? Is there?
Yes. Yeah, some are asking in the chat. If they are asking in chat, I will stop interrupt and then I'll post a question. Sometimes they used to ask it by unmuting themselves. So in that case, it will be asked.
Okay, so if it will be great if you could monitor chat, because sometimes it's a little difficult to track both slides.
Sure.
Those would be good. And last question was: is there a way to set up maybe just a generic quiz with 1 question, 4 choices, just A, B, C, D?
Okay.
Okay.
Right now, it may not be possible because I have restarted the meeting. We disabled the
okay.
But probably you can type the question in the chat box where they can answer it.
Let people use chat. Okay, no problem. Okay. So also, if you had done any survey in terms of background of the participants, that may be helpful as well. So one is maybe disciplinary mix, are they primarily computer science, or do we have people from other side, GIS, civil engineering, geography?
Yeah, so we have mostly civil engineering students are there, many civil engineering students are there, and few electrical and even mathematics students are here. So totally about 150 participants they have registered. Some of them are watching directly from the YouTube also. Some of them are watching, some of them are here, and they ask the questions directly. So we have various disciplines, like we have 10 industry persons and about 50, 60 researchers are there, and students about remaining are students, EG and PG students are there.
Okay, and what is the mix with undergraduate versus masters versus PhD?
So about 20% is undergraduate, remaining 20% PG students, then researchers and remaining are researchers.
Okay. Okay, good. So also it may help when people ask question if they can simply, just add a line about their discipline and the level, that sometimes helps in kind of crafting the answer, right? So,
sure.
So that will be great. Wonderful.
Good evening, everyone. So here with us, Professor Sasi Sekhar is going to give a talk on what is special about GeoAI and spatial data science. When I thought about this workshop, the first person who came into my mind is Professor Sasi Sekhar. After contacting only, I contacted the remaining people, and he also kindly agreed for giving a talk here. So let me brief about Professor Sasi Sekhar. He is McKnight Distinguished University Professor and Distinguished Teaching Professor at the University of Minnesota, and he is a UC Berkeley alumnus. He is a leading scholar in spatial data science and spatial computing issues, GIS, etc. He is also serving Computing Research Association Board and also co-editor of some of the Springer journals like Geoinformatica. Also, he was earlier he worked as president of the University of Consortium (GIS) and many other national academics awards and other things and recognitions like IEEE Technical Achievement Award, UC GIS Education Award, IEEE Fellow of AAAS Fellow. Also, he contributed many algorithms, especially on the route planning and spatial algorithm, mining, etc. So, without further delay, I hand over the session to Professor Sasi Sekhar. The floor is.
All right. Good afternoon, everyone. So, and thank you, Dr. Mariappam, for a warm introduction. So, without further ado, let me actually share that, come to the topic. So, I'll share screen and then PowerPoint slides. So, so I hope these PowerPoint slides are visible. And let me try to go to slideshow. Okay, great. So I hope everyone can see the slides here. Right now it's the title slide.
Yes, sir.
Okay, wonderful. So before going into the topic, let me first give you a little bit of sense of my color of glasses, because this topic is very multidisciplinary. In fact, I heard many of you are coming from civil engineering, and certainly surveying and many parts of this area were pioneered by civil engineers. But there were many other disciplines as well. You can imagine geography, electrical engineering helped with a lot of remote sensing activities and so on. And I actually come from computer science side, which is sort of a new kid on the block. But as you know, in recent years, they have certainly made major contributions to this area, because many of these data sets are becoming very big. And in order to store them or analyze them, you need state-of-the-art computing infrastructure and ideas. So I stumbled upon this area about 30 years ago after coming to University of Minnesota. And lots of things, that I learned from this area were actually, they started from civil engineering colleagues, because one of my first projects had to do with routing. What you know as Google Maps today were research projects back then. And the Center for Transportation Studies, which originally was housed in civil engineering, they were trying to build a team across disciplines. So that's where I kind of started. And most of the things I know about this area, I learned by doing. I don't have any formal coursework. Right? But so over the year, I started with this database perspective. This is a book from 2003 that I had to write to teach my own courses. But around 2006, with smartphones, advent, this technology became very popular, like Google Maps kind of things. Right? Billions of people started using it. And also Wikipedia was picking up. So there was demand for, encyclopedia, like, broad audience articles. So I was fortunate to be given responsibility to pull together people and publish, to lead this encyclopedia of GIS. I think first edition was 2007. The second edition was around 2018. And now Springer just asked us to start work on the third edition, because these have been popular, 250,000 downloads or more. Also within computer science, there were no journals. So I was asked to help coordinate this journal. And these, after that, I think even within computer science, enthusiasm has grown. This is our main society magazine. So 2016, you see a cover article from our group. And MIT Press just a couple of years ago asked us to write a short book amenable to all professionals, because the cat is out of the bag now, right? Everybody knows what is GPS. And if you're watching Ukraine war, people, more and more people are now knowing what's remote sensing. So there is enthusiasm, across a broad set of people in the society, right? So we should all feel very fortunate that the technologies we are working on is of broad interest. Right? So within this talk, I'll talk about two terms. GeoAI is a new term, and spatial data science, you can imagine, is a more broader traditional term, but I will try to define both. And at least from computer science perspective, try to say what is new, what is different relative to the generic AI or generic data science. Okay. And I should also acknowledge a lot of my work, I was fortunate to get support from National Science Foundation. So this is a project with urban planning community. Again, you can kind of say transportation science collaboration continues. We still have projects in the area. This technology is so pervasive in public health, it's important, and I'll show you examples. So during COVID-19, we were asked to analyze smartphone mobility data to understand the impact of the disease on that and so on. And you kind of see other areas, intelligence, and this is new on the climate change and so on, right? Agriculture is again, very enthusiastic, and they are getting big in this area. All right, so let's start with an old story. So we all kind of situate ourselves. And this story is still relevant because of the pandemic, but you go back to about 1854, right? So about 150, 60 years ago. And back then, cities were new, and they used to run into trouble in terms of cholera and plague and those kinds of things. And the science was not very well developed back then. People did not understand what caused cholera and how to spread, right? So first, a quick question. How many of us have seen this map of London cholera? Okay, in the chat, could you please type in if you have seen this map before? So if you are coming from public health or visualization, okay, a few of us have seen, that's great. So John Snow, as you know, he collected the data over several weeks of death in London, and he made this map. And in the map, he saw that these little dots are the deaths, right? They were not all over the place. They were concentrated in one area, what is now called hotspot. And that did not go well with the scientific theory at the time, which said the cholera was airborne. So, but based on this pattern or hotspot, John Snow also saw that center of this hotspot was a water pump, right? Broad Street water pump. So he went and suggested to City Council that we should, this pump may have something to do with the disease, so we should maybe take off the handle or something. But science was not with him, so it took a couple of days. But finally, one city official said, "Okay, let's take a chance," and they removed the handle, and that started to subside the disease. So this created a new hypothesis saying maybe the cholera is spread through the water, not air. And then Louis Pasteur and others, they started pointing microscope at the water, and then they saw these little things floating around, and the fledgling germ theory was boosted. So, so anyway, I think this is something which is, you can call it a broad data science story, but this map or spatial data, as you can see, its strength was to generate a new hypothesis, right? But one had to still follow through with the rest of the science, controlled experiments and theory development in order to develop the understanding. This was not the end, this is just the beginning, okay? And later on, we all know, civil engineers know very well, because of the germ theory and this work, the city design was changed, right? We created sewer systems, separated drinking water and wastewater. And in case of public health, and doctors started washing hands and things of that kind. So this has been a really good story in terms of the value of spatial data. And today, as you can imagine, this practice is very standard. Public health departments all over the world, they make maps of infectious diseases, and they look for geographic areas where concentration of a disease or a phenomena is unusually high. And if that's the case, they start looking at local environmental things to see if there is something that can be changed. So for example, National Cancer Institute does that. In case of COVID-19, at least the earlier phases, you saw that happening, all over the world, where they were looking for hotspots and trying to manage them, and so on. And now this paradigm where you start with the data and generate hypothesis out of the data now actually has been picked up across the sciences. This is broadly called the fourth paradigm. Some people, if you think about the big data and sciences and so on, you are seeing many other people trying to leverage the data. And sciences like astronomy, genetics and so on, they have benefited a lot, where you don't have a lot of physics-based, or simple forward model theory. They often benefit from looking at the data, generating hypotheses. But again, those sciences, they don't stop there. They still do rest of the scientific methods. Okay? So this is a broad data science story, which means, we start with the data-driven hypothesis generation, and we follow through rest of the science. Okay? Even in case of COVID-19, if you have seen, early days in China, in Wuhan, if you look at, this has been reconstructed, but you kind of see similar patterns, and that can be used to think about the origin of the disease. All right, so this is an old story, and you may wonder, so what has changed, right? And many things have changed, and you probably know some of them, and I'm going to just divide them into 5 pieces. The first thing that has changed is the amount of data, right? John Snow, it took him several weeks to collect a few hundred cases, okay? But today, we have so many sensors and satellites that we can collect a lot more data, okay? So this stamp is actually showing you sort of John Snow's days, Lewis and Clark expedition in the United States, when they had gotten access to the western part. It took Lewis and Clark several months to go down the river and collect the data, right? But all of us now know, even in last century, satellites were going up, right? And other sensors were going up. So, but there were few satellites last century because each one was big and expensive. So you could get a scan of the Earth every other week or so at a coarse resolution. But today, we have a lot more satellites. In fact, some of you know that even a single Indian rocket sent up about 100 nanosatellite, right? This was a few years ago. So the number of satellites has just proliferated. You can scan the Earth every day, and interesting parts of the Earth you can scan at a much higher frequency, maybe every once a minute or once a second on geostationary satellite. So essentially, the amount of data has grown up quite a bit. So these are the old satellites, as you know, like a bus, and these are the new Planet has hundreds of these, but these are nanosatellites, right? And many countries are launching that. And because of that, we can get very high frequency imagery of Earth at a pretty high resolution, right? And again, I will not repeat it, but it started with the visual band, and now infrared, and those things are also coming to nanosatellites. But the key point is there is a lot of data. Okay. Also, GPS has proliferated, right? If you look at the number of GPS receivers today, it's in billions. And not only that, if you look at clocks in all infrastructure, whether you are looking at internet or cell phone or power grid, all the clocks are being synchronized through the GPS satellites. And because of that, people actually think that if GPS satellites are disrupted, it will interfere with our lives a lot, and people, there will be big economic impact. So many countries are building alternatives to the satellite-based navigation, ground-based systems, and so on. And there is a good reason, because I said it's very important, but it's very easy to actually interfere with GPS. Particularly the US system is very old, and the power of the signal is not that much. So these things are happening, and people are doing that. But the main point is that both GPS, and GPS is also a great source of data, as I will show you in your smartphone and so on. GPS gives you the location, but if you accumulate the data over time, people get trajectories, and using that, a lot of information can be derived. And then remote sensing is another big one. So not only there is a lot of data, but people also feel this data is very valuable. So for example, remote sensing data, this is a report from National Academy 2019, and it estimates that the value of remote sensing data is over $1 trillion per year just for energy exploration and so on. Okay? So extremely valuable. Same way, the GPS that you have on your smartphone, on vehicles and so on. And many companies, as you know, the location-based services, they are collecting the GPS traces of phones and vehicles and so on. And this is a report which is a little bit older, about 10 years old. And they had estimated that if you just look at GPS trajectory data, its value would be $600 billion per year by 2 years ago. And some of that value is actually being realized by companies which are doing ride sharing like Ola in India or Uber and so on, right? So these things are very valuable. And beyond what you see in ride sharing and so on, or navigation, there are many other applications, okay, that people are trying to use this to understand patterns of life in many different ways. Okay? And I will show you some examples of such kind. Even, for example, vehicles, again, beyond your GPS trajectory, they can give you information about energy use or emissions, using which you can create new generation of routing systems to reduce energy use or emission instead of distance traveled or time and so on, right? So spatial data, availability has grown. People have understood its value, and it can allow us to do things, that we could not do before. And I will show you some examples, areas which were very hard to monitor before, and slowly they are becoming more visible, right? And things of that kind. So let me give you a few use cases to kind of see how things are changing in recent years. So let's first start with food. Because of Ukraine war, you probably have heard that, we are risking a major food crisis or shortage in the world, possibly once in 100-year event. Okay, but this has happened, recent past. If you remember Arab Spring, about 10 years ago, when there were a lot of chaos in this part of the world, and some people connected it to Twitter, but really it was about food prices. Okay, because back then again, people had stopped exporting the food, and food importing countries, the prices went up, and there was a lot of social chaos. Okay, so after that, the major countries which have the satellites, they came together and they said, well, we should cooperate, because using the satellite, you can see the general health of crops. Okay, and that's what is being shown here. So they came together, and every month they produce a report. Okay, they produce a report which kind of gives you a sense of the crop health worldwide. Okay, where green seems crops are doing well. For example, if you see India, China, Southeast Asia, they are doing pretty well right now. This is about a month old, and the next report is due any time now. But they can also tell that some parts of the world are not doing so well, right? The red ones. And if that means, for example, over here, if that means Syria, this may be Ukraine and so on, if that means that there could be food shortage in that country or countries which import food from there, then those governments have several additional weeks to take remedial action to import food from another source or take it out of storage or whatever. But the hope now is that you will reduce the repetition of Arab Spring, right? So fewer surprises you get. And this is quite amazing because, if you think about how, if we wanted to do something similar last century, it was far more expensive. US just wanted to look at its wetland, took them 40 years and $400 million. Contrast that now, within weeks, you can actually monitor things. And this is a pretty well, high quality data. This is used by every government. This is used by companies and so on. Okay. All right, let's look at another one. This is a little bit different. So as you know, open seas have not been easy to monitor in past, right? Because there were few naval resources to do that. But about 10 years ago, ships started reporting their locations, for a different reason. They wanted to avoid collisions. But now that data is getting aggregated, and you can start seeing patterns in that. So this data is called AIS. This is kind of showing you the locations of ships based on this data. Okay, this is you can say GPS trajectories of bigger ships. Okay? But in this data, you can actually see other patterns. For example, one of the things many people are concerned about is illegal fishing. Okay, and in here you can kind of see patterns of this kind. So here is a fishing vessel. The yellow is the trajectory, and you can start to see they're reporting locations for a while. Then they stop reporting, okay, for 2 weeks, no location, okay, and then they start reporting again, they go back here. So you can say, well, where could they have been? And the risky part is that there is a protected marine habitat right here. If they were going in there and doing illegal fishing, that's a worrisome. Although just because there is a gap, we cannot claim that they were doing illegal fishing. But what you could do is to say, okay, if that's happening, maybe the intelligence agencies can go look at the satellite imagery, because in satellite imagery, there are a lot of signatures of illegal fishing. For example, you can, sometimes the big fishes, you can actually see that in satellite imagery, the resolution is so high. Or you can see the ships, the drought change, right? If they are catching a lot of fish, then the amount of ship that is underwater will grow and things of that kind. But anyway, you can now monitor the oceans, which were very hard to monitor before. Here is another one. And so as I was mentioning, in addition to GPS track, if you are in a vehicle, you get other data sets such as energy consumption or emission. Okay? And based on that, you can actually compare now the two routes. So here are two routes in Ohio. This is out of our own project. And it actually shares these two routes. You can compare them not only on travel time, but also on energy consumption. And their rankings are actually different on two criterion here, right? So this route, even though it takes slightly longer time, but energy-wise, it's more efficient. And as we all can get concerned about climate change and environmental impact, we may ask for paths which have less energy use or less emission over paths which are faster or they are shorter distance, right? And in fact, this is already happening. So this is the future of your navigation systems. Instead of asking for shortest distance or travel time, you can ask, give me things which reduce emission or energy. And in fact, Google just announced that last October that they are supporting it. And let me actually have show of hand. Has anyone seen this part in Google Maps? Next to some of the routes, they are putting a leaf to say this particular route may have lower emissions than other routes. Has anyone seen that? Is it offered in India yet? You could put it in the chat. Okay, not yet. All right. So yeah, this is an opportunity. In fact, Tirupati is very close to right the auto industry, which is concentrated in Tamil Nadu in India. And this may be a conversation to have with auto industry to see if they can allow you the APIs to look at this kind of onboard diagnostics data and do this in India as well. Okay, so this is one big change. As I mentioned, the amount of data has grown. Many of you have heard this. How many of us have heard the term big data? Okay, so I'm going to type this in. Is this term something how many of us have heard this term, big data? Okay, yes, some of us have heard. That's good. So again, about 10 years ago, this was an initiative, and this is basically acknowledging that there are large data sets around and they may have a lot of value. Okay, good. But big data also implies that they may be so big that, oh, great. So Devesh is word working on it, right? So Devesh, could you define what is big data? When we say big data, what does it mean? You could use microphone or you can type it.
Hello. Yeah. I'm audible. So sir, we have a different time series data, big data contains the 4 V's, basically velocity, variety, and different patterns of life, etc. So we have a worldwide positional data, Twitter data. So we do the analysis on it, and we identify some of the pattern of life.
Okay, great, wonderful. So you said about the big V, 3-4 V's, and that's one way to define it. But some of those V's are basically telling us that the computers we used to use in last century, like these personal computers or mini computers and so on, they may not be sufficient to process this data. This is so big and coming so fast. So let's maybe briefly go to these platforms, and all of us know, this century, we not only have cluster computing, but we have cloud computing, right? So these data centers have not just thousands, sometimes hundreds of thousands of computers. And if you have petabytes of data, these kind of platforms are there, right? And these things have come to geospatial data as well. A lot of geospatial data is now on the cloud. and if you can process petabytes of data without having to buy very big computers or communications equipment, okay, which is a big change. If some of you had done satellite imagery processing last century, you will remember that you had to have your own, download links, special communication facility and big machines to do it. But because of cloud computing and other advances, this has gotten much easier, right? So this is a huge data, as I said, that are coming up, but you don't need huge computers or communication equipment locally in order to take advantage of the data. Okay, so I will next basically talk about this revolution in computing, which is now making it possible to process very large data sets with modest expenses. Okay. So first, I said spatial computing platforms, they range from very small to very big, right? So this is all it is showing. So in the middle are these workstation systems, ESRI, ArcGIS. Again, quick show of hand, how many of us have come across ESRI, ArcGIS, this software? Last century, this was the dominant software in this space. Okay, few of us, great. There were a few million users last century. But, as you come to this century, things have, gotten much more different. So Google Maps, or you see navigation services or ride sharing services, of course, billions of people use that. But there are other things on cloud computing, and I'm going to mention a couple of them in the next slide. And the key thing is that these big data sets are much easier to access today. We don't have to worry about the rest of them. Okay, so let's go look at least one thing, which basically says that, yeah, these big data sets are there, but you don't have to have big machines. So these are 3 cloud computing platforms. This is Amazon, AWS Earth. Google has Google Earth Engines, and this is NASA Earth Exchange. And I believe in India also there is one cloud-based repository of satellite data. Maybe if some of you know the name, you could share that. But on these cloud repository, a large amount of geospatial data is now available. And in here, let me actually ask, the data sets I'm showing on the left is, are we familiar with any of these data sets? And so cloud just, basically you can go to these places and use these data sets. Okay, Divesh saying yes, we know. Which one, Divesh, are you familiar with in this space? Can you name one and say what that is? SpaceNet. Okay, and what is SpaceNet about? What does it have in SpaceNet?
So, sir, SpaceNet dataset has a high resolution satellite imagery with embedded with embedded labeling of the feature classes. So we can train we can develop the machine learning model for the supervised learning and unsupervised learning. So we are developing our own algorithm based on the data.
Great. So not only there are raw satellite imagery, but some of the satellite imagery, you have labels for buildings and roads. And this came out of the DARPA project on geospatial cloud analytics. So even for machine learning, this is growing. But if you are, coming from the traditional satellite imagery world or other world, you will recognize other data sets like OpenStreetMap gives you street center lines for roads around the world, right? Sentinel-1 and 2 from European Union is a data set that people use in agriculture and other land cover mapping and so on, right? Landsat and MODIS, these are the traditional data set. So, and same way as even some of the Indian satellite data sets have gone on the cloud computing. So the point is that, yeah, these data sets are big, they come very fast, but you don't have to be intimidated, in terms of using it. You can go to these cloud computing platforms, and they're becoming as easy to use as your navigation and ride sharing systems. Okay? And that's the main message I wanted to give here. Let's maybe continue to the next one. Okay? I will skip the others if you're not interested, but they have different use cases. Okay, so let's next go to, so we have a lot of data. Okay, and we have a lot of compute power. Okay, once you have plenty of data and compute, then as you heard, machine learning and AI becomes possible. Okay, and so we are kind of going to now go to these, what I'm calling spatial data processing, but some of the people might call them AI and so on, right? But if you're coming from this world, you may find the word AI having a slightly different meaning. Okay, so this word, we actually use a word, a phrase called geointelligence. And this is coming from security agencies. As you know, geographic information was very valuable for security applications for a long time. People collected maps were sensitive and so on. So even today, many countries have these agencies which collect a lot of geographic information just to be aware of, to make sure the adversaries are not making designs on your country. Okay. And AI in this world, we think of them as augmented intelligence, because in past, when this data was collected, it had to be processed manually. And now with computers, you can process them better. So let's give you an example. So here is another imagery that I'm showing you from 1960s. Has anyone seen this imagery? This actually was very important in terms of world security, almost led to a major war between United States and back then USSR. Who recognizes this remote? This was taken from a plane flying over Cuba. Anyone seen this imagery? And this is, okay, no, all right. So this is, if you see, there are two triangles here. So this is essentially a design of a Russian missile site back in 1960s. And one of the US airplane, flying over Cuba, when they took pictures, they saw one of these in Cuba. And that sent red flags all over the place saying, oh, Russia is building missile sites in Cuba. Okay, this is what led to the blockade of Cuba by John F. Kennedy and Khrushchev, and Kennedy had to negotiate. Now, so back then, this was all manual, right? I mean, this was a photographic reel. They developed the film, and analysts were looking at it and saying, oops, we are seeing something which is a big red flag. Okay. Now, today, when the Ukraine war started, as you also remember, they were watching satellite imagery and predicting that Russia is going to invade because they are accumulating so many military equipment and they're surrounding Ukraine. But today, it's a little bit easier because some parts of that imagery is processed through computer algorithms. So when we look at imagery today from satellites or spy planes, then they look like this. So not only you can see these vehicles, but it can actually automatically, you have done object recognition and classification saying, there are planes and the plane is of this kind, right? So many planes of this kind, and there is, the tent, and there is other stuff like that. So this is sort of being done through computer algorithms. Some people will call it AI because computer vision and image recognition people have developed some new technologies to which aid in that, right? So let's go and talk about GeoAI. By the way, this has become a very big issue now. Of course, this started with other applications like face recognition, but their success in those areas is much, more controversial. But in case of military intelligence, this is extremely valuable. In fact, so valuable. Okay, question from the audience. Okay, please switch off your microphone unless you have a question. All right, so this one, I wanted to show you, basically there was a discussion that there should be export control on this. And it's a very simple technology. In fact, I'm going to ask how many of you have actually gone through this process because some of you are using the machine learning data set. So this one, basically the technology that came from neural networks world, the convolutional network, and then ImageNet, benchmark showed that this deep convolutional networks can do much better job of recognizing imagery than the competition, right? But it's a very simple technology. You first start by creating some learning samples, right? So you can go in the satellite imagery and say, this is a house, this is a road, this is a vehicle, right? And then you kind of, expand your learning set to make sure it's a little bit diverse. It's not so that, particularly in geographic images, there are things that vary, like intensity varies and so on. And once you have done that, you train the neural network, and now you can use it for analyzing new satellite imagery, right? So a quick question, how many of us have gone through this workflow? Could you type in? So for example, Divyesh, when you were working on SpaceNet, did you use this workflow or you were using something else?
No, sir, we didn't follow this workflow. I got to know first time.
Okay, so you did not use the CNN, you used a different method to analyze those?
Yes, sir, we are using a YOLO-V5 library.
Okay, all right. Has anyone used this deep convolutional neural network?
We have used it for some of other but not for XPC and GSPC. Similar.
Okay, okay, good. All right, but as we all know that this is a technology, deep neural network, which is right now, experimentally doing better than traditional computer vision algorithms to recognize objects and so on. Okay, and this is being used widely, and I'll just show you a few examples. So people are using it to analyze satellite imagery to find different things. And again, I'll first give you the contrast. So if you go to about 10 years ago in Haiti earthquake, people had left the town, and so you couldn't even get the relief supply there. So back then, in order to find people, first, we had to do manual feature selection. And it turned out the blue color tarp was a telltale signature because it's often available in Haiti and it's very unnatural, right? Most of the Haiti is green. But once you found the feature, this was done by hand in traditional computer vision, then you could very quickly go and find the objects of interest. But what deep neural network is doing is to combine these two areas, right? So it does feature selection and prediction both. And because of that, you have a little bit easier workflow, and experimentally, it seems to be doing pretty well. So a lot of people are switching to this workflow. Okay. And this is sort of the crux of GeoAI. So I'll show you a few examples from our own group. So so here, if you're looking at, for example, vehicle detection, right? So this is the input image. And through CNN, you can go and find these boxes. So YOLO is one variation of that, which can find these boxes. Of course, you can refine it a little bit. So for example, our group, we said, well, these boxes, if you're always making their sides parallel to the axis, which is what traditional CNN or YOLO does, your accuracy will not be as good as if you allow these boxes to be rotated. Okay. So these are small variations, but what it is demonstrating is the space net problem, right? Given the aerial or satellite imagery with vehicles or houses, you can find them in a reasonably accurate way. And here are the houses example. It is showing the two types of boxes. You could also predict other things. So here we had another project where we were trying to detect trees for a different purpose, and where we used two types of data sets, added the LiDAR, which gives you the height, and that's an additional data set, and you can actually map trees pretty well in an urban area. Right? So this is sort of, these are examples of what we will call GeoAI, and many other people are doing it for many other things. Even in our group, we have worked with this technology for urban garden mapping, and most recent work is to actually find grass and weed, in there. So, and things of that kind. Okay, so I will pause here, and that's mostly what I wanted to say about GeoAI, and see if there are any questions that we have at this time. Okay. So let's pause for 30 seconds and see if there are any questions before I go to spatial data science. And yeah.
In one of your earlier slide, you were telling like the response time in months and weeks, right? So what is the response time?
Okay, could you repeat the question, or let me?
Yeah, you were telling about the response time in weeks and months in one of the slides, especially with respect to some of the AWS data sets, right? What is the reasons for that? The response time was months and weeks.
I see. So okay, so I will have to go back to something specific. Oh, I see. You're thinking about the crop monitoring. Maybe GeoGlam is when I was saying that.
Yeah.
Okay. So first comment I was making is that if you go to last century and you were trying to get a crop report, what is the prediction of crops in India, right? It almost was done over months, because do you know agriculture census, how they do that?
Not exactly, but I have some idea.
Okay, basically they go to farmers and they do a sampling, right, and then you have to do the data cleaning. But as you can imagine, this was done once in season, so right, once every 4 months in India it would be done. Okay, so relative to that, the GeoGlam is much faster. They are publishing it once a month. Okay, now you could argue that, well, if I am thinking from computer science or AI perspective, I have a big cloud computer, I have remote sensing data, I can just push it through cloud computer, and within a day or few hours, I can look at the crop health. And you are right, you could do that. However, if you are going to give this data to governments and companies, and if lives are riding on that, then it's not good enough. You need to do a lot of quality control. Okay. So when I'm saying it takes them a month to publish it, it's, probably there is a couple of days of this remote sensing satellite data processing, right? Because there are 82 countries involved, they all do that. But then there is a fair amount of ground truth checking. So all these countries, then they call up some of the people in their farmland to verify that this is what satellite is showing, your crops are doing well or not doing well. What do you see on the ground, right? So there is a fair amount of quality control and then review and merging, and that's why they publish it only once a month. So the actual compute time may be a day or two or maybe hours, but by the time you do all the ground truth checking and make sure the data is reliable, they only publish every few weeks. Does that make sense?
Yeah.
Okay. Yeah, because you are from civil engineering, so sometimes computer scientists don't understand it. But civil engineers, you build a bridge. If the bridge fails, people die. That's not a good thing, right? So you put a factor of safety in there, right? And this is what our AI colleagues have to learn, right? We don't, Elon Musk says the car will drive itself, right? And then people die, right? So that's not a good thing. So it's not enough to just do computer processing. You want to make sure if life and death is involved, that there are other ground truth checking and other guardrails in place. Is that good?
Yeah.
Yeah, and geospatial data, many applications are like that. The cost of false positive is very high for us. So we can't just be cavalier like a lot of AI people, Okay, any other questions? Okay, so let's go to now spatial data science. As I mentioned, so AI for us is, okay, you can process things instead of manual, you're doing automation. But in Geo, we understand that your automation it's just a step and you still have to do manual quality checking and other kinds of things. Okay, so let's go to spatial data science. Basically, once you have found these vehicles and patterns in the satellite, you still need to contextualize it, right? Even if you think of defense, in Ukraine, borders, they might have seen a lot of tanks Russia was putting. But, you have to look at the context. If there are a million tanks and there are no soldiers around it, I mean, it may be a junkyard, right? It has no meaning. But if you see tanks and then you have soldiers and they are moving in a certain formation, that may indicate defensive or offensive maneuvers, right? So once you know these objects, you still need to find patterns and analyze it. And that's how life works. And that's what kind of takes us to this data science world where, so this is what we call it a virtuous cycle, right? AI also learns from the application domain that false positive costs are high and we need to be a little more careful than face detection or things of that kind. Okay, so let's go and look at what some of these ideas. And in this world, we learn that one size fit all AI may not be enough. You may have to do some other custom things. Okay, so why do we go beyond object detection? So this is sort of now telling you some of the limitations of AI. So for example, here in this image, you can run CNN and it will say, oh, there are two Obamas. There's one over here and one over here. But that's not the point of this image, right? When you see this image, what do most of us see here? I mean, we can count how many people are there, but that's not the main point, right? What most of us see is there is humor, right? The President Obama had a sense of humor and he could prank his staff and things like that. Okay? So AI still is very limited. Yeah, it can do object recognition, but a whole lot of other processing has to be done. Okay. So and these things are being realized in many other areas, and there are many research projects, right? Plus AI itself is bigger than vision, right? Deep learning is just a piece of AI. You have text and so on. So I'm just going to give you a few limitations of AI and so on. So first limitation is in sensing itself. And many of you know, coming from civil engineering, that computer vision focuses on RGB cameras, and that's not always enough. For example, self-driving car that Elon Musk is so proud of, they cannot drive in bad weather, okay, because their sensors are so poor. Okay? Some people are trying additional sensors, which Elon Musk doesn't believe it. But if you come from remote sensing, you know that these RGB sensors are very limited. Human vision is just a small band, and there are many other sensors around. You can use infrared, right? And for living things that help, even in agriculture, you can use microwave, radio, and so on. And computer vision, as I said, is very limited down here. And we can learn a lot from civil engineers, remote sensing colleagues, and so on in this area. So this is mostly aimed at the AI colleagues in the room. Same way, when we go to natural language processing like Google search engine, and they are also very limited. If you ask them some simple geographic question, for example, between a city and the country it is in, like it could be New Delhi and India, then most of us would say, well, the answer is 0 because the city is inside the country, right? But if you go to all these fancy Google, search or Siri or Alexa, notice that they don't understand that. For them, each city is a point, country is a point, and they start computing distance between the point, right? So there is a fair amount of things that AI has to also learn. Machine is still learning. That's the way we should put it, right? So GeoAI also has a lot of things to add. So in our world, there is a geometric library which is very, very popular. So this is called OGC, simple feature types. Again, quick show of hand in the room. Has anyone used this library before? Because this has been around for 25 years. It's widely implemented in software. If you have used Postgres, PostGIS, or Oracle Spatial, and it actually has things like polygons, line strings, beyond points. And it also has many operations, not just distance, but you can also say within or touch and things of that kind. So, all right. So at least some of us have used, that is good. And this should be one main takeaway from this talk. If you haven't seen this library, then please, this has been around for a very long time. There is no reason not to know this anymore, and it's widely available. So basic geometric reasoning you can easily do within this, right? So, but in addition, beyond this object detection, once you have these objects, we often look for patterns. So initially, when I started the talk, I was talking about hotspot patterns, and there are other patterns people look at. Okay, so for example, for a hotspot pattern, now there is a software called SAT-SCAN, and if you run it on the London cholera example, it will give you this circle, but in addition, it will also give you a statistical significance value. Okay. So you can make sure it's not generated by chance. So the probability of this dense circle coming together by chance is extremely small. Okay. Again, I don't know if people have used SAT-SCAN, but this is one pattern. And there are other patterns as well. So this is for the Wuhan, COVID-19 data set. People use similar methods. And then there are other patterns as well. So here is a pattern called collocation or segregation. And I'm showing you now the example from actually a different kind of map. So this is a map of cancer biopsies where you can actually detect every single cell. So you put it under microscope, it's a very high resolution image. Then you can run computer vision algorithms to find immune cells, cancer cells, and so on. But once that is done, then people want to know this pattern. They want to know whether the cancer cells and immune cells, so these are cancer cells, these are immune cells, if they are segregated, then that's not a good thing because you're less likely to cure the cancer, right? But if they are intermixed, they are colocalized, particularly the CTL, cytotoxic killer cells, if they're right next to cancer cell, then you have a better prognosis because those cytotoxic immune cells can kill the cancer cells and so on, right? So there are patterns of this kind that people want to analyze and so on. So object detection is the beginning, and then we look for these patterns, okay? So we'll talk briefly about spatial data mining, which is the methods for detecting these interesting patterns, okay? So in there, again, you can think about, oh, there are other data mining methods. Why don't we use that? And here is one, here are some challenges that make the other methods less effective, okay? And I will show a couple of them very quickly. So let me first show the simple, the noise challenge. So when you see this kind of a data, sometimes, if you throw darts at a two-dimensional space, just by chance, couple of darts may come very close and you may see, oh, this circle has more, density than average, right? But if you did that with public health data, then the risk is the following. If you get a false, spurious pattern and you say this neighborhood is a hotspot of disease, then that neighborhood gets stigmatized. People stop going there, right? And your politicians lose elections. So your false positive cost is very high. We don't want to do that. So because of that, National Cancer Institute actually puts a simple guardrail. What they do is they say, okay, let me look at different circles, compute density inside each circle, but then compare that density with what could happen if the data was completely random. Okay, so compare it with complete spatial random. And that way you have fewer chances of making error, right? So this you check the probability that it's not happening by chance, okay? So in this case, it's showing that the chance of such a dense pattern happening in London was less than 1 in 1,000. And you can put a threshold, and that way have fewer positive. And this is important because, in traditional data mining, when you use DB scan and stuff like that, they don't always do that. And they can easily give you spurious patterns. Okay. So for example, here we are showing you. So let me first ask you, how many of us know DB scan, which is, very popular in database world for detecting dense areas? Anyone who is familiar with this? Okay, that's good. Some of us are familiar. Very good. So we know that it's highly cited. But what I'm showing you here is they don't check for noise. So if I send complete spatial randomness to DB scan, it will still find some clusters, and that's not good. Okay. Now, if I send you this, where the TEST is the real signal with some noise in the background, okay, notice that DB scan will find the pattern, but also a lot of spurious things. Okay? So one of our recent work, we added the statistical significance testing, and now you see we can separate the noise from the signal, right? And these kinds of things are very important in spatial world because the cost of false positive for us is very high, right? And it's so just showing you some of the new things that you can do. Let me talk about another problem, which is a very classical problem, but data mining machine learning people haven't thought about it. So let me also ask, how many of us know about this modifiable areal unit problem, which is written here, MAUP? And then I will quickly walk through that. Has anyone come across modifiable areal unit problem? This comes from the GIS literature. Okay. All right, I see someone moving a mouse and writing something on the slide. Okay. All right, so let me explain what this problem is. So if you look at spatial data with red, blue, and yellow dots here, and I'm asking a question, which colors are correlated, then traditional methods like Pearson correlation coefficient face an interesting problem, right? They have to first discretize the continuous space to be computed. And if you discretize it, this way, the Pearson correlation coefficient looks like, red and blue go together, but yellow and blue don't, right? So negative and positive. But if I change the partitioning, you notice the conclusions flip. Okay. So this is, this is a problem. This, basically, if you change the space partitioning, many traditional methods, their conclusions change. And this is not desirable for spatial data. So I'm just motivating spatial statistics. There we don't try to divide the space, but instead we create a neighbor graph and we compute new interest measures based on neighbor graph, and they are a lot more robust. This is coming from classical spatial statistics. This is from our group. Okay. And based, and then you can formalize it. There is an interesting, math and notions like Ripley's cross-K function, which is defined on that neighbor graph. And they actually look at even statistical significance in there, right? So for example, if I give you this picture and ask you so this picture, you see a lot of locations of bluebird or houses or green tree or fire and so on. So let me pause here and ask you a simple question. In this picture, can you find a pair of features whose instances are often together? So let me give you 30 seconds to look for that, and you can put it in the chat. Do you see anything whose instances are together? This is, looking for the co-location pattern, and it's saying whenever I see one, I see the other. Okay. House and bird, great. So this is one pair. You see, when you see one, you see the other. I mean, not always, okay, not always, but like here, there is no bluebird, but statistically you see that. So this is called co-location. And in here, if you use the old association rule by space partitioning, you are likely to have this modifiable areal unit problem. But you can use things like cross-K function based on neighbor graph. And here, if you have two things which don't interact, then there the value of Ripley's cross-K is pi r square or pi h square. You can put a confidence band around it. But the pair that you just flagged, the house and bird, you see that blue line is way above what would happen to the complete spatial random pair. Okay. Another one, if you had stared hard, you would find fire and dry tea. But anyway, there are ways to formalize spatial data and make fewer mistakes. And our group has also given a method of this kind. If you're interested, you can go look at it. it has not only a reasonable statistical worldview, but also is computationally more scalable. The third challenge is this violation of IID, and many of you might have seen that. So here I'm just going to give you a quick view of what that is. In traditional statistics, many methods like linear regression and so on, they assume that your data samples are drawn independently of each other and from identical distribution. But spatially, this assumption means that this is what your data looks like, okay? Like white noise. But real spatial data, you see nearby things are similar. Okay, this is the first law of geography. And this violates this IID assumption in many machine learning, AI, and statistics method. So because of that, if you fit one size fit all methods to our spatial data, the performance is poor. And if you are interested, this has been formalized in spatial statistics, spatial temporal statistics, and you may have read about it. So I'm going to skip this and just show you a quick summary of different methods. Okay, let me actually complete this. So here, this is showing you the traditional methods like regression, neural network, decision trees. And here you are seeing newer methods which actually have some notion of spatial autocorrelation. So neural network world, when you go to convolutional neural network, you kind of look at nearby pixels, and that's the autocorrelation term. Okay. For regression, there is a model called spatial autoregression. This is quite common in spatial statistics or regional economics. If you like Bayesian classifier, you can incorporate the context in Bayesian classifier and so on. But the main point here is that if you are looking at spatial or spatiotemporal data sets, then incorporating the spatial context or autocorrelation will give you better predictive power as well as interpretability. So I'm going to, I know that time is running out, so I'm going to skip this part, but basically estimating parameter for spatial autocorrelation is computationally a little harder. And that's the reason computer scientists were quite involved in this. And I'll skip this part. Let me also mention one other challenge is spatial heterogeneity. Okay. So if you use, for example, we go back to the GeoGlam, right? Remember when we were doing the crop classification and you were saying, why does it take more time? You have to deal with spatial heterogeneity. So here are Midwest farms, very large and homogeneous. Here is a farm in China or India, right? So if you use the same machine learning methods on both, as you can imagine, your performance won't be great. So in case of GeoGlam, each country has its own machine learning algorithm to customize to their conditions, right? And then you bring the results together in order to improve performance. Now, if you can ask most, about AI methods like CNN, they don't model this. They try to fit a single neural network everywhere in your data set. And that's why unless you are aware of these things, your performance will be poor. So, so this is something that has been studied in GIS quite a bit. So here is a linear regression model where your individual coefficients like beta are thought of as a scalar, right? Traditionally. But we have GWR where these things are thought of as a map. Their values vary by the location. And a similar idea recently was brought to neural network by our group, where your neural network weights, instead of being a scalar, could be a map. They vary from place to place. And I just showed you why that makes sense. Okay, and they can improve your classification, as I mentioned. So let me maybe go to the last one, and then we can take questions. The last part is this visualization. As you know, if you have large amount of data, then sometimes visualization can help you cut through, look at the main point. So geographic data also, lots of different visualizations have been there in traditional world, maps and so on. And newer visualizations include spatiotemporal. And I just wanted to ask, how many of us have seen the face, Google time lapse? Because this, what it has done is to take 30 years or 40 years of satellite imagery, stitch them into video. So a few of us have seen this. That's good. If you haven't seen this, then maybe I'll just show you the Tirupati one very quickly, and then we'll go to the question answer. So this is showing you Tirupati area. And you can probably see the urban growth. I guess some of you have probably lived there. Can you confirm? So this is showing, 30 years ago, Tirupati's footprint was small, but now it has grown quite a bit. You see later years, you see a lot more construction. And this kind of a visualization, is helpful in understanding urban patterns and so on. Okay. People are also using 3D visualization, this is, and so on. So with this, let me actually try to conclude the talk, and then we can take some questions. So best way to conclude this talk is a call for action that came from UC GIS, and it it essentially says that, geospatial data, should be studied in data science degrees and curriculum in a special way, right? So first, this data is coming up. There is a fair amount of this data, and it's a very valuable data, right? Mackenzie said very large amount of value. It's societally important, right? But it has unique challenges, and you can't use just one size fit all, right? And you need to deal with autocorrelation, spatial variability, and there are other details. And people have developed special methods for this, whether they come from spatial statistics or spatial data mining and so on. And it's worth actually incorporating it in our curriculum and so on, right? So this is sort of, the last slide. Spatial data has already transformed our society. We are all using navigation, ride sharing, GeoGlam, crop monitoring is a big thing. And, there are more things we can do, and AI can also learn a few things from this space, to deal with these challenges. And so with this, I hope that, more of us will study this subject and support this subject. So let me stop here and see if there are any questions. And the next slide actually gives you some references and things of that kind. If you are new to the area, this may be a more general references. If you are more mathematically inclined, this may be a better reference, and so on. Okay. So let me pause here and hand control back for questions and answers.
Thank you, sir. Thanks for the participants. Any questions?
Hello. Yes, sir.
Yeah,
Am I audible, sir?
Yeah, please go.
So thank you for the nice presentation. Like, I got to know the very interesting and new thing. Sir, my question regarding the data mining techniques, like in the traditional data mining techniques and spatial data mining techniques, like how it different to each other?
Okay, very good question. So if you remember in the first slide on that, I was showing that there are at least 3 new types of challenges that you need to think about, okay, with spatial data. The first was a very simple challenge. First, I said if you look at satellite imagery or GPS track, you often see a lot of noise or measurement error, okay? And if you have to be cognizant of that, if you don't pay attention to that, you can get a lot of false patterns, okay? Whereas many traditional data mining techniques have ignored it, okay? And that's one reason, actually, if you go back to the beginning of data mining, remember statisticians were very unhappy with data mining. Some of them were calling it black magic and stuff like that, right? Because statisticians have studied the issue of noise, right, and uncertainty, and they have developed certain techniques. Unfortunately, our data mining colleagues, when they wanted to scale up to big data, many of them took the shortcut and they just dropped any statistical considerations, right? So this is one thing to remember. It's not news. I mean, this has been debated for a long time, but in spatial data, ignoring noise, ignoring measurement error can be very problematic because the cost of spurious pattern is very high for us. Does that make sense? Remember, I was showing you DB scan versus
yes, sir. Yes.
Right. Okay. So that's first issue. The second issue I was bringing up was something that's a little more specialized, but if you are coming from geography, you will know this. They have debated it for over 100 years. Okay.
Yes, definitely.
Right. The choice, if you partition the space, it creates some distortion. Okay. And unfortunately, again, our data mining colleagues have often ignored it. For example, look at spatial association rule. I don't know. Are you familiar with spatial association rule?
No, sir. Right.
No. Okay. Do you know association rules? Okay. Don't worry about it. For association rules, you need transactions. Okay. Space is continuous. So what they did was they would just cut up the space. Now, without realizing that their results were sensitive to how they partitioned the space. Okay. So their methods became very unstable. And that's problematic for many of our scientists. Okay. So you need to at least go to neighbor graph and define your methods on the neighbor graph, and don't discretize the space without realizing its ramification, right? That's the second question. The third one comes from statistical perspective, where remember I was talking about IID assumption, right? So many statistical methods you learned have IID assumption. Are you familiar with IID assumption?
Yes, sir. I heard first time, sir. IID.
Oh, okay, okay. Anyone in the room which has heard the IID assumption in
Yes,
you know,
sir.
like linear regression and
Yes,
so
sir.
on?
Yes, sir.
Okay, good, good. You know, it's a very multidisciplinary discussion, and each discipline has found some interesting challenge in this world, and it's good to kind of, you know, think about all of them. Okay, so I hope that helps.
Okay, yes.
Okay, all right. Other questions and so on?
Any other questions? I have.
Yes, sir. First, thank you for your nice presentation. I have one doubt that in for spatial clustering purpose, you are giving the priority to the spatial association based upon thing. But what is the guarantee that whether the spatial association after is it any threshold distance, or how we will determine that threshold distance, that on which basis we can assume that this spatial association will be invariant with respect to the certain leg?
Okay, very, very good question. Very, very good question. So you are saying, okay, with neighbor graph, in order to define neighbor, you have to have a distance threshold, right?
Yes, sir.
And right, and just like I was criticizing spatial partitioning, you could criticize that distance that I have selected, right? So yeah, it's a very good observation. So that is actually correct observation, and the property that we are defining, like Ripley's cross K, its value depends on the distance, and that's why in spatial statistics it is always, you know, listed as a function of distance. So if you remember the plot I was showing, otherwise I can go back to that slide. Let me go back for a quick minute and show you. So in spatial statistics, we acknowledge that, but fortunately distance is much easier to formalize and deal with than space partitioning. Okay, the number of ways in which you can partition the space is far more complicated than distance. And let me show you in Ripley's cross-K, I was actually showing you that. So in spatial statistics, you know, most functions are function of distance. So here is, are you able to see my slide now?
Yes, sir. Yes, sir.
Okay. So look at, you know, one example, Ripley's cross-K. So this is the the Ripley's cross-K, and notice the x-axis. This is the distance that is used to define the neighbor graph. Okay. And the value of cross-K, even for that house and bird, right? You see this blue line. For very small distances, it's not that different from random. You see what I'm saying? But
yes,
after a while, it starts to separate from the random. Okay. So in this case, even though I didn't get into it, but you will say, look, house and bird, they are collocated, you know, statistically significant if distance is possibly greater than 2 in this plot. Does that make sense? But of course, if you go further, if you take the distance to infinity, everything will come back to random. So you will give a range saying, look, over this range of distances, their collocation is significant. Okay. Or their segregation is significant if they were way below the random. Does that make sense? Okay.
Yes, sir. Yes, sir.
Yeah. So this is another important thing. Distance is a very, very important parameter in geographic space. And as you can imagine, in a lot of other machine learning AI techniques, also they use distance, but they don't often make things function of distance, right?
Yes, sir, but if you think properly that there is not only a certain factor, there is also one more factor, is that is direction. Because
yes.
when we are only assuming the distance, that means we are assuming that the spatial process is isotropic and intrinsic stationarity, but it is not always applicable in the real life.
Yes, yeah, very good observation. So now you are looking at the cutting edge of this world. Spatial statistical theories have largely assumed, as you said, isotropic world where distance. So distance part is better understood. See, most of spatial statistics was developed in last 100 years. And computers were not powerful enough to really take them very far, but now they are. So when you go to anisotropic space, like water flow, right? Water flow depends on the slope, right? So direction matters. But those methods are very new and they are more cutting edge research, but there is some literature on that where people are looking at direction, but absolutely direction matters for many, many phenomena, right? So you can make things better, you know, so current spatial statistics, from there, if you go to, you know, particularly spatiotemporal statistics or do things for hydrology and so on, then anisotropy is very important, and people are slowly thinking about how to formalize it. Have you come across some good methods for anisotropic data and so on?
So for anisotropic data set, yes, I have come across some copula-based method, probabilistic methods. But the problem is that the variation of the distribution, since the data set is anisotropic, so the variation of the distribution is so random that sometimes we have advised to use extreme value theory in copula. Then we can capture only that randomness. Otherwise, it is difficult.
Yes, it is cutting edge. If you are developing a thesis or you're looking for publishable research, I will suggest, at least try out these ideas and see which one works, right? But once you go to an isotropic space, what I have seen in the literature, there isn't a lot of consensus and people are trying different ideas. So it will be good. You should try your own idea, compare it with what others have tried.
Okay, sir. Thank you.
Great. Other questions or thoughts? Yeah.
Any other questions? I have one quick question. So I have seen like the dark data. The dark data means like the data is collected, but it is never used. And I have heard that in the geospatial data science, this is a large amount of dark data, which is there in all the things, but in geospatial data science, it is a large. So how do we address that issues of dark data?
I see. So this is a very good question. Of course, a lot more data is gathered, and not everything is in open space. Now, and this has been actually discussed for a long time, and it's getting better, right? Yeah. Now, is there a particular dark data set that is of interest to you? I mean, have you seen?
It's a generic question. It's not particular data sets. The dark data in the geospatial data sets.
Okay. So actually, geospatial world, I showed you the 3 repository, right? AWS Earth, NASA Earth Exchange, and Google Earth Engine. So geospatial world actually things are getting much better than other spaces. And it started with about, 2008, when USGS gave away its data. Before that, you had to pay for all the remote sensing data, okay? You had Terra Server or Google Earth, you had just one, scan of Earth. But at least in US, President Obama's time, there was Open Data Initiative, where, they thought that there is so much value. If you just open up the data, different people will go and do different things with it. And that can create jobs and value and so on. And that's why President Obama told all the federal agencies to open up the data. And that's why, you see the whole thing. USGS gave away the data set, and the time lapse was one of the first application. So people could see urban sprawl, people could see other things. And after that, many federal agencies have done that, right? So all the weather data of NOAA is in the same data set. And DARPA gave away the machine learning data set. And many new businesses have come up. You will be surprised. So GeoGlam or Crop Monitor, you saw, that's a more government application. But there are private companies which use this data set to monitor traffic in retail stores to understand the value, how economy is doing, and they sell it to Wall Street and stockbrokers. There is a company which actually monitors oil storage, because oil storage tank, the roofs are floating. So by the length of the shadow, you can assess how much oil is in there, right? And that's a private company, they are making money. And there are a whole lot of other companies which are floating around, right? So the key thing is whoever has this data, right, you have to think of their motivation, because initially these agencies were saying, well, we spend so much money and we want to recoup the money, right? And it took a precedent in US to say, well, just give it away, because for the whole country, this is better, right? Now, very similar thinking, I believe, has come to India, and last year or year before, I believe that, right, they opened up some of their data, but they said, okay, you have to be an Indian citizen or something, right?
Yeah.
Right. So I would say, a lot of this mindset, people who collected the data, they had the money, you have to somehow motivate them to share, right? And geospatial world, I think, is far ahead of other worlds in this space, because the amount of data that's actually been opened up in geospatial space is far, far greater than what has happened to else. But there are other data sets which, are, so for example, some of the defense data, for example, is still classified, and so on, right? So dark data problem is there. but it's getting better. Right now, I think the amount of geospatial data that is in the open, and if you like, let me just go to that slide one more time, just to give you a sense of how much data is open. And I believe something similar is happening in India. I don't have exact status.
Yeah, they framed the policy 2 years before, and that is open. So still they are framing, but the companies which is emerging is still trying to explore the data. Many competitors are there.
I see. So okay, yeah, I think it's just geospatial world. Right now, you have actually more data than most people have figured out what to do with. But let me just go over that one quick minute, if I can share screen. I didn't explain all those alphabet soup, but we should do that. So do you see my slides now?
Yeah.
Okay. So where is my mouse?
I think we lost the connection. I think sir, connection is lost. You wait for a couple of minutes. Okay, so for tomorrow we have the session at 10 o'clock. So please join. So tomorrow we'll not do the live streaming. We'll stop the live streaming because we expected that about more than 100 participants will come. So the live streaming is necessary, but we couldn't see more than 100 participants today. So we'll stop the live streaming for tomorrow. We'll just post it only in the stream. Yeah, if you want to leave, you can leave. If the professor joins, I just say thanks to him. He's back. Professor, I think there was a connection issues from your side.
Okay, yeah, sorry about it. So yeah, so if you like, I can still, can you show you the slide?
Yeah,
one
yes.
quick. Okay, so let me share screen. All right, so you see my slide here, right? Yeah.
Yes.
Okay. Yeah, so this actually is quite impressive collection. So let me actually show you a few of them. So NOAA is the weather agency here, right? So all their data set is on, as you can see, Google Earth Engine as well as AWS Earth, Sentinel is the European satellite. It actually is slightly better than old, Landsat and so on, better resolution and more up to date. So people who are in agriculture or land cover, they, this data set you can get from Google Earth Engine or NASA Earth Explorer. Elevation data, we were talking about hydrology and flood. So some of the LiDAR and other data sets are coming up. Okay. OpenStreetMap is sort of equivalent of Google Maps, a lot of street, center lines. This we heard about the machine learning one, right? and so on. So they're saying there is a lot of data set here. So right now, complaining about dark data in geospatial world is very difficult, So last 3-4 years, this has opened up amazingly, right? It started, as I said, about 14 years ago, but last 5 years, there is more data than we know what to do with. Does that help?
Okay, thank you. Thank you, Patrick. Yeah. So once again, I thank you for your nice talk. So whenever you come to India, please visit IIT Tirupati. We're ready to host you, and we can arrange some seminars.
Great. Thank you for the opportunities and very nice questions. Really appreciate it and look forward to meeting soon.
Thank you.
All right. Okay. Have a good night, everyone.
Thank you. Thank you, participants. We'll meet again tomorrow morning. Thank you.